compared to what maybe it's training or production, right? So you have different teams kind of taking care of different stages of the, let's say, MLOps process, and then there are walls, and there are situations where you throw your work over the wall to the next team or the next person responsible for it, and that obviously creates frictions and creates points of failures and things like this. One other thing that we see often is that there are oftentimes custom, like one-off bespoke pipelines to do different things, right? So a team might build a pipeline to train a model that's taking data from data warehouse, do some transformations and train a model. But then the same model needs to be served in production when you got time behind the REST API, and the team goes off, or some other team goes off and build a totally different pipeline that maybe relies on a Kafka stream, or maybe relies on other like technologies underneath. And then it's a nightmare to keep those things the same, right? So these are kind of the eye level challenges, and feature stores to a large degree try to address those challenges. But what we found is that tools only get you so far, right? So the challenges, you can't just magically drop in the feature store and all the challenges go away. You need proper process in place. So we work with users and we work with customers to try to identify some of the patterns and things that we always see and make for a successful implementation of a feature store, right? So the goal for us is to go to a complex system like this to a more well-defined system, a more simple system to understand and reason about, which is the FTI pipelines. We call it FTI pipelines. FTI stands for Feature Training Inference Pipeline. And the goal is essentially to split the process of developing a model and deploying a model into production into three independent logical components, which are responsible for different parts of this process, right? So we have feature pipelines that are responsible for reading the data and computing the features and producing those features. Training pipelines are responsible for actually building the models, and that includes everything from experimentation and actually training the model, the final model. And finally, we have the inference pipeline, which is responsible for taking the model and making inference both real time or also in batches. These are independent components. The nice aspect about this is that you can reason about every single component individually. You can have, for instance, different teams working on different components. You can have you can use different frameworks. You can orchestrate, for instance, the different different pipelines independently. So you might have a feature pipeline runs in a streaming way. You might have a feature pipeline that runs in a batch fashion every day. But you might have a training pipeline runs once a month or something like this, right? So the idea is not to have a single unified pipeline, but you have actually split them up. One thing that is missing here from the picture is how the three different pipelines work together to build these ML systems, right? And that's where OpSource comes into the picture, right? So OpSource as a feature store provides the capabilities to manage the artifacts, to manage the features, to store them and serve them and so on. But it also provides an open API, which are in Python mainly, but also available in Scala and Java, to be able to actually interact for these pipelines to actually interact with the feature store, right? So if you are writing a feature pipeline, then you will call the API to register the features with the feature store. If you are writing a new training pipeline, you will need the API to retrieve the features from the feature store, and also for the inference pipeline and so on, right? So OpSource provides the capabilities for these three pipelines to share the outputs and build on top of each other, while keeping them separated and independent. Now, if we look a little bit more in detail about the different steps, so if we start from the feature pipeline, right? The feature pipeline, as we've said, is responsible for computing the features and producing the features and potentially also the labels if necessary, right? The expectation is that you have a really clean system where basically you get a bunch of data and you do transformations, and then there you go, you basically have your features. As we said earlier, like one of the challenges that you have when you're building machine learning systems is that you're dealing with a bunch of different data sources with different timelines in terms of ingestions. So you might have, like I said, a streaming pipeline coming in that needs to be processed in real time. You might have a data warehouse, that is loaded once a day, once a month. You might have, existing pipelines that you need to combine. So there is a lot of complexity and a lot of different tools and different processes that are required. One of the challenges is that you don't have one tool to rule them all. So you don't have one single framework to do everything, right? So you have different frameworks, and different teams actually prefer different frameworks, right? So for instance, if you're working with small data sets, you can probably get away with pandas and polars. Maybe you're dealing with streaming API with streaming data. You might want to look at stuff like either Beam, Flink, or Spark Streaming. You might have data and data warehouse, so you might be looking at BigQuery, Snowflake, and leveraging their execution engine and so on, right? So there's different tools and different pipelines are written different tools, and they need to be combined with each other, right? The idea and the benefits of the feature pipeline is that all this complexity is actually hidden and taken away from the rest of the training pipeline. Inference pipeline is all combined into the feature pipeline. Opsworks has always adopted a philosophy of being an open platform, and the feature pipeline kind of adopts that philosophy as well, to basically allow different frameworks to be used. Not only the frameworks that exist today, but also future-proofing your infrastructure and the infrastructure of our users and customers. So that if, let's say, in 2 years from now, the next activity comes out or the next Polars comes out, we can plug it in and you can leverage it to compute features, right? You don't have to wait for a specific tool to add support in the DSL. It's just use it and call the API to register what we call in Opsworks register data frame. Data frame are a common concept across all the data processing tools out there. That's essentially what we provide in terms of platform to implement the feature pipeline API. One additional thing that actually is something that it's new in Opsworks that we have released as a preview right now. It's feature monitoring, right? So the goal is that when features leave the feature pipeline, everybody can trust it, right? So if I'm a data scientist building a training pipeline, or if I'm building an inference pipeline, I know that the data coming in the data that's available on the feature store is actually high quality and correct, right? Opsworks has had support for Great Expectation for many releases now, and that's mostly covering bad data. So, for instance, I have nulls in my data, or I have negative values when supposed to be only positive. These new capabilities, feature monitoring, actually looks at more statistical data, statistics properties of the data, and making sure if the data is shifting or drifting, you can basically get an alert, and you either retrain your model or adapt your model essentially. And we have again open Python API to do that. It's the same API for batch and the same API to monitor real-time pipelines. And you can basically have a look at documentation is going to be available soon as well to look at this API. The next step is once the feature has been produced, is actually it's time to actually train a specific model. Training a specific model, again, the underlying concept is the platform needs to be able to support all the different frameworks that the scientists might want to use, right? So everything from deep learning frameworks like PyTorch and so on, but all the way to, let's say, if you're working with tabular data and so on, you might want to look at, I don't know, XGBoost or Scikit-learn or something like this. So for Opsworks and for feature stores, the key concept here is to provide an API to give back Pandas data frame, right? Opsworks supports it. All the feature stores out there, they support the same API. One important aspect I would say that you really want to be careful about is the way you're retrieving data, right? So if you look at feature store out there, and to a large degree, Opsworks back in the days, they are either built on two underlying technologies, right? They're either built on Spark or they are built on a data warehouse, right? Then they ship the data to the clients using a JDBC protocol, essentially, right? The challenges of this architecture is that, for instance, Spark has a really like a long cold start. Like if you want to start a Spark application, it takes a couple of seconds to get up to do anything useful, to even like start retrieving the data. And that has an impact on the user experience, right? So one of the things we see oftentimes when we work with data scientists using Opsworks and using feature stores is that what they want is they want to be able to have the same, let's say, laptop experience that they would have if they were to train on a CSV file, right? Obviously, if you are a large enterprise, or if you're, if you care about data governance and you have working with sensitive data, you can't just have a bunch of CSV file flying around on the laptops of people, because that's a recipe for disaster. So you want to adopt a centralized architecture, but at the same time, you don't want to take away the flexibility in the user experience that people are used to, right? So that's what we actually try to address in the summer with Opsworks 3.3, which essentially allow replacing the Spark Query Engine with a combination of DuckDB and Autoflight, right? The basic idea here is DuckDB has really good performance, especially for point-in-time correct joins. That's a typical work use case that you see when you're dealing with feature data. And Autoflight is a protocol to be able to ship data between client and server in a way so that you don't have to, you don't have to do a bunch of deserialization. You don't have to go from columnar format, which is the typical way the data is stored in a feature store, to row format, which is the DBC, to back into columnar format, which is a data frame in Pandas, right? So with Autoflight, you can do end-to-end without serialization, so on, right? So that's something that, as Jim was mentioning earlier, we have benchmarked. We have worked with KTH and Karolinska Institute to look at typical use cases. As I said, typical use case would be sending data to a Pandas application for training your model. So we have done actually two main experiments. One is, as I said, this one, which is basically sending data itself using DuckDB and Autoflight for Opsworks, and use other technologies for the other vendors. You can see that like performance are extremely well compared to tools out there. Similar thing, oftentimes you don't want to just get a Pandas data frame. Oftentimes you want to, get a materialized version of the trained data set. Maybe you're doing parameter tuning. You want to have a fixed target that you're training on. So in this case, you can potentially say Opsworks offers the API and the other tools as well, to be able to say, okay, collect all these features in a CSV file or a TF records file. And we benchmarked it as well. Again, for Opsworks using the combination of DuckDB and Autoflight. And you can see that again the performance are significantly higher, both because of this implementation of point-in-time join DuckDB, but also because of the Autoflight protocol. So yeah, finally, we're looking at the inference pipeline. So the last part of the MLOps lifecycle. Theoretically, the inference pipeline is responsible for outputting predictions. Whether you are predicting on a single vector or you are predicting on like a 500 vector input, or a million rows or something, doesn't matter. One of the benefits of the FTI pipeline, and you can really see it here in the inference pipeline part, is the unified architecture between batch and train, right? So the feature pipelines and the training pipelines don't really need to know whether or not you're going to be doing real-time inference, or you're going to be doing batch inference, right? So the inference pipeline takes care of that complexity. All the complexity for that is included and limited to the inference pipeline itself. The inference pipeline does essentially two things, right? So and this is really important in terms of real-time use cases. The inference pipeline is responsible for retrieving data from the feature store. In Opsworks, if you're retrieving a small set of data because you are doing real-time inference, we go to the online feature store. If you're retrieving data for like large batches, we go to the offline part. And the other aspect it does, the inference pipeline is responsible for, is actually doing on-demand transformations. right? So there is a class of use cases. I would argue the majority of the use cases for which some of the features data is not going to be, you're not going to be able to pre-compute it, right? It's going to come in using the request data from the request data. What we do in OpsWorks is we actually do that we use something called like Pandas UDFs, right? Pandas UDFs are really powerful because you can run them on top of, Pandas series. And so you can get, if you are in inference pipeline, you are in a pure Python environment, you can basically just retrieve the compute the features on top of the Pandas series. But you can actually apply them if you're doing, for instance, large feature engineering, or you're backfilling a large amount of data. You can take the same feature. You can take the same feature functions as Pandas UDF and give them to Spark. Spark is optimized for that. It's going to push them down to the executors, and it's going to use Arrow to communicate between the executor and the Pandas UDF and make it extremely fast and extremely performant. Again, the feature pipeline, the inference pipeline, again, it combines the data coming from the feature store, combines the data from the request data and the on-demand transformations, and provides it to the model for making predictions, right? And OpsWorks as a platform provides the API to combine these two and to retrieve the data and so on, and all the metadata about which features are needed, from where they are needed, whether they need to be computed on demand or it can be retrieved immediately. It's all managed by OpsWorks, and it's all part of the OpsWorks metadata layer. And ultimately, you can make predictions. We've done a bunch of benchmarks as well for the real-time aspect as well. We'll be looking at retrieving data from the feature store. We've done it for two. Well, we've done it for more than two. You can actually look at the feature store doc/benchmarks URL that you have here. We're going to show you like two examples, one for batch size 1 and the other one for batch size 500. 500 being a good number. That's usually a use case where you're doing, for instance, recommendation systems. That's, you have a large pool of candidates to be able to rank. You want to rank to be able to, recommend to the user. And the larger the candidate pool, then potentially you're gonna get better results in terms of more diversity of candidates to give back to the users. You can see the difference between a couple of different vendors out here, OpsWorks and a couple of different vendors. And again, you can find the code of the benchmarks to be able, if you want to reproduce them, if you want to add your own system, you can find the code in the URL itself. And and some of the other benchmarks that we have done. If you go back and we take a step back and look at the full pictures of what are the the benefits of this new architecture, this new FDI pattern, and we compare it against the data challenges that we had at the beginning. The first one being variety of data sources. The feature pipelines is the one responsible for dealing with all these data sources, all the complexity of changing or dealing with different data is all combined and constrained into the feature pipelines. In OpsWorks, the feature pipeline can be expressed with any framework, and so we're going to solve also the second challenge, which is basically say, okay, I have a bunch of different pipelines running, a bunch of different frameworks. OpsWorks can take care of all of them. Again, we provide an open API to be able to actually, write to the feature store and later on retrieve features. The other challenge is the disconnection between experimentation and training and production. The new setup, the new pipelines actually allow you to, register features for experimentation, and whether or not you're going to train a model, whether or not you're productionizing the model, it's the same pattern, it's the same API. It's one tool to kind of go through all the steps. This is one pattern for them, and it's also one pattern for doing both batch and real time. As I said earlier, the only really component that needs to be aware of whether or not it's retrieving features for a real-time request and for which he has a bunch of SLAs against, or as more like relaxed SLAs because it's a batch job running every night, for instance. It's actually only the inference pipeline, right? Training pipeline and feature pipelines are not going to be responsible for that, and they not need to be aware about the implication of where when the data is going to be needed. Now, if you want to try out this pipeline, if you want to try it out, these patterns, we actually have as OpsWorks available a serverless platform. right? It's a free sandbox that you can register. We launched it over a year ago, and we have reached over 3,500 users right now on the platform. The platform is the same as if you were an Opsworks customer and deploy it in your own VPC on the cloud or on-prem. The same APIs, the same user experience, as the same components for feature store, so feature management, but also model registry and model service. So you can also go and serve your models directly into Opsworks. So the same user experience, same API that you will use if you were an Opsworks customer, enterprise customer. You don't have any infrastructure to manage, so everything is managed by us. It's free, and you can just register, and there is no time limit. We built a community around it. If you go on the serverlessml.org website, you can find a bunch of different examples that you can take inspiration from. All of them follow this FTI pattern, and so you can get a feeling of what the API, what this pattern looks like in practice. And we also have two amazing educators, Paul and Pao. They've been building a lot of tutorials and a lot of the examples for the community. And they're really active in the community and on Opsworks. Now, the serverless platform is great, but it's not meant for enterprises. It's meant for as a sandbox for you to build your examples, or to build your own side project and so on. We don't provide any strict SLA. It's a shared infrastructure for everybody, and you have limited quotas. That we also, one of the things we actually get once we launch is we get a bunch of people asking for, okay, can I get more quotas? Can I actually deploy my own enterprise applications on top of Opsworks, right? So that's why today I'm super excited to announce that we are actually releasing the same user experience of serverless as Opsworks SaaS. So it's the same user experience that you find today in serverless, but targeting enterprises with both enterprise SLAs and managed platform as a fully managed platform. It has the same set of functionalities, both feature store, model registry, and model survey. It's currently being used by a couple of different small set of users, but you can register and you can join the waiting list right now by scanning the QR code. And we open up a bunch of different slots every couple of weeks, and so we're going to reach out to you once new slot becomes available. You get a bunch of quotas in terms of both online, offline, and number of models you can actually serve with, again, enterprise SLAs and support from the Opsworks team. One of the things that really excited that we worked on really hard throughout the summer, we actually made Opsworks available across multiple regions. This was one of the requirements that we worked with a Fortune 500 company, and this is targeting Fortune 500 companies essentially, right? So if you are, for instance, on-prem or also on the cloud, and you want to be able to, be available if one of your region goes down, now you can deploy Opsworks so that the data and metadata gets replicated between different regions, so that if your region goes down, you can still be able to serve your applications and serve your business processes through from essentially the other region. We have, again, this is mostly to help Fortune 500 companies. As I said, we built it with a Fortune 500 company. We're going to run webinars. We're going to run a bunch of different events, going in details about these capabilities and what it means and how to deploy and so on. So you can, feel free to join us. We have a bunch of different events coming up. We're going to talk about it. We're going to be in several US cities over the course of the next couple of weeks. You can find all the events in this QR code. And that's everything for me. I don't know if there are any questions. I think I don't have too much time, but yeah, let's see if we can take them.
Thanks, Fabio. Very exciting, very interesting, and great to see the feature store platforms being pushed forward with features like multi-region, high availability, and serverless. We have a couple of minutes for questions, so I'm going to move over to the Q&A button. Thanks for people who ask questions using the Q&A button, because often people use chat, and that's really great. I'll start with Joe. Joe Schmidt asks, how does Opsworks deal with time series data? Does it help to split the data by time to avoid leaking future data? And what's your answer on that, Fabio?
Yeah, I mean that's a really good answer. Like I think the challenge when you're dealing with the biggest challenge when you're dealing with time series data is making sure that if I go back 1 second, if I go back all the way here, if I'm dealing with time series data, I want to be able to have different transformations. Having different transformations, joining them together and making sure that I'm not leaking information from the futures, right? So there are two aspects, right? When you're dealing with time series data. First of all, is you end up with a bunch of different events. Opsox, when you register a feature, you need to tag what is the primary key, but you also need to tag what is the event time that feature is valid for, right? So let's say someone goes on the website, makes an order, that becomes your event time for that specific feature. And when you do and join things together, then Opsox make sure, and that's one of the pattern that you can see here in the point in time join. Make sure that you can basically you're not leaking data from the future. So you're not joining the transaction done today with the profiles of the user done tomorrow. That's taken care of by Opsox behind the API, so users don't have to kind of deal with that. The other aspect is one of the typical operation you do when you're dealing with time series data. Also, it's logging and obviously looking at what's the event in the past and stuff like this. This is something that we defer to the framework itself that you're using feature engineering. So obviously Pandas and Spark and all the frameworks like this have good support for doing what is the what's the average order of the user in the last 7 days and stuff like this. All this can be done by the frameworks that you're using for doing feature engineering, and then you register that event with Opsox as a set of features essentially.
Great, thanks, Fabio. There are some more questions, but we won't have time to answer them live. I think Chris asked about DuckDB. Just a clarification that DuckDB is not the feature store in Opsox. It's just used as a query engine. Fabio can clarify that, I think, in the Slack channel if you go there. And then there's questions on should you store label columns in a feature store. I think it's a great question. Again, go to the Slack to continue that discussion, and integrations with Opsox, particularly with vector databases. We see that a lot for personalized recommendations. So I'm going to move on. We're going to move on. Thanks, Fabio. So we now have Uber, I'm delighted to announce. So we have Nicholas, who's here, not for the first time. So Nicholas Brett Marcotte, he's a staff software engineer and technical lead manager on Uber's AI feature store team in San Francisco Bay Area. And he specializes in serving data for ML models at high scale. And he previously worked on performance of Siri at Apple. And we also have Parth Chotani, and he's a staff software engineer on Uber's AI feature store team, again in the Bay Area. And he specializes in large-scale distributed systems for ML infrastructure. And he previously has worked at Microsoft Teams, Amazon.com, and AWS Chatbot. Thanks, guys. Looking forward to this. The floor is yours.
Hey, thanks. I was going to introduce myself, but thanks for that great introduction. So I guess we can just hop right in. So first, I'd like to give everyone a brief introduction of what capabilities and features Michelangelo's Palette Feature Store provides. Our feature store serves as the backbone for dealing with data in ML. One of the first steps when you're dealing with data in ML is feature preparation. Palette aids users here by auto-generating batch pipelines and setting up streaming ingestion services. If the necessary features are already available in our common store, Palette can help discover and analyze them. This beats manual selection or brute force iteration over many feature types. And here in the center and at the heart of any feature store is the actual serving of features. Palette provides APIs to consistently serve the same features from both an online database and offline batch systems. Low latency, high availability, and low cost are the name of the game here. Palette also provides automated monitoring systems to notify users as early as possible of any failures or issues with data quality. Bad data is just as detrimental to prediction performance as a bad model. Lastly, depicted here is the Michelangelo transformer, the convenience APIs provided to join and transform features consistently online and offline for a model. So next, I'd like to go over just a brief history of Palette's evolution to help understand how we got to where we are now. Back in 2016, 2017, we launched and made public the industry's first feature store. This had the core components that allowed for storing Uber's ML data in one repository and serving it online and offline. At this time, the focus was on batch features. Next, then, as Uber in its own, as its use of ML continued to scale, Palette needed to go through its own growing pains and meet the strong demand. This meant optimizing for latency and high scale of millions of QPS. At the same time, more support for streaming features was built into the platform. After data could be served at scale, a couple of years ago, the focus shifted back to the data itself, where teams ensuring that they're using the best features and ensuring they remain high quality. We added automatic feature selection and tools to ensure high data quality to address these concerns. And that brings us to today, where we have focused on feature APIs, embeddings, and reliability. Today's talk focuses primarily on the feature APIs and its related metadata, which have helped ensure seamless operation and better modeling of complex systems. So what level of scale are we looking at in Palette? Our online serving systems serve a wide array of use cases across all major Uber products, such as Eats, Rides, Safety, all summing up to over tens of millions of requests per second, and with P99s under the 10 millisecond range. Offline serving is also no small task, with some single training jobs reading up to hundreds of terabytes of data per training run. Along with so many models comes thousands of feature pipelines. With so many touch points, it is key to have a highly available and reliable system with minimal user involvement. Lastly, in the topic of today are metadata changes, which are in the thousands per week. With many moving parts, feature deploys, and code deploys, it is essential to avoid metadata changes negatively affecting production services. As a platform at this scale, any small cracks in the system can have an outsized effect. So what high-level problems can a subpar metadata system cause? First off is unreliability. When bad metadata changes are deployed across the system, it can negatively affect any number of services and products. Second is slow developer velocity. Without clean APIs and tooling, the system can be difficult to operate and debug. And lastly is customer dissatisfaction. So we want to feature store users and our team alike find it a breeze to work with anytime working with data for ML. So now I'll provide a couple of problematic examples to illustrate all these potential gaps. The first is the system misbehavior. So first off, we have an example of the bad config being deployed online. This could be a change such as adding a new feature group incorrectly, or maybe a change which routes requests to an online database cluster which hasn't even been created. If this change gets rolled out, it causes serious effects for downstream services, such as causing bad recommendations in the Uber Eats home feed, or any other product. So if these changes are rolled out quickly and with no auto rollback mechanisms, this could spell disaster. Second, we can have inconsistent metadata in the system. Depicted here on the slide, we have user order features writing to one online database, but the recommender service is trying to read the data from another. Reader and writers of the feature data are not in agreement of where the data is even residing. This can be caused by multiple sources of truth, such as configs living in separate repos. Another cause can be incorrect coordination of metadata rollouts, such as the metadata change being landed, but not yet taking effect in the live system. Without tools to fully understand and strictly control the state of the system, services are unnecessarily exposed to risk. And our last example here is high operational complexity. So in the image here, you'll see a complex web of where services fetch their features. Many use cases across Uber require isolated environments to avoid noisy neighbor effects. We don't want one high spike in QPS from an experiment or relatively unimportant use case, bringing down the most important models. This results in unique setups per isolated environment. Also, many of these cases are such high scale to require multiple database clusters as well as caches. This adds even more complexity to the web. If all these cross dependencies need to be constructed and maintained through manual metadata changes, there are many touch points for failure. So our new API and metadata design are targeted to solve exactly these problems. We've introduced much better validation. We now maintain a strict schema design with added semantic checks to ensure cross-entity consistency. And this helps catch bad configs as early as possible. We have further unified the metadata. Instead of configs living in multiple systems, we've centralized them all under one roof. This simplifies everything and allows for better cross-entity validations. Third, we have made the system easier to operate by being more dynamic and automated. Time to deploy and validate changes has been significantly reduced. And finally, we have added new abstractions to simplify the complex web of configs, providing for better modeling of the problem space. So now I'd like to hand it off to Parth, who's going to dive a bit deeper into each of these solutions.
Awesome. Thank you, Nicholas, for the wonderful journey so far. So as Nicholas was just starting to talk about the solution aspect of how we solve these problems, these are some of the principles that we wanted to keep in mind as we were building the solution out. So first is we wanted to have like APIs for all our first-class entities that we define in the system and we want to clearly identify. And then we wanted a solution which could work well when if we build a UI on top of like our whole metadata system, as well as we support like code-driven interactions for interacting with the metadata. Thirdly, we wanted consistency, making sure like all the metadata pieces live together. We have a clear way where metadata entities can interact with each other. And there's no fragmentation at all in how metadata is structured and where it's placed. And then lastly, we wanted to make sure our solution is such that we can extend it for very future use cases that we haven't even anticipated completely yet. Yeah. So next slide, please. So looking at our Uber experience of how, we built the Palette feature store, and Palette being the first feature store, we have like, tried to scale Palette to millions of QPS. And with that experience that we have across like managing this complex millions of QPS across Uber, we took those insights and we came up with this unique, schema and you can say object model here. Specifically, features is obviously the heart of the ML system here, and feature group. When we say here feature group, it means it's collection. It basically can have collection of features which are correlated under the umbrella of a feature group, right? Now, we introduced a concept which is pretty unique and not heard of anywhere else. It's called online feature serving group. Now, this concept comes from our years of experience of how we manage the infrastructure underneath to support this much scale. So online feature serving group, what we mean here is a collection of all the various storage entities that basically come together when we need to serve a particular inference server, for example. And we'll go into examples of how we have structured this for various use cases. But it's an abstraction that helps us cleanly bring all the storage entities together. And then from an inference server perspective, we don't need to leak any of the storage details to the inference server level. The inference server just knows that, yes, I need to talk to this entity called online feature serving group. And the rest of the details of what storage exactly we need to fetch features from, where do we need to cache these features, all of that is abstracted away. So it's a very clean abstraction. Similarly, is the case for a feature group, where feature group, let's say, is dispersed to various online storage systems for online serving. But we don't want to leak these details completely in a place where the inference server now needs to care about this. So feature group also has a wonderful abstraction and link with the online feature serving group. And that way we bring all of these hardware, storage abstractions very, very underneath in one umbrella. And all of the other entities don't need to care about it anymore, which makes it very easy for us to navigate the system. And for customers, for the Palette basically on calls, and Michelangelo engineers in general to interact with the Palette ecosystem. Yeah. All right, so we can go to next slide. Yeah. So here is an example, basically, of one of the tenets that we were talking about, right? And Nicholas started going into that, which was cross-entity validation. So imagine we have a bad configuration and as Nicholas was mentioning, when the bad configuration lands into a production system, it leads to actually, surfacing either error messages to the user or a poor experience where the recommendations are of not good quality because we had a bad configuration, which leads to bad predictions. So to prevent that whole chain of bad predictions, what we have done is we introduced this feature validation service, which can basically, given a metadata configuration, it can validate across all the entities that we've mentioned in the previous diagram, and it can validate and make sure the whole health of that entity ecosystem is maintained before the configuration is deployed to production. In that way, we catch any metadata problems right at the code review time itself. We don't let it go beyond code reviews. So that's something we introduced here to make sure like no bad configurations can be deployed ever to production from now on. Yes. Yeah. Yes. Next slide, please. The other problem that we had was like our configuration was fragmented in many different systems. To give an example, we had like a cache configuration, which was living in one particular metadata system. There was database related configurations of which feature groups connect with which databases, and all of that abstraction, all of those storage level details that was living in another ecosystem. And then we had streaming features related configuration, which was living in third system. And then we have the metadata repository, which is like the central place where our customers interact with Palette. That was living in another system. And basically, we were in such a mess where all of our configurations were in these different systems. And imagine a new engineer coming to our team, and then like the complexity in which they are interacting right now, and like the confusion in which like they have to navigate to make sense of the metadata, is very complex. So we took that feedback from our new engineers on the team. We took feedback from our customers, and we started rethinking. We were like, this is not the way we want to design a new system. So we wanted to unify all of these different metadata systems in one place. So what we did here was we eliminated all of these different various metadata systems, and instead unified all of that in our metadata repository, backed by a schema that we talked about in the previous diagram, the object model, right? That way, all of our metadata now is in only one place. Customers and Palette on-calls, everybody has only one place to go, one single structure to interact with. There is a solid schema now, and there is only one system which pushes this whole metadata to the online serving as well as offline serving. So which makes life very simple for our customers when they want to track a metadata change, and also for our on-calls when they want to interact with the metadata and want to track and see where the metadata changes are for a given particular change. So we unified everything under one umbrella now. We eliminated everything, all the other configurations, and now life is very simple to interact with as everything lives in one ecosystem now. Yeah. All right, next slide. Yeah. The other major change we did was previously our metadata, the way we were interacting with it and way we were actually trying to push some of the changes to our offline and online serving systems. Anytime a user or a Palette on-call makes a metadata change, we would iterate through literally, and you can imagine in the previous slides, Nicholas was mentioning there are thousands of these metadata changes happening on a regular cadence. And imagine having to iterate through all of them every time even one change is happening, we're iterating through all of them, which is there in the metadata repository, and then trying to push each one of them again back to offline and online serving. And imagine as the metadata, as the number of feature groups grow, the scale at which the push is happening is super slow. And when you make one small mistake in the system, the rollback is also extremely slow now, which makes the whole system extremely slow to interact with, very fragile, and leads to a lot of online serving issues, offline serving issues. and the speed at which we can react to a problem is very, very slow. So which means we hurt the business a lot in this case. So we wanted to redo this whole push system because we felt we had opportunities to enhance the system. So instead of making it a full push system where we go through all changes or all particular metadata at once for any small change, we came up with this incremental update system where whenever a metadata is changed, we look at what particular metadata has changed. We only pick those changes and push them to offline and online serving systems in an incremental manner. That way, the speed at which the push is happening is coming from hours to minutes. And also, we are able to react much faster when there is a problem. We're able to link all the alerting with this incremental changes, and we are able to roll back automatically when there is a problem now. So, and the rollback speed is also super fast because we are only pushing what we have changed. So the rollback also means we can react much faster now. Yeah. All right, next slide. Yeah, so the other part to our pain of the old metadata system was because we had this many configurations living in many different places. That was one part of the problem. And another part of the problem was our online serving system. It was basically linking with the whole metadata as a code. And, you know, generally there's a principle about making sure that your config lives in a different place, your code lives in a different place. In our case, we were mixing up the code and the config, right? Excuse me. So because the code and the config was mixed up completely, every time we had to make a config change, we had to deploy the config as part of the online serving code. And the rigor obviously is much high when you have to deploy a code change, which meant that we always lost 1 to 2 weeks for any small change. And this is frustrating for our on-calls, frustrating for our users, having to wait for any small change to be deployed. You're waiting now 2 weeks and you lose such velocity, which means that you know, you could iterate on things much faster, but now you're losing time just for the deployment sake. So we as we were unifying the whole configuration system, we also wanted to make sure we stick to the principle where no config lives with the code anymore, and we eliminate all the configurations that are living in the same place as where our code lives. So as we were revamping this, we brought all the configurations inside the metadata repository, and now you can see the number of steps is also reduced, and also we no longer need the deployment to happen with the code now, which means configuration changes, they get deployed in order of minutes, and we have eliminated the whole cycle time for waiting weeks to interact and really use Palette. Yeah. So that's how we have automated the whole the onboarding system to Palette, and we also reduced the number of places where configuration is living going forward. Yeah. Right, next. Yeah. So coming back to online feature serving group, I want to go slightly more deeper into that concept because it's a unique thing that we have introduced here. And this diagram depicts the problem that we had before, where we have a recommender service, we have a pricing service. All of these services need to know which particular databases they need to interact with to get the features, right? And on the right side, we have these various feature groups like restaurant ratings, user orders, demand and supply. And all of them also need to interact and say, yes, you know, these feature groups need to be dispersed to database 2, database 3, database 1, database 4, right? And you can just imagine the complexity when you are interacting with, let's say, hundreds of features, and visualize the messy graph you would land into, right? Where and this was exactly where we were. Anytime we had to even change, let's say we had to make a hardware upgrade. Now we want to move from database 2 to database 5. Now we need to know, we have to build this graph ourselves to even visualize, okay, which particular feature group, which particular service is interacting with which database, and which databases we need to update to even migrate, right? So that was the complexity we were dealing with. And any database change, we would be, you know, any database upgrade, we would be looking at months generally to make sure we don't cause any outage anywhere. So that's the mess we were in before. Now with online feature serving group in the next slide. Yeah. So with the abstraction that we have created, it's such simplified system where all the recommender service, pricing service, all the feature groups, they only need to care about which online feature serving group they talk to, right? And which they link to. And that's the bridge between your online services or your feature groups. And that's the abstraction we created. Underneath, if you want to swap out a database, let's say 2 with database 5, there's only one place we need to update now, pretty much. And other places don't need to worry about those aspects, which means it's a clean abstraction and only one place that the on-call needs to care about. And that way, the whole migration of particular database is so simple now and also easy to visualize. As you can see, the graph is very simple to visualize here. Yeah. So the online feature serving group has simplified our interaction with the storage entities, and we have simplified our on-call lives thanks to that. Yeah. Yeah. Next slide, please. Yeah. So with migrating to the new system, we did encounter a lot of challenges. Now, as we know, Palette is at scale running at millions of QPS. Any small metadata mistake is a recipe for an outage, right? So we had to make sure first we do our due diligence comparing the metadata between old and new systems so that we have parity in the metadata, right? And then for which we used a thorough metrics between old and new metadata system. And we also made sure that the data integrity is preserved between the old and new system. That way, there is no mistake whatsoever as we are migrating, right, with this. For our offline ecosystems also, we did something similar where we did thorough testing, we did thorough metadata comparisons to make sure everything lines up as we are moving the offline ecosystem, which where our training and other ecosystems use this metadata to make sure the training happens in the right way, right? We had a solid rollback plan where we had a kill switch, which could flip which system we read the metadata from in matter of like minutes, basically. So any mistake we would want to make sure like we could come back to the old healthy system and quickly, right? To make sure our customer lives were easy as we were migrating, because we changed the underlying structure of the new metadata. It was backed by a new schema. The old metadata did not have any schema. We did automated backfills from old to new metadata. And then our customers, when we were onboarding them to the new system, we had clear onboarding docs. And we made sure that because we had the automated backfills, customers didn't have to worry about creating those new metadata files and new metadata entities. We did everything for them, and they just had to use the new onboarding docs, and that was it to interact with the new metadata system. I'll hand it over to Nicholas to conclude here.
Yeah, thanks, Parth. So to wrap things up, we'd like to reiterate some of the benefits we've seen from improving our APIs and metadata ecosystem. First off is ease of use. So with these new abstractions and more automation, we are no longer hitting a lot of the misconfigurations that used to occur. What might have been multiple code changes before is just a single one. Second is reduced maintenance and operation cost. We've reduced the number of moving parts in the system, making for easier updates. This improves the process for adding new capabilities into our system, as well as performing tasks such as migrating from one online database to another. Next, we have reduced deployment time and customer onboarding times. By clearly separating out code from config changes, now we can have a simpler rollout flow that is independent of the code changes in CI/CD. So changing the metadata backbone of a system such as FeatureStore, which has so many moving parts, was no easy task. And we are happy to now be seeing these benefits of our hard work at the end of this year. So shout out to all the members on the team listed here on the slide who also helped make this happen. And we'll soon be publishing a blog with more details on our journey and hope for all you to tune in. So I think we might have a couple minutes for questions now. Thanks, everyone.
Brilliant. Thanks, Nicholas. Thanks, Parth. A fascinating talk. It's like a look into the future, I think, for many of us here to see, the challenges you have at scale. One of the kind of cliches you get is that every time you 10x the size of your platform, you have to do a rewrite. I don't know if you've heard that cliche before. But you mentioned that there were two main areas here. One was the metadata rewrite, it was fascinating, and then you had the online feature serving rewrite. So if we start with the metadata, what lessons do you think we have for the community in general in terms of the importance of metadata and I guess some of the techniques you worked on, because you presented a bunch of them here.
Yeah, I think, it's about modeling the problem space correctly, having simple flows, auto validation, kind of all the points we talked on in this. Yeah.
And let me be technical now. I mean, you talked about, the way you did the incremental updates to the metadata. Often, I think, and we look at many other feature stores, they tend to use row-oriented databases, so transactional relational databases for metadata, but you seem to have a columnar store behind this and you're pushing incremental changes. Is there a motivation for that?
No, it's not a columnar store. It's just a matter of changing how all the code changes. We do have a centralized database as well as a different repository for distributing it in all the online services. So just making sure that entire pipeline end to end is served in an incremental manner was what brought a lot of the benefits into our system.
So we have a question from Ben online is, how big is the metadata schema now that there's one unified metadata service? Can filling out many metadata fields get burdensome for a user?
I mean, yeah, the schema, in terms of schema, we do have many fields, but we have simplified the number of fields that user needs to interact with. So we divided what users interact with versus what palette on-calls interact with. So we have actually reduced the number of things users need to fill in now. So which makes it less for the user. The burden is less on the user going forward. Plus there is a schema now. So users also have an easier time interacting with the system, given that they know what field means what in the new system. Yeah,
I'm sure that makes for happier users. I have one more question on the online part. So, your online feature serving group, it's backed sometimes by multiple different databases. Is that for multi-tenancy or different performance characteristics of the databases, or is it because teams are organized around that way, or what's the main motivation for that?
Yeah, Parth, do you want to take that one?
Yeah, sure. It's a matter of basically us having to work with the scale at which we work with, right? So Uber scale, given the millions of QPS, it's just hard for us to scale, let's say, and have just one centralized database which can just serve everything. It's also a matter of just sharding and our high tier use cases. We want to make sure that we give them a really good experience with SLAs and all of that, and we have very, very extremely low latencies in terms of milliseconds. So we can't afford to have low tier use cases mixed with high tier use cases and disrupt the customer experience here.
Brilliant. And those numbers, tens of millions of QPS at P99 of under 10 milliseconds is really incredible. Thanks, guys. Brilliant, fascinating as always. We'll move on. So I'm delighted that we have one of the Chinese hyperscalers, the AI hyperscalers. So we have WeChat, we have Yin Shang here. Yin Shang is a software engineer in WeChat's ML platform team, where he maintains the feature compute engine for their in-house feature platform. He holds a master's degree in computer science from CMU, and he previously worked with Google Cloud Vertex AI feature store team. And he's also an active contributor to the Apache Arrow project that we heard about earlier. The floor is yours, Yin.
Thank you, Jim. Let me show my screen. Hey, how does, oh, here. Okay.
Great, we're good. Yeah.
Okay, cool. All right, thank you everybody for attending my session. My name is Jin. I'm a software engineer at Tencent WeChat. And today I'm going to talk about our feature compute engine for real-time recommended systems. So a little bit about myself. I'm currently a software engineer at WeChat's ML platform team. I'm the lead developer of our vectorized feature compute engine. And I'm also an active community contributor of Apache Arrow, because our engine uses Apache Arrow, and we actually contributed a lot of functions back to Apache Arrow after our engine is deployed. And previously, I was a software engineer intern with Google. I worked on the Google Cloud Vertex AI feature store, another feature store, before I joined WeChat. And I got my master's in computer science from Carnegie Mellon University. So some background. So WeChat is the biggest app here in China, and it offers a lot of functionalities. You can think of it as the combination of Facebook and Twitter and TikTok and maybe Amazon and Uber. So basically, we offer a lot of things to our users, and we also use machine learning in a lot of scenarios. So the most prevalent usage of machine learning is for recommender systems. We recommend a lot of stuff to our users, such as advertisements, articles, videos, live streams, feeds, like
Okay, we seem to be having technical difficulties here, folks. So Yin, the speaker's muted. Yeah, as people can see, we do have a connection problem with Yin. We're going to try and connect to him in the background, and we'll see if we can get him back as soon as possible. Yin, you're back. Can you hear me?
Yeah, I can hear you. Okay.
We lost you for about 30 seconds there.
Sorry about that. Yeah, because I'm in China, so maybe the network between China and US is a little bit unstable. Sorry.
The VPN. Okay, I mean, just continue. The floor is yours again, and we'll let you know if there's an issue again. Thanks.
Okay. Thank you. So sorry about that. Okay. Let me here. Yeah. So basically, what I want to say is we use machine learning for a lot of stuff, and the feature engine I'm going to talk about today is used on our recommendation systems. So basically, today's topic is going to be feature engineering for recommendation. And in our scenario, feature engineering is divided into two stages. So the first of which is offline feature generation. So basically, we generate features from logs. I think this is kind of like there's already like an industry standard. So people use Apache Spark for batch jobs and Flink for streaming jobs. This is also what we use for offline feature generation. And the second stage is online feature extraction. So basically, extraction is to transform data in your database into features for the models. And these are OLAP-like operations on small batches. So basically, for us, every request is typically a few hundreds of items fed to the model, and also requires low latency because it's an online request and users are waiting for the request to complete. So typically it requires very, very few milliseconds for requests. For us, the requirement was about 50 milliseconds, but typically the average time for online feature extraction for us is about 10 to 20 milliseconds. And typical examples of feature extraction frameworks are Facebook F3 and OpenMLDB online engine. I think OpenMLDB was here last year, and Facebook publicized their F3 engine like 3 years ago. So what are the operations that we do online? So operations, typically online operations are more expensive than offline operations. So the principle is to do everything offline unless there's a necessary condition that we have to do it online. So here are a few examples of operations that we have to do it online. So the first one is filtering. So basically, when doing things offline, we're doing things with distributed machines. For example, Spark is a distributed cluster, and we typically use a distributed database. And when things are distributed, there are always corruptions because you have to send data across different servers. And the first thing in online extraction is to filter out the corrupted data. So when there's so basically we use a filter operator to eliminate the invalid and abnormal values. And the second one is joining. So in recommendation systems, we use a lot of cross features. Basically, we need to combine user and item features into a new cross feature and feed it to the model. And if we do this join offline, it will be too expensive. And in my opinion, it's basically impossible for large-scale recommendation systems. For example, for us, there's over 1 billion users, and the item space is in the form of millions or even billions. If we have to cross it offline, that means we have to cross it for each user and each item, then the key space will become millions of trillions, which is impossible to store in any distributed KV store. So we have to do this drawing online. And sorting and aggregation are typically performed on user action sequences. And it is actually cheaper to do the sorting and aggregation online for us, because if we do it online, we'll have to do it for each request. And if we do it offline, we'll have to do it for each action, because whenever user has an action, you will have to update the sorted list or the aggregated result. And typically in a recommendation scenario, if we have, so for every request user send us, we'll give back a few hundred items, or like tens of items at least. And then the user may have a lot of actions on this request. For example, user may watch a video, user may tag the video as favorite, user may like a video, user may follow the author, and they may have a lot of actions on each of the items. That means for each request, there will be hundreds of actions. So it's actually cheaper to do the sorting aggregation online, because there are very few requests compared to the actions. And the last one is numerical transformations. Examples are discretization and hashing. And because typically different models have different parameters or different algorithms for doing these numerical transformations, if we do it offline, we'll have to do it for all the models that we have. But if we do it online, because in the online stage, we already know which model we're going to use for this request, we only have to do it for the model we choose. So it actually saves a lot of computation engineering resources if we do it online. And next, there's a few observations on the online extraction workload. So first, each request will contain a single user and multiple items. And for each item, we'll compute the same set of features. And the features will have fixed computation logic once they're deployed online, because because once you start training the model with the certain features you choose, you cannot change the features anymore, because that way there will be data leaks or inconsistencies between training and inference. So you have to fix the computation logic once the model is deployed online. And that basically means the same computation tasks are repeated over and over again during online extraction. So with these observations, it leads to a conclusion that it's actually the online extraction stage is actually the perfect scenario for vectorization and compilation. It's perfect for vectorization because we have to do the computation for each item, and they're the same computations. And compilation is good because we know the logic beforehand, and we're going to repeat it for each request. So we can just compile the logic into some fixed code, a compiled code, and then we just call it during the online extraction stage. And that is what our feature engine uses. Vectorization compilation proved very, very efficient in our feature engine. So next, I'm going to talk about the technical details or implementations of our engine and how we use vectorization and compilation to accelerate our feature computations. So first, as I said, our feature engine is based on Apache Arrow. What is Apache Arrow? Apache Arrow is a standard for in-memory columnar or vector data layout. It's actually, I believe, the most widely used vector format in data analysis world. For example, for ad hoc analysis, there's PyArrow, the official Python package for Arrow, and there's Pandas, and there's Polars, both data frame analysis frameworks, and they both depend on Arrow. And also some famous OLAP engines use Arrow, for example, DuckDB and Meta's Velox engine. And Data Fusion is a query engine provided by the Rust version of Apache Arrow. And also people use Arrow for ML data. For example, Hugging Face dataset uses Arrow for file I/O, and Ray dataset uses Arrow as their internal internal memory format. Sorry. And apart from being a standard, Arrow also comes with a complete toolbox for vector data. So the first thing is it's actually very expressive. So other than the primitive data, so people think of array as like just a flat array. That's a primitive array for Arrow. There's also list array, map array, struct, union, and even extensions if none of the previous ones satisfy your need. And also there's I/O utilities. So basically Arrow provide utilities to convert to and from major file formats such as CSV, JSON, Parquet, ORC, and Avril. And also Arrow provide a zero-copy serialization scheme for IPC, so basically inter-process communications. You don't have to copy, you don't have to serialize anything. You just copy the data to and from processes And also Arrow comes with a lot of compute functions. So basically they are native functions that you can call to operate on Arrow data. And apart from that, Arrow also provides interoperability between languages. Basically, it provides a package for all the major languages listed here, and also I think C#, Swift, and Ruby, and a lot more. So how do we use Apache Arrow to represent features? In our scenario, each feature value is represented as an arrow array or scalar. So for user features, it's quite simple because there's only one user for recommendation. So scalar feature is just a narrow scalar, and sequence features are just primitive arrays. So just a simple array for sequence. And for item, it's a little bit more complicated because there are a lot of items, so we can't use a scalar to represent scalar features. If you want to do vectorization, we have to use a vector, so which is a primitive array in Arrow to represent the scalar features. So for example, here we have this array here to represent item ratings, for example. And suppose we have 5 items, we'll have an array of length 5, and each single value in this array is just the score of the rating for each corresponding item. So the first item will have rating 9, the last one will have rating 7. And you can see here there's a null value. So Arrow arrays natively support null value. In this case, null value just represent the feature is missing for a particular atom. And for sequence features, we use list arrays to represent the feature. For example, here, let's say, for example, movie tags. The first item will have action horror list as its feature. And also for 5 items, it's a list array of length 5, and each of the array elements is a list. And there's also a nuance difference to note between the empty list and the null list. So here, the third item will have a empty list, and the fourth item has a null list. So for the nuance difference comes from, for example, if we want to get the size of the number of tags the user item has in the end, the third one will have 0 as a feature value, and the fourth one will have null. So the third one will have a value, but the fourth one will have no values. And next is, how do we do computation with Apache Arrow arrays? So our framework, our compute engine, provide common operators such as join, sort, or mathematical expressions to users, and user define a feature by combining these operators. So for example, here, if we want to do a cross feature, here is the definition of that feature. So it takes a user sequence and item ID as input. It first does aggregation on the user sequence. For example, we take the sum for each item, and we perhaps want to do a sort on the sequence. And after processing the user sequence, we do a join with the item IDs to get the features for each item. And once we have the feature for each item, we do a hashing to hash it into a value used by the model. So basically, user doesn't have to write any code or doesn't have to write any complex logic in order to define a feature. It's just the user just has to write down a couple of combinations of operators, and that's it. That's the feature definition. And so how do we do simmed vectorization on Arrow arrays? There are 4 major ways we do it. So the first one is with LLVM JIT engine. So the LLVM JIT engine is basically we compile our logic, we compile the operators into LLVM IR, and the LLVM JIT engine will execute these IRs. And the second one is Arrow native compute functions. So Apache Arrow officially supports a lot of compute functions to operate with Arrow data. And sometimes our operator just call these compute functions to operate on the data. And the third one is compiler auto-vectorization. So if for very simple operations, if it meets certain standards, the compiler will just automatically vectorize, will automatically generate simmed instructions for these operations. And the last one is handwritten simmed intrinsics. So in certain scenarios, the compiler is not smart enough. We'll have to call manually the simmed functions in order to generate simmed instructions. So let me go over these 4 approaches one by one. So the first one is LLVM. we do this with Gandiva expression compiler. So Gandiva expression compiler is a sub-project of Arrow. So it's originally developed by Dremio, and it was donated to Arrow, I think, in 2018, and it's currently maintained by the Arrow team. I'm actually one of the maintainers myself. Gandiva provides arithmetic functions pre-compiled to LVM-IR. So basically, you can see here, you can write your original function in C or C++ or Rust, or even you can just hard code it in LVM-IR, and the compiler will just compile it into LVM-IR. IR here means intermediate representation. So it's like a middle level representation between user code and assembly code. So it's like an intermediate one. And Gandiva would combine these functions into expressions at the IR level. So basically, once you have the IR, Gandiva will combine these functions into a module, and then it will leverage LVM for various optimizations. So LVM provide a lot of optimization passes. And for example, here we use loop vectorization paths for vectorization. And there's also function inlining, instruction combination, and a lot of other stuff. And we use Gandiva expression for projection and filtering. So basically, we deal with mathematical expressions with Gandiva. So here's an example. For example, a simple feature is defined as A plus B times C. And here is the Gandiva expression in the IR form. So you can see here at the very beginning of the vector body, we do a lot of bit cast from a double pointer into 2 times double pointer. So double pointer is basically the input. The input array is a double pointer. It's just a pointer. It's the same as arrays. And here it will be casted into a 2 times double array, which means the elements of the array becomes 2 times double, which is the vector form in LVM-IR. Since it is compiled on my Mac M1 machine, which comes with ARM v8 Neon instruction set, where the maximum bit width is 128 bits. So that's exactly 2 double, because each double is 64 and 2 double is 128. And you can see here the addition, A plus B, and the multiplication times C here are operated on the 2 times double, so on the vector rather than on the double scalars. So this is how LVM-IR represents vector operations. And here's how we're able to do this with Gandiva. And well, Gandiva is actually very, very fast. It's I think one of the fastest possible ways to do compiled expressions, but it's kind of hard to develop and maintain because we have to first compile our code into LVM-IR, and then we have to operate on the IR level to combine them into expressions. And it's actually also very hard to debug because we're essentially running a virtual machine, and GDB doesn't really give us a lot of helpful information when we want to debug our code. So that's why we use Gandiva only for simple operations such as math expressions. And Arrow also comes with these official compute functions that are natively written in C++. And these functions are actually much easier to write, and then therefore they support much complex operations. So they're dynamically dispatched at runtime. So when you call a function, it will go through a function dispatcher first, and then it will match a C++ kernel depending on our input type and input size, and then it just calls the kernel for a data. You just call the kernel on your data, and then you get the output. It's very easy. And Arrow provides a vectorized kernel for many functions. And because it's easier to write, it's just native C++ code. It supports various complex operations. For example, sorts and aggregation are all supported. And another benefit of Arrow Compute is all functions are exported to Python. So it's much easier to experiment with compared to just C++. So for example, here, I have a bunch of examples to show you the benefits of, show you the power of compute functions. So here, the code is in Python just for demonstration purposes because Python is easier to experiment with, but the actual code we use is actually in C++. So here, for example, sorting, if we have an array here, and we just call the compute sort indices function, it will return the values sorted represented by their indices. And we call take on these indices will get a sorted. So take is basically materializing the array, and we'll get the sorted array. And here is the aggregation sum. So if we call sum on the array, we'll just get back the sum of the whole array. And on the right-hand side, this is an example of joining. So basically, we use this indexing function. So we call indexing, we want to find the index of requested items in user history ID. So here, this 999, 777, 555 are all item IDs. And we want to find here, these are the candidate items. And we want to find their index in the user history. And once we have the index with the indexing function, we just call take again. We'll get the respective watch time of each candidate item. So here in the end, we have 50 for the third one, which is 777. And you can see here for user, it's 50 for 777, and 30 for 999. Here we have 30 for 999. So this is how we do joins. And well, since we started using Arrow, we noticed that even though the compute functions are very powerful, it's still like a lot of feature operations. So we actually write those feature operations by ourselves and contribute these functions back to Arrow. So for example, cumulative functions, rolling functions are basically rolling statistics over a fixed length sliding window. And a join as list is basically if we have a couple of features, we want to combine them into a list feature, we use a join as list to combine them. And pairwise difference is to compute the difference between two consecutive elements. So we use this for computing the difference between user action timestamps. So like how often user perform actions on our items. And integer round functions are basically rounding functions into powers of 10 or powers of hundreds. This is used for discretization. And also Arrow supports temporal types such as timestamps and durations, and it didn't support arithmetic operations on them, and we added these support. And on the right hand side, it's actually my GitHub handle, and you can see here I was actually among top 20 contributors in the past year for Apache Arrow. And the third approach we use is with compiler auto vectorization. So because Arrow arrays are always stored in contiguous memory, for some lightweight operations, it's actually too heavy to use Gandiva or Arrow Compute. So we just rely on compilers to automatically vectorize these operations. For GCC, we just pass in the tree vectorize optimization option. And for Clang, it's enabled by default. So for example, when we are dealing with multiple arrays, we'll have to do a bitwise AND on their null bitmap because, as I said, Arrow natively support null values. So it uses a bitmap to store their validity status. And sometimes we use bitwise AND. We just do a simple code like this. And compilers are smart enough to compile it into these vectorized operations, such as like vmove, vinsert, and vpend are just the vectorized form of move and AND. And this insert is just to pad the memory. And for simple operations, we can just rely on the compiler, but for complex operations, they are not smart enough. So sometimes we have to manually call the SIMD functions provided by Intel and AMD to convert them into SIMD instructions. So for example, here, our hashing functions, we use a very complex hashing algorithm to hash our values, hash our feature values into tensors. And the compiler doesn't automatically compile them into SIMD instructions. So we have to, so on the left side here, you can see this is the code we used to have, which is to shift a 64-bit value to the right by some bits. And this code doesn't compile to SIMD instructions. So we have to call these, see MM256 shift right, and here's the shift left, and here's OR. So they are basically the SIMD version of C++ operations we can call. And these are the AVX2 instruction sets. So with all four approaches, we perform very efficiently. The engine perform very efficiently on vectorized data. However, not every request come with a large batch size. So not every request come with a vectorized data. So in some scenarios, there are only a few candidate items or even one candidate item. For example, sometimes we do online training with just one sample, and we have to get the features for that one item. And also sometimes there's push notifications. So we basically use an algorithm to decide whether we want to push a certain item to a user. So there's only one candidate item. We just need to decide whether we want it or not. And in these scenarios, there's only one item. So it's not necessarily, it's technically not a vector. If you use a vector of length 1, you can still use a vector of size 1 to store it. But the vectorized operators will perform very badly if the batch size is very small. So there are 3 overheads. So first one's the array overhead. Apache Arrow arrays need to store array metadata. For example, the type of the array, the length of the array, and the bitmap. And also Arrow arrays always aligned at 64 bytes because it's better for vectorization if you are aligned at a certain 64 128 bytes. But if you only have one data, which is like, for example, int, it's only 4 bytes. So we're basically storing 16 more data than I need. And there's also a vectorization overhead. For example, if you call a SIMD instruction, it will perform the instruction on whole 128-bit or 256-bit data. But if you only have a 32-bit integer, that will be extra cost on computation. And also there's a compute function overhead because compute functions are, there's a dispatcher. So you have to go through a dispatcher on every function call. And this overhead is actually very small, but if you only have one data, it can't be amortized over the vectorized data. So the overhead will become significant if you have only small batch size. So how do we solve the performance issue for small batch size? The answer is native operators. So basically for all operators we provide to users, we also provide a native implementation, native meaning non-vectorized. And in this native engine, every atom feature is stored separately as a single value. And we dynamically dispatch to native and vectorize when the feature request comes. So basically, in our benchmark, the threshold is 8. So if there are fewer than 8 items, we use a native engine. And if there's larger than or equal to 8 items, we use a vectorized engine. And another problem is how do we guarantee the consistency or the equality between these two engines? Well, we have a full test coverage. We have unit tests on the operator level, and then we have end-to-end tests on the engine level to guarantee the equality between these two engines. And we also have a daily pipeline to examine diffs from feature logs. So basically every day we have certain requests that go through both engines. So we send this request to both the native engine and the vectorized engine, and we log the result, and we have a daily pipeline to examine if there are any diffs. So with these two approaches, we can guarantee that it's 100% equal. And another performance optimization we use is operator fusion. So basically, there's an overhead for each operator call. There's virtual dispatch. There's we have to validate the input and copy it into the function, and we have to allocate memory for the output. And these calls, these overheads can be saved with operator fusion. So basically, most operators can be fused with projection and filtering. Normally, these operations, for example, if we do a projector with a sort with a filter, normally they will have to go through 3 different function calls. But with operator fusion, they can be combined into one operation, into one operator invocation, and these overheads can be saved. So the last part is the performance benchmarks. So here we can see a difference between the vectorized approach and the native approach. You can see as the number of items increases, here the black line is native approach. You can see it's a very sharp linear. Well, it's linear because here the x-axis is logarithmic, is exponential, sorry. So you can see an exponential curve, but the actual curve is linear. And you can see the blue curve, which is the vectorized one, grows much slower than the black one. And the threshold, as I said, is 8. When item num is less than 8, native is better. When it's larger than 8, vectorized is much better. And at 64, vectorized is 6 times faster, and 128, vectorized 10 times faster. And that's because the overhead is amortized for a larger batch. And also actual deployment statistics, once we deploy it online, we see a 50% down in CPU usage on deployment. We can see this right line here is the CPU usage. We can see it dropped from 40% to 20%. So this 50% drop actually saved us millions of CPU cores over the last year. Okay, this is all that I have to present. Are there any questions?
Fantastic, Ian. This is a great set of feature engineering tips for high performance online feature computation. We're out of time, unfortunately. We had our little networking disruption there, and we're going to keep schedule. We're going to keep schedule today. We're supposed to have a 2-minute break, so we're going to start again in 2 minutes' time. You can ask Ian questions on the Slack channel. I have a couple of questions I'd like to ask. I'll pop over there and ask them. Ian, if you could join the Slack channel, that would be great, and we can take them in there. So I'm going to take other people take a quick break. We'll be back in 2 minutes. All right, that was a quick break. We'll get cracking again. So I'm delighted to have Alexander Hristov here from Wayfair. Alexander is a staff ML scientist on Wayfair's marketing science team. Previously, he led development of the Mercury feature platform, as well as several initiatives improving marketing personalization, which is a really hot topic and area where people are applying feature stores at scale. Alexander, great to have you.
Thank you. Let me just see if I can share my screen here.
Yeah, it's gone well so far. Let's not jinx it.
You able to see it?
Yes, we're alive. Thank you.
Great. All right. Thank you very much. So yeah, I'm excited to talk to you today about this Mercury project, which is one of a few feature processing tools we have at Wayfair. It was built with a specific set of use cases in mind by, a number of folks pitched in, but it was kind of on average about a 2 to 3 person kind of project that found a lot of success. It does some unusual things that I want to tell you about today. So the core idea behind Mercury is it's a very opinionated feature processing platform, specifically designed around lowering the effort to define features, similar features, and to lower the compute resources necessary to calculate them. In the long run, the goal of this project is to improve ML performance because small teams can effectively manage more ML signals and therefore have their models have access to more features to learn from. This is achieved because at its core, Mercury assumes you aren't writing a single feature at a time. Rather, what you're doing is writing, building, and consuming features as a group together. Features can be as few as, say, 6, or they can be significantly more, over 1,000. So maybe it's helpful to illustrate this with an example. Let's say you're trying to figure out how popular a product is going to be with customers. If you're working in such a problem space, it's not uncommon to have similar features like the 2 that I'm showing you here. You can count the number of times the product has been ordered on, let's say, different browser experiences and over different time windows. And Mercury treats this not as just some accident, rather it's a core design concept for us. Mercury kind of nudges you to define and build these features together. And I'll describe this how later. But before I do that, what I actually want to discuss is a general framework for trade-offs in machine learning systems that'll help you both understand the decisions we made with Mercury, and I think it'll be hopefully applicable to some of the ML applications you may work with. So at its core, this is a conversation around trade-offs. So if you take any production enterprise ML system, you can collect its characteristics into like 3 main groups here. In generally, we face trade-offs between these 3 axes. So the first of these is predictive performance at some business critical task. Many widely used statistical metrics for this, F1, NDCG, but also many business metrics can also be thought of as falling under this category. Then you have resource efficiency, that's the number of CPUs, GPUs, cloud costs, or maybe it's hitting your latency budget. And lastly, there's the human effort needed to maintain and evolve the system. You can measure that in things like headcount, hours spent, velocity, things like that. So a core theme of this talk is that we should be deliberate about the path we want to take through this 3-dimensional space. So in that vein, I'd like you to think about the following example. Here, I'm showing you 2 models. One's in red, one's in purple. The red one's more predictive, but it's also more computationally expensive. It's more operationally complex to maintain. So which one of these would you deploy? Which one of, when faced with this trade-off the last time you had this at your company, which one did you favor? So in general, there's no single answer to this question. It depends on all kinds of things. It depends on, can your team handle supporting the more complex system? Do you need something simpler? Can you move your resource budget, or is it fixed? Maybe you don't have a way to get more VRAM, or you can't move your latency budget. And I think another question is, how valuable is this business problem to your company? What I want to emphasize is that a big driver in all of this is opportunity cost. What else could a team be working on? Here, it's helpful to introduce this framework of like tall and wide teams. Tall teams kind of tend to iterate in the same problem space over time and incrementally improve a core function. Wide teams tend to kind of build something good enough and then move on to a net new problem that maybe hasn't been covered by ML before. And, it's not always clear that the needs of those 2 team types are going to be exactly the same. What I want to emphasize here is that company context can determine where we prefer our ML systems to be in this 3-dimensional space. It's not often about making a single model maximally predictive, rather than it is about optimizing the portfolio of ML systems a team can effectively support, whether that's a few or many. Now, within this concept of trade-offs, I think it's important that we talk about the flexibility of our feature platform. So specifically, I want to talk about how much flexibility users should have in defining the features that they use. Should they be able to build anything in any way? Or should there be strict guidelines for how features are produced and consumed? At first, it's very tempting to think everything should be permitted. How can we know ahead of time what some ML practitioner might need to do to deliver business value? But at the same time, if everything is permitted, it's harder to provide operational guarantees at platform level for the features and the ML systems. A more restrictive approach is often easier to maintain and better out of the box. So both of these approaches have merits, but I personally strongly suspect that on average, like across our industry, we probably overvalue flexibility a little bit because it's easier to kind of envision this hypothetical best case performance we can get through flexibility, but we have a harder time thinking about the like longer term maintenance and overhead and opportunity cost that we get from increased flexibility. So the reason I think flexibility comes at a high cost is that every ML practitioner is always short on time. There are too many experiments to run, there's too many features to write, there's too many projects you could be working on, and you don't ever get to put into practice all of the flexibility you might be given to you. So another way to say this is that teams have bounded time. They're not always trying to perfect a single model. They're looking to maximize the total value of a portfolio of projects. And we can think of this in terms of a team having like a carrying capacity, a total amount of things that they can support, rather than just focusing on the velocity to ship one thing. So down at the bottom, I want to show you the approach we've taken, which is to first make features more efficient and maintainable to produce, get a lot of them. And then over time, as you have access to more and more signals, models can become more predictive out of the box. So the way Mercury makes features more maintainable is to reuse the recipe and pipeline for similar features. And the key idea here is that related features can be thought of as, kind of filling in the blanks on a common pattern. I've shown 2 examples of this in these gray boxes. You can quickly see from the one in the top that, yeah, you can be filtering by different browsers or aggregating over different time windows. And through those combinations, you quickly get a lot of leverage. It's easy to imagine being able to get dozens more from the pattern I've shown you. And for completeness, there's another example below that. So in preparing this talk, and as you've kind of heard from others, you've heard multiple people use the term feature group. I think it's a widely appealing phrase, but is one that's a little bit overloaded. So I want to follow suit here and be very specific about my definition that I'm using here. When Mercury talks about a feature group, we're thinking about 2 core things. One is you're sharing the same template pattern here. The second is that you're sharing the same source event. So there's that allows you to basically build the features together all at once effectively. Now, within that, I also want to take a bigger picture view and kind of introduce this notion that like Mercury has a full hierarchy. At the bottom, you have individually programmatically generated features that get all built together through this next level in the hierarchy, which is feature groups. And then we have an additional notion, which is something we call a feature family, which is this idea that if you're counting, let's say, the add to carts across different geographies, well, you probably want the orders too, and maybe the times a product has been favorited. So that higher level in the hierarchy is a tool that helps with discovery and also helps with users basically being able to understand what features they want to use. So with that, I want to briefly summarize where this approach has taken us. The emphasis is on helping users define and maintain thousands of features and to do scoring for millions of entities every day. This enables us to run hundreds of models on Mercury in production. The real focus, however, is kind of these user experience improvements. So some numbers, rough numbers to share. A few systems migrated over from previous pipelines onto Mercury. When they did so, they observed, let's say, a few percent improvement in their target predictive metrics. For net new development, when teams started working on completely new projects, they reported sometimes reductions of 2 to 5 times in terms of time it takes to develop a new model. And one team reported saving up to 4 hours a week on the pipelines that they got to deprecate as a result of switching over to a centralized product. So with that kind of out of the way, I want to talk about focus in further detail on some of the key architectural enablers behind Mercury. I won't go into everything, but rather I want to focus on the kind of key enablers of this mission to define and produce many features efficiently. I'll focus on what I call the paved path. It's shown here with these kind of purple boxes. So raw events get pre-aggregated. From those pre-aggregations, features are built as grouped and consumed across scoring, most often through Spark ML libraries. And there are going to be 4 key lessons I want to share from that paved path, which I want to highlight because I think they're generally applicable, regardless of whether your feature processing system is going to look like Mercury or potentially look quite different. So they're about the importance of pre-aggregation, about the ability to package features together as vectors, an emphasis on reproducibility, and different ways we can drive feature reuse. So first of all, I want to talk about pre-processing. So you probably know that if you want to compute an average over some set of events or some set of facts in your data store, you don't need every single event, every single row of some table. You just need kind of sums and totals. So you can pre-aggregate data and kind of boil it down into just what needs to get used later. So here's a made-up example. We have some made-up products and the price of those products in various orders and across various geographies. So rather than computing averages by directly scanning through all of this, what we do is store sums and totals. And when it comes time to computing features from this, we have a lot less work to do. Similarly, the process is also helpful if you want to enrich data. Say if you want to, rather than grouping by geo, you want to group by, let's say, style, and maybe to count the style of products that a customer is buying. Well, if the style of the product isn't in the event itself, you can just join ahead of time to save yourself having to do it later, but still create essentially the same core data structure. And we found significant savings by having systems pushing compute earlier into the pre-processing to make future downstream compute run faster. So despite being very opinionated about this data format, the approach actually supports many different types of features, averages, extremas, sums, counts, so forth, right? Probably more that I haven't listed here. It doesn't support everything. You can't easily count distinct values, and there are some complex sequence processing things that obviously are a little bit harder to do, but nonetheless, like some of those calculations can be approximated pretty well through these approaches. And furthermore, you can choose to aggregate over different types of windows. I know lots of feature processing systems do this, but here I'll just say we kind of have two things are enough for us. We have, for features that have up to a 1-year look back window, we use daily binning or things smaller than that. And for things beyond that, we can combine both daily and monthly aggregations. Okay, so now given those aggregates I've shown you, I want to talk about how Mercury builds features and from those aggregates in groups and packages them as a vector. So busy slide, I'll walk you through it. But the goal is to have a quick picture of what this looks like. And we're going to make a group of features that all at once, for both average price and total orders per a supplier. And we get that across various geographies and across various time windows. So at the very top on the left, the user provides a list of entities for which they want to calculate the features. So this is, in this case, suppliers, dates. From that user provided list, Mercury actually builds an entity mapping layer. So it maps suppliers to products because the data that we need to build this feature is aggregated at the product level. And then the mapping data is joined to pre-aggregated data. That's this top table on the right. Along the way, you group on things or aggregate on things like the time window, the geography, the supplier. And then you do the aggregation that allows you to compute values. Now, once all of that's done, all of your features each feature is basically a different row for, let's say, a fixed supplier here. What we do is we pivot back into a single vector for the entity. And this actually deploys all the features and produces them all at once while actually needing to do only a single scan of the large underlying data. Okay, so these large vectors may seem like they're kind of bulky and difficult to use, but we've actually found they can be used quite flexibly and easily, particularly in Spark ML. So I want to just give an example of this. So here we have two of these feature groups. We can, one of them has the numbers you can see in red, one has them in blue. What you can do is concatenate them together. So this builds you a single vector. And then you can have multiple models who are packaged together with what is in Spark ML, something called a vector slicer. This allows them to essentially pick out from this vector only the features that a model needs. And this packaging actually makes it possible for lots of models to share the same vectors while not having to actually use all of those features. And it simplifies the operational process so that you can run, many, many models that are all sharing the same data set. So the next lesson of these 4, this is now number 3, that I want to share is about how the choice of upstream data sources influences the requirements of feature processing. To explain this point, I have to introduce a tiny bit of terminology. And the reason is I think feature store can sometimes be a little overloaded. I think it helps to break down the functionality into 4 key parts. So there's a library, that's the collection of recipes by which you make features. That could be SQL, could be a YAML file, could be a collection of Python functions. Then you have an engine, which is how those recipes get materialized into values. That could be streaming, could be batch, could be some combination thereof. You have archival, which is the ability to store outputs of feature computation for further use. And of course, you can also cache for low latency retrieval. Sometimes when you're building features from data sources where you can't reproduce past state, In those cases, the information might be getting overwritten, or you don't know when it got written into the source at all. In these cases, you can turn to feature archival to give you a measure of online-offline consistency. But this still has some drawbacks, right? You might need months of historical data to train a model, particularly if the events you're trying to study or trying to model are rare events. You might need to look back for a very long time those. Also, when you cold start and build a new feature, you have some period where you need to accumulate new features for training. Now, on the other hand, if the data source you started with has an easily reproducible historical state, so like maybe it's an append-only log that replicates the data that was being streamed in real time, and all of the timestamps are properly, provided, then you can design a feature engine and feature library around that fact, and produce and reproduce features quite reliably in practice. Excuse me. And this actually diminishes the need for feature value archival and helps you save quite a bit of money on storage costs in our case. So, so the fourth lesson I want to talk about is different mechanisms that we found from this architecture on driving feature reuse. So we spend a lot of human and machine time writing, calculating features. We should want to make sure that those features get used. Earlier, I mentioned how feature vectors can be sliced and consumed by multiple models, particularly in Spark ML. I've also talked about how Mercury reuses pipelines to build features together. Now I want to talk about a different kind of reuse, which is the reuse of a feature definition across multiple entities when building features. Let's start with another example. So on the left, you have data that is pre-aggregated at this product date level. In a previous example, I showed you can group these products by supplier and use that to compute feature values. However, it turns out if you hadn't grouped on supplier and instead you were grouping on product class, well, all of the subsequent recipes downstream, all of the subsequent steps in the recipe downstream would have been exactly the same. Similarly, if you had kept the data at product level, you could also do all of the subsequent, after grouping at product level, all of the downstream steps for calculating the features would be exactly the same. So this is a remarkably powerful idea. It means you could write 100 features for one entity. So let's say you could write features at the option combination level. That would be something like, how often has this particular red king-sized bed frame been purchased? And then you could actually reuse that feature at the next level in the hierarchy, which is how often has this bed been purchased for all different colors and all different sizes. You might even be able to reuse the feature at category level. So like how many beds have been purchased, right? These values that you're computing are different, but the single recipe can actually be reused. And this pattern can actually be reused in many places because there are many places where you have hierarchies of entities like the ones I'm showing you here, whether that's in ad campaign management, whether that's user accounts belonging to different businesses, so forth. So that's an often kind of unusual form of reuse. I think there are other drivers of reuse I want to kind of highlight quickly. So first, I think it's important, or I think it's helpful that we have leverage from being able to produce many features with fewer lines of code. You can read all the feature definitions your model uses, and this actually reduces the need for some forms of metadata management. Second, I want to highlight that discovering features by metadata alone, such as who uses them, who owns them, when were they created, is often secondary to just being able to know whether the feature will improve the model performance for the problem that you're working on. And for this reason, just as the earlier speakers from Uber alluded, we've invested in automated and scalable feature selection methods so that you can traverse these large feature libraries to find features that are helpful to your problem, not just on metadata alone. And last, I want to point out that in my experience, the single most effective way to actually get ML teams to reuse each other's features is about having clear expectations around what happens in the event of changes to upstream data, who's going to be making changes to the definitions, who's going to be having to retrain and so forth. And combined, I just want to share all of these because I think all of these are incremental parts in scaling reuse and therefore scaling the number of features that each team can effectively use because they don't have to keep their own copies. So with that, I just want to provide a little bit of intuition for why Mercury has been effective in making models performant. Making lots of features like this doesn't seem at first like it's guaranteed to work well. But I want to put the results in the context of some previous theoretical results about something called random kitchen sinks. This isn't a proof, but it's a helpful vehicle to build intuition. So to do this, the intuition depends on the following analogy. Think of your enterprise data lake as a kind of neural network, right? Let's think, so on the left, we have a neural network. It takes inputs on the left, I1, I2. Through linear algebra and some nonlinear functions, you get the numbers in the middle, H1 to H5. Those then get consumed to build the output O1. A common way that we build intuition about the functioning of this network is to think about the middle layer, H1 to H5, as kind of building features from the raw data, right? And because the model trains over time and learns better weights, you can think of the network actually iterates to build better features. Okay, so then now on the left, let's look at the data ecosystem. A very simplified picture is you have raw data, perhaps in the form of some event logs. You write features to transform the raw data via some functions, and then you combine those into a model. Over time, your data engineers, ML engineers, data scientists tune the feature definitions to make the features better. Now, that brings me to this paper by Ali Rahimi and Ben Recht. In the interest of time, I'm going to try to distill the paper through these two pictures. On the left, if you visualize what's happening in the training process of a neural network, you have these hidden layer, these values H1 to H5. They depend on I1 and I2. And in the plot, what we're basically showing through these colored marks is how much each one depends on I1 and I2. Now, let's say there's a best case performance where these 5 hidden units, these things, their dependence on I1 and I2 is represented by the black stars. So the goal of training the network is so that over time, these colored marks move around to be on top of those black stars. And that's what happens when you train a conventional neural network. Now, what this paper shows you is that instead of doing that on the left, what you can do is on the right. Rather than trying to tune the featurization process, you just initialize many, many features at random and apply a simple learning procedure to figure out how much to weight them. In fact, by using an L1 penalty, you can use sparsity to basically throw some of them away. And what this paper does is it shows uses functional analysis to basically prove the models you get are very similar with high probability, but there's this further benefit that they train up to 10 times faster. So to further distill this down, the key idea here is you want to replace a slow end-to-end learning process with a fast, high-dimensional kickstart, and then you want to quickly learn how to do weighting. So if we translate that to the enterprise data warehouse, what I'm saying is you can take 2 approaches, right? You can iterate to build 5 perfect features, or you can make many features and learn to weight them well. Essentially, what I want to suggest is that programmatic feature generation gives you this on the right of this inset. It's a not so random kitchen sink. It's a large basis of features in a complex functional space that's hopefully very close to the best case you would have if you tuned your features by hand. And in practice, because we have finite time to train models, the models you get out of this are actually quite performant. Now, I want to be clear, I'm not saying feature quality doesn't matter. Features should all be of a high standard. But what my message is that you want to maximize the value delivered by a portfolio of all features and over all of the models that consume them. It's hard to know in advance which ones are important, so it helps to have a large library of high quality features to draw on. So lastly, I just want to situate this in what I think is a growing trend. Over the last decade, there's been a considerable investment in so-called AutoML frameworks that take a given data set, optimize training over that data by handling things like hyperparameter search and missing data imputation. The methods are very powerful. They've saved a lot of human effort. They've become the basis of offerings at many cloud providers. But these methods only work with the data that's been given to them. And where I think there are still opportunities is about extracting more data from the warehouse, from what's available, and making it easily consumable. The area is much less mature, but I'm happy to share some of our first forays into this problem space. And I'm excited about what future changes are going to look like. So thanks. And with that, happy to take any questions.
Thanks a million, Alexander. That was a tour de force, I think. You know, we went from great templates on how to create features in marketing domain, you know, to counts and frequencies, and really intuitive, I think, for people. And then feature reuse, you went into great detail about some of the great things you've done there. And then you finish off with this vision. I mean, it's a great vision for data-centric AI, really. You know, the data lake as a function approximator and neural network. What would the loss function be for these features? And, you know, we have gradient descent to update the weights. So what would be that? I mean, where does domain knowledge come into feature engineering? Is domain knowledge part of our future, or what are your takes on all of these kind of questions ringing around in my head at the moment?
Yeah, I want to be clear. This is a vehicle for building intuition, not a formal proof. But I think if you kind of think about this, maybe to continue the analogy with this kitchen sinks paper, one of the things that's important is that your randomization over a feature space, at least in that paper, it should be saturating. You should kind of cover everything. I think the place that domain knowledge, you can very easily see it still applying, is the notion that you have to have coverage over relevant fields, right? So it's much more about getting access to data. So maybe you have information about product reviews. Maybe you don't have information about incidents. How often do things break and need to be returned? So the domain knowledge is going and saying, okay, that's the missing source. We have to think about how do we pull that into our system and get better coverage of the basis. And I think there's less of like aggregate over 7 days versus aggregate over 10 days kind of questions, which are very incremental. I think the other thing is there's still a lot of domain knowledge in label engineering and a lot of data-centric work there. Obviously, you know, don't have time to go into all of that, but I think there are still places where it's just really about shifting prioritization and where we invest heavily and what are the things that we think are maybe like lower return, because as I've alluded to multiple times, we're all very strapped for time, and so we have to prioritize.
I definitely agree that automation is coming. Arno Estrev has a question, a more prosaic question. What does Mercury look like in practice? Is it a domain-specific language, templates, YAML files?
So it's a combination of SQL and YAML files. There are, and I kind of showed this. It's built on a combination of BigQuery and Spark. For the core processing.
Cool. That's brilliant. Thanks a million. If you have more questions for Alexander, please hit them in, take them in the Slack. We're going to move on again. And I'm really delighted to have Georgia O'Callaghan here from Gartner. Georgia is a Gartner analyst on the Analytics and AI for Technical Professionals team. And she covers feature stores, data literacy, analytics, business intelligence tooling, analytics governance. And previously, she had been a cognitive neuroscientist specializing in the analysis of fMRI scans of the brain to understand development. And most recently, she completed a postdoctoral research fellowship at the NIH in the US, studying neural correlates of depression in adolescents. Fascinating stuff. And I think we're also both graduates of Trinity College Dublin, which is great to know too. Over to you, Georgia.
Great, thank you so much for the introduction. I'm really, really thrilled to be here. I'm going to try and share my screen so you can see. I haven't used.
We're not there yet. Right. Now we're going. Yeah, we're great.
How are we doing?
Yes, perfect.
Always have to go between so many different modalities. Great. Well, thank you so much. Really interesting talks so far. That's going to be a little bit more higher level because I have an interesting perspective, or at least I get to speak to lots of different organizations who are at various stages of trying to build this out themselves, or wondering, you know, what products in this space could potentially help them. And I know this isn't an interactive session, but what I want to start with is a question. Just, you know, if you can think to yourselves, how good do you think organizations are really at getting their machine learning models into production. So I'm talking about a reliable pathway. They've got a great success rate. They're very confident in their process. And in our research, we've actually found that it's just 10% of organizations can get at least 3/4 of their model into production. So that means that 90% of organizations are still struggling to create that reliable pathway so that they can be really, good at this. And one aspect that organizations are still struggling with is how to get better at managing their data for machine learning so that they can create that reusability, reliability, and reproducibility of features. So what I'm going to cover is a little bit about the problem. I won't dwell there. I know we're all very familiar. And then to go a little bit more into some trends that we see in terms of what people are interested in, what's happening in the market. And then what these conversations usually boil down to is that question of build versus buy. What capabilities do we need? Is this something that we can do ourselves? And what might that look like? So what would some sample architectures be? So talking about the problem, in our data that we found, it takes on average about 7 months for people to develop a model, put it into production. And that's only if you're staffed correctly. So if you have some talent shortfalls, that average rises to 10 months. And we've all heard those numbers. Data scientists spend between 60 to 80% of their time just finding data and preparing it, doing feature engineering before they even get to building the model. And since data scientist skills are so coveted, so valuable at the moment, we really don't want them to be spending so much time, especially when often it's the case that they're just duplicating the work that has already been done by other people. So we want to shift this so they can spend less time on that feature engineering component, more time developing models, productionizing them, optimizing them. So to do this, we've got to tackle some of the main data-related challenges that you face during that machine learning model development lifecycle. And the first is a lack of reusability. It's been mentioned already. You don't want a lot of siloed work that isn't reusable, particularly if people then end up having to resolve the same problems over and over again. Another issue is reliability, because after you put in so much effort into developing a model and getting it into production, you want to make sure that it's durable and provides value for a really long time. But then training serving skew is such a big problem, and it can arise for a variety of reasons. And then the third problem is reproducibility. So, it's really difficult for a lot of people to recreate the exact data set that was used to train a model. And, even if people have retained their code, you need a lot more information about where the data came from, how it was sampled, time windows to establish point in time correctness. And there are increasingly, really valid use cases where this is necessary. So if you, need to, abide by some model audit regulations, if you need to do explainable AI, or even just for model retraining. And some of our data shows that people do this at least once a quarter for any given model. And so if you're talking about doing this manually for one model, yeah, sure, you'd be fine, or maybe even tens of models, although you'd find this extremely difficult. But people are trying to break that barrier. How do they scale and get into hundreds or thousands of models? And so the challenge of trying to manually manage features and other artifacts for machine learning just, becomes more pronounced when you're trying to scale up. So, what many organizations want to know and what they come to us for, is this something that they can solve themselves, or do they need a product for this? And then, if not, if they're looking to build their own solution, what would that implementation look like? And across the last 2 years, if we break down the types of requests that we get for information, about half generally fall into that theme of still even just understanding what a feature store is. Then, wanting to know what's the state of the market, how mature is it, best practices for implementing feature stores, pitfalls to avoid, and also real interest in case studies. People want to know success stories. How much value are these really providing to organizations? Then 26% are specifically interested in vendors. So they want to know who's out there, how does one compare to another, and even how they compare to other platforms that they may already have, like DSML platforms, MLOps platforms, sometimes even certain data management platforms like semantic layers. But then we still have a good portion, 21%, who want to build a feature management solution themselves. They want to understand more about the essential capabilities or how to evolve their existing implementation. So if we focus on those first two categories, so the inquiries that we get from clients, so we see that despite the idea of a feature store being around for a few years, there are still a lot of people who are confused about what capabilities really constitute a feature store and what the underlying architecture should be. And one reason for this is because, if we look across the market, not all feature stores are created equal. So if you break really it down into some buckets, there are still some out there that just serve as a repository for holding your training and test data sets. And then many more that also add on that serving component. So for batch or online serving, and some vendors are better than others. And then while many clients that I speak to take this for granted, actually not all products out there can orchestrate the data pipelines to keep features up to date. And this is definitely not a trivial thing, because if we know, and we've seen already, depending on the requirements of your models, you may need data to be refreshed at really high rates. You may need on-demand feature transformation pipelines. So this is not a trivial thing. There are also some vendors that jump straight from creating pipelines to the serving, so not having a storage aspect. And there are also others that their product is more following a virtualized approach. So more flexibility in terms of what underlying storage modalities could be used in compute, rather than having a unified storage of features. And then finally, not all contain monitoring out of the box. So if you can see from this, people are understandably quite confused when they're trying to compare their options. And then this is made kind of further complicated by a high degree of overlap in places with data science, machine learning platforms, MLOps tooling, some even monitoring tools, or even things like data versioning tools or semantic layers. And when we specifically look at DSML and MLOps tools, a few have incorporated what we'd consider to be a feature store into their product. There's been a few more over the years, an initial kind of burst when interest came up in this area. But really, it is still a small proportion of these platforms overall. And those that don't have kind of an explicit feature store still have some feature management capabilities often. So they can, in often cases, orchestrate your data pipelines, at least for batch updates. Some, they often offer model monitoring in production. Some offer data monitoring. Some can provide some feature reuse capabilities. So, reusing engineering code in different workflows. So again, people come to us and they say, well, we have a particular product, what feature management capabilities do we have? Do we need something that's going to plug in this gap, basically, if they identify one? And on the other hand, we have a whole kind of group of clients who would completely deliberately avoid a platform like this, because you can see that they just they don't want to be locked into a particular vendor, that their preferred strategy across the board for machine learning is that they have a composable platform. So it's made up of components, some open source, some best of breed, some custom solutions. And that's the strategic direction that they have taken. So when people come to me and they ask, the question, do they need a vendor could they build this themselves? I like to pose back the question that it shouldn't necessarily be can you, but should you, particularly if something that already meets your needs is available off the shelf. And the opposite can also be true. Sometimes, when people come first with the wanting to know about the feature store, this can just lead to a product-centric discussion when they haven't even considered what their own requirements are yet. So we want to take it back a little bit, start with more of the idea of feature management. So what we have is the concept of the logical feature store. So it's a bit more flexible because it lets organizations define and implement the capabilities that are proportionate to the requirements of their machine learning portfolio. Because the answer to this question of build versus buy and what your architecture should look like will depend on the scale of machine learning operations within your organization and the requirements of those use cases, the types of capabilities that you need. And it very much also depends on what in-house skills you have, and things like resources like money, and time that you would have to undertake this project, because it's not trivial. Obviously, the more complex your requirements and your use cases, the harder it's going to be to build out and maintain this solution yourself. And then on the other side, like much more simple requirements don't often necessitate a full-blown feature store product in the kind of traditional sense. So whether anyone here is just starting to think about feature management, or you're already more mature in your implementation, I want to just walk through the feature management capabilities that make up the logical feature store solution in more of an implementation technology agnostic way. And then based on these capabilities, we can go over different implementation options. So the first key thing to this is to have some ability for storage of pre-computed features. In an ideal scenario, data scientists would be able to commit features to this store themselves. Then within this repository, you need to have features that are accessible so that they can be reused. So here we're talking about some kind of UI or catalog where people can search for features, find what they need. You need to be able to tag to that certain policies and processes so you can govern access in a way that balances democratizing that data and also securing it. Then within this catalog, you need metadata to make features understandable. So things like feature descriptions, definitions, transformation code, when they were last updated, how often are they updated, lineage, basically the kinds of metadata that help to promote trust in your data, which will facilitate reuse. Then, you want to accelerate the development of new models. So you want a way to be able to pull data sets for training and testing, but you also want to facilitate that faster time to production. So you need a way to serve these features directly to models without needing to replicate code, build new pipelines. So this serving, it could be batch or on demand. It kind of really depends on your specific requirements. And then to establish reliability, you want to make sure features are constantly validated and monitored so you can prevent poor data quality or drift from disrupting the performance of your models in production. And then finally, version control features is really important. So you want to be able to allow feature definitions to change over time, but still be able to serve the right version of the right feature to the right model in production. So if we look at all of this together, we know that many organizations have built out all or some of these capabilities to varying degrees, and that there are several product offerings on the market. We've already seen some examples, and I know that we'll see many more across the course of today. And they're largely referred to as feature stores or sometimes feature platforms, so there's some variability there. But as I alluded to earlier, not all of these solutions will have exactly the same set of capabilities. So what we really need to be asking first is not what product you should select, but what are your requirements, and then what architecture can support that. And this is overall the logical feature store approach. So we try kind of coach clients through this thought process, so that basically they're getting something that's aligned to their specific needs. So for example, let's say you just have features and models that are updated in batch. What might a logical feature store look like in that context? So, at a very basic level, you can store pre-computed features in some dedicated tables in an existing relational database in your organization. So they can be retrieved for offline training and offline model scoring. It's really not groundbreaking. Some people are exploring the capabilities of some modern cloud databases for doing in-DB analytics. So for some organizations that might work really well, gives data scientists the ability to create feature tables themselves. The danger here is that, and maybe some of you have come across this, you can really, really quickly rack up some huge costs if you materialize a bunch of features that you don't need, or if you're iterating through feature definitions. That's not ideal. So for that reason and others, particularly governance reasons, organizations that have these capabilities don't really want them necessarily to be used in this way. So if that is the case in your organization, you're kind of back to that problem of trying to figure out, well, then who's responsible for actually taking my code and translating that into materialized features in the store? So it's not an ideal scenario. But if we are going back to the logical feature store kind of capabilities that I mentioned before, it's not just about being able to transform and persist features, keep them up to date, but we also need to be able to find and understand those. So you're talking about adding to this then some kind of feature registry and catalog. And this can be very homegrown here. So we're talking about a very, like a simplistic implementation. So it could just be something like your feature registry could be well-organized Git repository. And then the catalog could be something standalone that you're managing yourself. There's some open source tools that can do this at a more basic level. Or if you have an enterprise data catalog that's available and you are allowed to use it, because that's not always a given, then that could be something that you use to basically catalog your features and add that metadata. And basically encapsulating then all these capabilities is the logical feature store in its basic implementation. But if we consider this, obviously it doesn't include all of the use cases that you may potentially want. So for a lot of people who might just explore this as an initial scenario, often need to graduate off this pretty quick, because as soon as you talk about scaling up the number of models you have in production, or if you've got lots of features, if you need both batch and streaming, and you've got both batch model scoring and online model scoring, then that previous approach isn't going to cut it. And we all, know, having, attended some of the kind of early, really interesting webinars on building a feature store, that when people have approached this problem, they usually then end up looking at two separate databases to handle these kind of diverse use cases. One optimized for, scalable storage, and the other optimized for low latency of retrieval. And the logical feature store, it's not something brand new that you're introducing. It's often recruiting existing technology that you have in your stack. So when we look across the various solutions that have been previously, captured on our featurestore.org website, very common options for offline include things like Snowflake or BigQuery, and online feature stores are most often key value stores like Redis or DynamoDB. But in this scenario, you do have to think about how, what are your data pipelines that are feeding features into these stores? They're typically seen as separate. And again, you can be using existing technology, Spark EMR, there for ETL and orchestrating things with Airflow. But you do have to think about, in this kind of scenario, if you're doing this yourself, you now have two databases that you've got to manage, maintain, and have consistency across them. And you need orchestration to push features from your offline store into your online store so that you're only retaining the latest version of every feature. And this is even before we have touched on demand. So I think what I'm trying to illustrate here is that you're ending up with now, you've got to be able to have a much more comprehensive solution, additional catalog capabilities. You've got many more features at play. And a lot of people who attempt to build a solution like this, some are more successful than others. Others are kind of starting out on this journey and they're wondering, like, should we commit to this? Should we keep going? And others that have built this and they found that it was fine for a while. Now they're looking at the next evolution of this. They want to be able to manage this complexity a lot better. It's getting kind of too much for them. So, when we talk about the more comprehensive, logical feature store approach that we see, when people are trying to emulate something like this, people often start out building something before fully realizing how complicated it's going to get. So if we think about that evolution, people tend to start off with something small that they've built in-house, and then they might graduate to some components that are open source or sort of similar light solution that they're customizing and incorporating some kind of pieced together components. But when it grows to the point where they're finding it difficult to maintain, then they start to really examine the market to think about, is there a vendor solution out there that can really simplify this for me, because it's getting too much of a beast. They want to, set up POCs with vendors. But there are still plenty of customers that we speak to who are fully confident in this, who have achieved something similar. And you can see even from the speakers today that this is definitely done. But, in the majority of cases, though, particularly when we're talking about the size of the enterprise, the number of people that they have on staff, it really, and even the existing technology components they have in their, in their tech stack. I think the real question isn't, could we do this? But the question should always be, should we do this? It's not something to take lightly. And from experience, we've seen that, only a smaller percentage of organizations can actually get to something like this. So to bring that all together, organizations want to put as much care into managing their features as they do with their machine learning models. The aim overall is to create that reusability, reliability, and reproducibility. Feature management systems that I've seen, they vary across organizations, even within organizations, and they evolve over time. So the logical feature store approach, we've kind of outlined this flow to help people to make a decision. So the very first thing that they have to do is understand the current state of feature engineering, the requirements of their machine learning portfolio, the kind of data types they're working with, serving requirements, the scale of operations, and also what inefficiencies they currently have. And then based on that, to determine the kinds of, feature management capabilities that they need, and, thinking about something that's going to satisfy their requirements. It's, that balance between something that's not overly complex and, has too many capabilities that you don't need, versus what's going to kind of future-proof you and allow you to grow and scale over time. And then part of this is to review the existing tools that you have. As I mentioned, in many cases, people already have a data science machine learning platform or an MLOps solution. So there can be a lot of overlap. And then, if the decision is made that you have this gap that you need to fill, and you're thinking of build versus buy, so thinking of whether this is something that you can build yourself, or do you want to use an off-the-shelf product? And then, for your logical feature store, whatever your implementation looks like, my advice would be to appoint an owner early on. So maybe the lead data scientist or a senior data engineer. Somebody has to manage and maintain the system. You want to make sure you establish and reinforce best practices for its use, like making sure everybody adds relevant metadata when tagging new features to the store, or that there isn't duplicated features there. Because the last thing you want to do is for all of your hard work, all of your effort, to turn into something like what we see happen to data lakes all of the time, but to turn into a swamp. So yeah, thank you so much. This has been a pleasure and I'm so happy to be invited to speak at this. Thank you to Hopsworks for hosting and for all of your attention.
Thanks, Georgia. Fascinating. And you did a better job, I can say, than any vendor I've ever heard of peeling back the layers of complexity of an enterprise feature store. And I think that's really, really fantastic stuff. I'm going to ask you a quick question about the interesting statistic at the start, and you may not know the answer, but you said 10% of companies get 75% of their models production. Do you have any stats on how many of them are running feature stores?
No, this research was done, and that was before we didn't include the presence or absence of feature stores, one of the questions.
I think that would be very interesting for the community. And of course, Gartner are very famous for the hype cycle, and I don't remember seeing feature stores in the hype cycle. Where would we be? Where would you think we are as a community right now?
Yeah, well, actually, I've championed the feature store, and it is on the hype cycle for machine learning. So this is the third year that it's been there yet now. The first year it was just feature store, and in the last 2 years it's been logical feature store. So to have more of that kind of flexible term. Okay, I actually missed that. So where are we on the hype cycle? Are we at the top, or are we coming up or down? I don't actually know. Coming up to the top. Okay. So it's something that really still not everybody knows about. Yeah. As I said, like there's still a significant proportion of my calls where I'm still just really helping to ground people in what it is and what it isn't. So I think over the next few years, hopefully we'll see the adoption catch up to the interest. I think so. So if you have questions for Georgia, you can put them on the Slack. We'll be around for, hopefully you can have time to drop in there, Georgia, and we can continue. Okay, brilliant. So we're going to move on. We're going to have a talk now from Delivery Hero. We have Breno Costa. Breno is a seasoned ML engineer with many years of experience in ML-driven software development. Over the last 5 years within ML platform teams, his mission has centered on delivering solutions to empower data scientists and ML engineers within application teams. He developed and delivered 2 feature stores running in production, as well as other platform components to streamline different steps of the ML lifecycle, such as model development, deployment, and monitoring processes. We're delighted to have you, Breno. How are things? Go and let's try and get over the hurdle of sharing your screen.
Okay. Thank you for the introduction. I think you can see my screen. Right?
Yes, we're good. I think that's you. So
okay.
Stage is
nice.
Yours.
Yeah. Hi everyone. So in this session, I will present this feature store solution that we have in the feature store. I think the focus here will be on the how the feature store is driving the efficiency and quality for some feature engineering process in some teams at Delivery Hero. And I will talk about our context, workflow, and some parts of the architecture. And before jumping into the presentation itself, I just want to talk briefly about the Delivery Hero, if you don't know, and where my team fits in the organization. Delivery Hero is a food delivery company founded in Berlin, that became a global company. Delivery Hero is a holding of different brands, and we are present in over 70 countries across the world. You might have used some of these apps of some of these brands here, like Foodora in Europe, or Foodpanda in Southeast Asia, Glovo in Spain, Pedidos Ya in South America, and all of these brands are part of the H. And we have an internal platform called Pandora. Pandora is an internal name that powers some of these brands of Delivery Hero. And I'm from the ML platform team within Pandora. And we have some cross-functional squads in Pandora. These squads work on different aspects of the product. And I think our mission as a team is to standardize some the ML lifecycle. We try to provide some platform components to cover the different parts of this lifecycle. That's our mission. We have some other different platforms within Delivery Hero that use different solutions, but just to show to you how this ML platform team fits in the organization. Back some 1 or 2 years ago, we were evaluating our context in our tribe, and we have this kind of context. The data science and ML engineers, they create their model implementations in different GitHub repos, and we provide some model interface, and they have to implement the training and the inference parts, and they use it to create the features for ML models inside these model repos. But this became inefficient for the company as the number of people, teams, and projects scale up. And we saw that features are not easily reused across different projects. Similar features were created over and over again. And there are some lack of standardization for the process, like the feature generation and feature quality process. And we decided to move forward with the feature store idea. And we decided to implement this feature store as a way of mitigating part of those issues. And the feature store acts as a central component that allows the people to create, serve, monitor features. This is not only the store part, let's say, but I will show some other parts of the architecture. And we've seen that this has been increasing the feature reusability, and then most of the feature generation and monitoring processes are standardized. And as a consequence, we've seen increased consistency and quality, and reduced effort to create new models. And in our case, we have some different kinds of features. For example, we have some features which are calculated by in real time, let's say, because they depend on the input of user. For example, the location is one input provided by user to use the Delivery app, and we have some features calculated based on their location. We also have some features calculated every minutes, but the most of features are calculated in batch. I will focus more on this batch part in this presentation, because I think we have more platform components provided for this use case. Let's talk about workflow. In our case, we decided to create one feature repo. All the features are in the same repo, and we maintain this feature repo as a platform team, but the users can contribute to this repo to create features, to make configurations, and the same repo is shared with different teams. They have permissions to create branches, open pull requests, and so on. And within this repo, they just need to clone this repo in their local machines. They can create and test features using their development tools. Let's say they have VS Code or PyCharm, these development environments, and everything they need for development purpose is out there. They just need to create a feature transformation codes. They have a CLI to run these features. They can create some configuration to monitor the features. They have a CLI to run the monitoring modules, and they have access to some reports and so on. And when the development is finished, they open pull request, request reviews from their peers, and this is also part of the process to guarantee the code quality and consistency. I think this is very important. And the CI pipelines are triggered as soon as the PR is merged into main branch, and those pipelines update some remote configuration files, some Airflow DAGs. They don't need to interact with the orchestrator, with the Airflow to run the features. We have some pipelines that make this in automated way. And just to show some high-level architecture, we have some components here. The feature transformations components allow us, the users, to create features using SQL or Python. They can choose according to the use case. A feature monitoring component, we have two kinds of monitoring. One is using rate expectations to set to run some assertions on the data, and also a component to detect drift detection. And these are pipelines managed by the Airflow, and the feature transformations, the pipelines ingested data to offline and online store. And as offline store, we are using BigQuery to run the SQL transformations and to store the data, the historical data. And we also use the RADS as our online store to provide the low latency database for model server APIs. And FEAST, we are using to provide a registry layer, some materialization jobs, and also to provide the SDK to get historical features and online features. This is the high-level architecture. Let me talk about the components. Feature transformations in Python. This is mostly used when they need to write some features that need some more complex transformations that cannot be managed in SQL, or when they need to use some Python package to apply some transformation function that is not available in SQL. They can use this. We rely on Kubernetes to run the transformations in Python, and this is orchestrated by the Airflow. And we also have this module to create the feature transformations in SQL. Data scientists can write their features using SQL, and this is definitely the most used one. I think the combination of dbt and BigQuery gives us many benefits. Both tools are extensively used at Delivery Hero, but I think they are mostly used on the data engineering side. But we decided to use especially dbt because it provides some benefits for us. Let's say BigQuery is a tool that makes it easier to manage the pipelines, your SQL scripts. For example, if you have a complex transformation pipeline, you can decompose your pipeline in different steps, and dbt provides some functionalities for that. It has a good usability. It's flexible for different data sources, and it has a seamless integration with BigQuery. And BigQuery is good also for many reasons, because it is serverless and provides a high processing power. to bring scalability to our workloads. And regarding the cost in Live project, we have used the flat rate compute pricing to manage costs, and in staging for development, we have used some recent feature released by BigQuery, which is the auto-scale to auto-scale the slots, the processing slots in BigQuery. Just to provide one example of feature transformations, in the feature repo, they have this kind of folder structure. For example, there is a folder called features, and this folder contains a subfolder DBT, and there are some features grouped by entities. Some examples of entities are vendors, products, and customers. But for this example, I just create one project called Sandbox. I cannot disclose some details on the feature transformations, but just to give you an idea of this, I just create one vendor popularity features.sql file, and the content of this file is shown at the right. In the file, you can see at the top of the file, we have some configurations. This is a mix of a DBT configuration and BigQuery configuration. And with this configuration, we can define some configuration for the tables, for example, the partitioning and the clustering. And we can also make some configurations on DBT, how DBT will materialize the data, what will be the incremental strategy for DBT, and other aspects of DBT can be defined here. And the data scientist can write a SQL file. And this is an example. If you look at the line 15, there is a brackets. This is part of the DBT syntax. With DBT, you can call some functions or macros from DBT, and this helps to create the scripts. And just to give another example, at line 25, there is a function called ref, and in DBT, you can use this ref function to use the results of a table that will be produced by another script in your project. For example, order with matrix is another script called orderswithmatrix.sql. And when you do that, when you create your SQL in this way, DBT will automatically generate the dependence graph for you. You don't need to do nothing. Yeah. And DBT also offers CLI. With the CLI, you can run the SQL scripts. You can run all the scripts. You can run a subset of them. You can also run some tests. You can create tests for your SQL. And you can manage the dependence graph, as I mentioned. For example, this is a screenshot of a documentation page from DBT. And in this documentation page, you can see the lineage graph generated by the DBT. The vendor popularity features, the right of this lineage is the actual feature table, let's say. And this script uses the order with matrix as a dependence. And order with matrix use another ones as dependence, and DBT provides this this kind of management for us. I think one benefit of another benefit of DBT is with this pipeline decomposition, we can also reuse some intermediate transformations. For example, the orders past 60 days is a SQL script that can also be reused, because this will produce a table that can be reused. This is another benefit of DBT. You cannot reuse only the features, you can also reuse other parts of the transformations. And other component of the our feature store is the feature monitoring part. We have two components, as I said. The first one is quality checks. This component is built on top of Great Expectations. Great Expectations is also extensively used at Delivery Hero. But for our use case, we decided to create one wrapper on top of Great Expectations to make it easier for data scientists and ML engineers to create this. For example, the folder structure is quite similar than the transformations one. They just need to write one module. For example, vendor popularity features is a monitoring module in this context. They need to write a function to fetch quality checks, and they need to write these expectations for the data. And this is a syntax from the Great Expectations. And they also have a CLI to run these monitoring modules and have access to the reports. And these reports on the right side is generated by the Great Expectations. And they can see the number of evaluated expectations, how many expectations have failed, and they have details about the failure. They can use this report to debug the issues and to fix the problem. This is the first one. The second one is for drift detection. The folder structure, the idea is the same. They have this folder structure. They can reuse the same Python module to define the monitoring module, the vendor popularity features. But for drift detection, they need to write this function, fetch drift config, and they just need to return this drift config. And this drift config contains some information about the columns that will be analyzed, the metrics that will be used to calculate the drift, the distributions, and the threshold for each column. And this component is built on top of Evidently AI. When the pipeline runs, it calls the Evidently AI to runs this drift detection. And they also have a CLI to run this monitoring module and have access to the reports. They can run this in their local environment and have access to these reports. This is an example of a report generated by this drift configuration. It has 6 tests, and when one test fails, you can see that it was failed, and you can see some chart. And this is also automated. I will show later how this is automated, but they have access to these reports on the live environment. And we, as per our experience, we have detected a lot of issues with these two components. For example, unexpected duplication of keys in some data source tables because of many reasons, because someone changed the application that produced the data, for example. This is one reason. And there are other detected issues. For example, some events that happen in some countries that was triggered by some event that we don't have much control on. This has happened sometimes. Or the classical error, let's say, some data production pipeline has changed the ETL scripts, or has deprecated some table or field, and so on, and that produce incorrect data. And all of these issues can be detected by these monitoring components, and this brings some quality and reliability for the feature data which is produced in the feature store. In terms of feature registry, we are using the FEAST, as I mentioned. And the FEAST, you can define the data source that you want to use, and you can define the feature view, and the feature service. For that example, I just define here one feature view with the schema, with a data source from BigQuery, and with the schema, you have to define the name and types. And for feature service, I defined this feature service with only one feature view, but you can combine some feature views to create one feature service. And Feast provides this user interface with the entities, with the feature views, feature services created in your registry. You have access to this feature view. They can version the features, and using this, using Feast, they can also create a feature views using different data sources. For example, they can create using stream data sources or some files as a data source and so on. But in the feature store for batch features, we use the BigQuery, as I mentioned. And the feature serving part, we have to create some setup to deploy these different RADS instance in different geographical regions, because we have some constraints about the latency, some requirements, tight requirements about the latency for model server APIs. And we have this multi-regional setup. Just put 2 regions here to give an example, Asia East 1 and Europe West 3. But the idea here is we have the RADs in different regions, and we have the model server APIs deployed in different regions as well. And we can have the model server APIs in the same region than RADs, and this to reduce the total latency. With this setup and with some optimizations on Feast SDK, I think it's important, something important to say. We have to make some customizations on the Feast to materialize data in different regions, because it's not kind of supported on Feast. And we have this setup, and we have good numbers of latency. We are able to, for some use case, we are able to fetch data with less than 5 milliseconds for P99, and this is a good number for our use case. And for pipelines, we use the Airflow to orchestrate the feature pipelines. For example, this would be like the DAG for this example proposed by me in this presentation. We can reproduce the same dependency graph that is generated by DBT. We use the DBT manifest file to generate this dependency graph on the Airflow, and we can reproduce the same. If some task fails, we just need to resume from that task and to save resources, computational resource. And they can also backfill tables. There is a configuration that can be used to backfill tables, and these DAGs are generated dynamically, programmatically. They don't need to interact with Airflow at all. And these DAGs run on live environment, and if some issue happen, for example, feature transformation is failed, or the data quality issue is found, is raised, they receive Slack notifications. They can have access. They can click on the issue and have access to the reports. For these, we have the reports stored in our metadata tracking server, both data quality and brief reports, and they can be verified by users. And just to finish my presentation, some takeaways from our side. I think having this central component actually promotes the reusability of features. I think at the beginning, this might be hard to get adoption from all data scientists, because we have to onboard them into a new tool. But little by little, they are sort of convincing when they see that they can reuse some features from the repo, when they contribute to their features to this repo, and this will be reused in different models. And this is very important for the long-term objectives, long-term goals of the company, because the data scientists can leverage existing features, and this reduce the creation of redundant features, and also to reduce the engineering efforts on squads, since a big part of the job is provided as a service. And I just put some articles here in the presentation. When you have access to the presentation, you can go to our tech blog to have more details. We have 2 blog posts on the feature store, and one for feature store, one for feature monitoring, and another about the personalization strategy at Delivery Hero. Yeah, thank you so much.
Brilliant. Thank you, Breno. Great to see the great work you're doing and bring machine learning to production at Delivery Hero. I have a question. I'm going to start with a question about George's statistic. Right? You remember in the previous talk at Gartner, she said that only 10% of companies, 75% of their models make it to production. Are you in the 10%? Are Delivery Hero in that 10%?
No. I think we have many models going to production using the feature store. Yeah.
But do you think, like, I mean, just to go on that, do you think the feature store helps increase the percentage of models that make it to production? And, you know, do you have any estimate of that?
Yeah, I think the feature store is helping the data science to create more models, to reduce the time to create new features. And yeah, I think this has some impact on this. Right.
And it was really fascinating. I think this is the first talk we've had where you've talked about using DBT for feature engineering. We at Hopstix, we wrote about this actually in the summer. I think it's going to be a growing area of use for feature stores, so feature engineering in DBT and SQL. But have you seen many limitations in engineering features in DBT? Because, you know, not all the libraries are there that you might want to have in Spark or Python or even Flink.
Yeah, I think these SQL features cover a big part, but this is only a part of the total amount of features. For example, if they need to generate some vector embeddings, for example, this sort of thing, they cannot use DBT and SQL. But I think the SQL is still a big part of the feature engineer, and I think it covers most of our use case.
Right, and then just one quick question from Alexi on the chat. How good is Feast deployed on top of Google BigQuery and Redis in terms of performance? Can you do all the things like materialization, feature retrieval on demand? I know you talked about adding support for multiple regions. What's your experience?
Yeah, I can say, for example, for this multiple regional deployment, Feast doesn't have this configuration to materialize a subset of data in each region. We have to create a customization on top of the Feast configuration file. That's one limitation. We also had another limitation in terms of performance on the Feast SDK. To get online features from Redis, we were able to optimize some parts of the code that fetch metadata. But yeah, we don't use the on-demand features. But I think for this use case that I've presented, it is good. So far, so good. Let's see.
Brilliant. Thanks very much, Breno. Okay, it's time for a break, everyone. We're going to start again. It's slightly less than 10 minutes now, 8 minutes time. I'm going to spin off and maybe get something to eat, or something to drink, but I'll see you all at 5 to the hour. Unless you're in India, then it'll be 5 to the half hour. Okay, thanks. Okay. Welcome back. I had a nice quick break there. I hope, hey Claire, how's it going? So we have, now we have another session starting. We have 4 talks from Arise, Bytewax, Dagworks, and Databricks. And I'm delighted that we have Arise again here at the conference, I think for the 2nd time now. And Claire Longo is a machine learning engineer and data scientist, and she's focused her career on building and scaling ML engineering teams. She's currently head of ML solutions engineering at Arise, leading post-sales machine learning solutions engineering efforts and assisting Arise customers in integrating ML observability into their MLOps infrastructure and workflows. And prior to Arise, she led the MLOps team at Opendoor and established a new machine learning team to deliver data-driven products at Twilio. All right, Claire, are you ready to go?
Yeah, let's do it. Thank you, Jim, for the introduction. Should I go ahead and just share screen here?
Yeah.
All right.
And we're live.
Great. So I'm talking about monitoring feature stores today. Shout out to ChatGPT-4 for the catchy title here. Stop blaming the algorithm. It's your feature store. The reason I love this title, though, is that it really does hit home a trend that I've seen over and over with feature stores and with models in production, where a lot of the issues we see with the model in production once it's deployed is not really with the model itself, but it's actually with the data quality of the model input. So that can be traced back to feature stores, to ETL pipelines, that kind of thing. So what I'm going to be talking through here is kind of a guide to monitoring your feature store, what kinds of monitors we should configure and that kind of thing to kind of maintain the quality both of the features and the models downstream that depend on it. So I think the group here already knows what a feature store is. I don't want to kick off the talk by explaining that one to y'all. I think we're all caught up here. So instead, I'm just going to go ahead and dive right in and talk about what can go wrong with a feature and a feature store. What does feature failure look like? Across my experience as an ML engineer, data scientist, I've actually been on teams that are building feature stores. I've been on teams that put models into production. I've actually seen a lot of this stuff on my own teams. And so definitely speaking from experience here, I'm going to talk through 3 examples of just feature failure that I've seen, and then we'll talk through monitoring, and I'm going to bring it back home and talk about how we could have monitored in these situations to prevent this. And these are really common issues that I think people see in models in production across the board. So number one that's super common is vendor data is shifting. So let's say you're a data scientist, you trained a model, and that model relies on data that maybe you're purchasing from a third party. Maybe you're even scraping this data. There's a lot of different ways to get rich data into your models. But if you're not generating the data, your team doesn't own the data, you're not able to really control if that data changes under your feet. So we've seen situations where that data will just shift. Maybe we're changing the data type. We decided that it could be a string instead of an integer. Those kinds of things are breaking changes that will break a model that depends on this data downstream. So it's definitely something that we want to be able to monitor for. Number 2 is statistical drift. So I'll get into a little bit more detail exactly what this is and metrics to evaluate it. But essentially what this is a natural thing that happens where data just changes naturally over time. You have a statistical distribution, you train your model at a certain point of time, and you capture those distributional patterns, but then you deploy that model, and let's say 3-4 months later, maybe that distribution has changed a little bit. Maybe something has changed in the economy, something's changed in the world events that can really impact the distribution of your data. And so when you see that kind of natural drift, it's important to retrain your model, keep your model fresh, but those patterns show up in your features in the first place. The last one is online and offline skew. So this one here is, let's talk through the scenario. A data science creates a model in a notebook. Let's say they do some iterations, some hyperparameter tuning, feature engineering, and they come up with a great model. Now it's time to deploy it. And now you have a ML engineer in some situations will step in and do that deployment step. And in that situation, they may be rewriting that online and offline feature transformation. So the data scientist already wrote some feature transformations in a notebook. You've got to, as an ML engineer, take those transformations out of the notebook and scale them and deploy them. And so you're essentially running the same transformation in like 2 points in the ML modeling lifecycle during model training and like research and exploration, and then again during deployment. And it's important to make sure that those transformations actually match up and are maintained together. Great. So different types of monitoring. There's 3 kind of veins of monitoring here that I'll talk about. Where we're mostly focused right now is in the middle, the data monitoring, and a little bit to the right with machine learning. The first one I think is very familiar to any software engineer here. That's system and infrastructure monitoring. You wouldn't deploy software into production without solid monitoring on that. And that same kind of concept applies to your data pipelines and your actual models once they're deployed and part of working software. The difference, though, is that you've got different people involved across this pipeline, and usually like different tools, different needs, different tech stacks. So starting with systems and infrastructure, you may have a DevOps engineer, a software engineer that owns that. They will tell us that ML ops is just DevOps for machine learning. It really is. Then you'll have like a data engineer that's maintaining quality of data pipelines, and you'll have the ML engineer who's responsible for maintaining the model itself. So the interesting thing here, and something that I actually get asked often, is let's say you're already on the end of the funnel and you're doing machine learning monitoring. You're monitoring your model inputs and outputs together as a model and looking at how those drift and move together. Do we need the data monitoring upstream? And my answer to that is yes, definitely. I think there's a lot of value in having monitoring at every piece in the life cycle that the data travels through, so you can really pinpoint and root cause an issue with your data. So even if you have like a good monitoring solution around like your machine learning models, your software systems and infrastructure, layering in some additional quality monitoring into your feature store is kind of a no-brainer, because that way you can like catch issues with your data upstream before it really impacts those like downstream systems, which would be like your machine learning models. Cool. So I thought a good way to kind of present this would be to walk through a day in the life of a feature. What is the life cycle of the features that a feature goes through? So starting on the left here, you're looking at your raw data. This can come from different sources. It could be streaming data that's collected in real time, could be the vendor or open source data that I mentioned, maybe your web scraping, purchasing data, or it could be internal databases. This could be a database that a different team owns that you're trying to access some data, or it could be a database that you own. So the first step here is really to like collect a bunch of raw data. The next step is data cleaning. This is typically data scientists, data engineers doing this type of work. They're really cleaning, pre-processing that data for a machine learning project. Then you go into feature engineering. This is where we're actually making the feature. The feature is born in this step. So this is really the beginning of their life cycle, but there's still that upstream kind of raw data that it's dependent on, and the quality of the feature itself is also going to be dependent on that upstream data. So feature engineering is, again, I'm not going to go into depth here because I think we all know, but we're essentially applying transformations to this data to create features that will be useful in a machine learning model. And that looks different depending on like if you're doing deep learning, like LLMs, there's definitely some different kind of data processing steps here, but essentially you're kind of creating features that are going to be used in a machine learning model, both pre and post production. Most people are dumping that into a feature store, very good idea. And then there might be a second feature engineering step here. This one I see is actually quite common, where you already have some features in your feature store, but for a specific team or modeling use case that's drawing on that feature, they might apply additional transformations. So you might have different kind of transformations being applied to your features as they come out of the feature store and get used in these different use cases. Then the features get used across some different kind of steps in the modeling lifecycle here. So definitely useful to tinker with them in like a research and experimental phase of a project, seeing what features are valuable in your modeling project. That's going to be useful in model training. This can be like initial training and testing models against each other. It could be like an automated retraining cycle. And then it's also going to be used in model serving when you're actually getting inferences and predictions out of that model. So what can go wrong? And really, where should we monitor this feature? So my answer to this is we should monitor it every step that we can, because it really helps put together a picture of root cause, exactly where the breaking points are. But there's a lot we can do within the feature store, which I'll get into. So first place where things can go wrong is that data shifts. You can have changes in your raw data. The second one, the second one is data cleaning. There could be quality issues there. An example of like quality issues that I've seen is like missing values. Maybe there's suddenly like a new value that shows up in a system that the model hasn't seen before, and that can definitely cause problems downstream. Feature engineering, so this can be broken feature engineering code. You're writing ETL, maybe you've got code in a notebook, maybe it's actually deployed somewhere else, but essentially like you've got these transformations on the data, and that can definitely have bugs because it's code. Then within the features themselves, there can be feature quality issues there. And then again, you're doing more feature transformation. So again, another opportunity to break things. And then on this side of things, you have that kind of online offline skew with the feature serving. And then in training, so yeah, you're going to have in this phase, you're going to have features as model input. So the feature is essentially going into the model to get that inference. So you're going to have like training and serving skew, online offline skew. The difference here is so like training and serving is like your feature look different when you train the model than when you're actually trying to serve it and get a prediction. And so that's going to cause some discrepancies in your model quality. Online offline is like you've got an online feature store, offline features. Maybe there's some features that you're able to like pre-compute before inference time, because obviously if you don't have to put something in your critical path, don't do it. So feature serving, we like to keep like really lean. So anything you can pre-compute is important there. You want to make sure those will always line up. Great, so that is everything that can go wrong. But wait, so here's kind of the challenge. If you own a feature store, if you're working on a feature store, you don't necessarily like own that upstream data. You may not even own the infrastructure for like the model deployment. And so how do we get like that end-to-end monitoring that I'm always advocating for, monitoring for the data in every step of that machine learning lifecycle? It's actually very hard to do because this is typically going to cross like multiple teams. So as like a feature store team and someone who owns a feature store, what I want to do here is I want to set up monitors that are going to give me like the most coverage as possible. I want to make sure that I can like preemptively detect issues so that my like downstream customers, the models that depend on my system, are going to be kept healthy, and I can like mitigate any issues with my features that those systems are dependent on. And I also want like a little bit of coverage on like the upstream data issue. Like I do want to trust my other teams to be monitoring really well. And for the most part, like I have seen people monitor that data very well, but they're not necessarily monitoring it for my use case specifically. So they might not like have full coverage of every issue that could really impact me as a customer to that data. So being able to set up my own monitoring across my feature store, super valuable. But the question is, what monitors should I really set up? So I like to think of three kinds of monitors here. Number one, data quality. This is a no-brainer. This is what I talked about in terms of like missing values, new values suddenly appearing, things that would really be like a result of like a broken data pipeline. The next one is going to be tabular drift monitors. So what I mean by this is that statistical distribution drift where you're seeing the data change naturally over time. This can be gradual, it can be sudden, but it's usually happening due to like natural events. And we want to keep the models up to date and healthy with that. And this one requires like some fancy statistical calculations to really monitor this, because essentially what you're doing is you're looking at you're measuring the distance between two statistical distributions. So there's some great metrics around that, including PSI, KL divergence, that really what these are essentially doing is like they're looking at two histograms and they're measuring like how similar are these two histograms. And if you have like true drift, you're actually going to see like kind of what we're seeing in the illustration here. We're going to see two histograms that really don't look the same. So if your features see this over time, you have drift in your features. So the last one is embedding drift monitors. And this is really interesting because this is important for deep learning, but it's also really important for like the LLM use case, which we're seeing so much of these days. This is really a popular thing to be building right now. It's definitely the buzzy thing. So if you're working with like generative AI, the question is like, how do I even like monitor a system like that? It's really hard. And the reason it's hard there is like your data is not tabular. Thinking about monitoring like a tabular feature, like, I don't know, a feature like credit score, or maybe like income, like those kind of like strong tabular features, it's very easy to just visualize in the 2D and monitor for like data quality and drift. But when you look at the data that is used in these like LLM systems and deep learning systems, NLP, computer vision, you're looking at embeddings, which are like n-dimensional. So how do you monitor drift on that? I'll talk through some approaches on that one as well. So those are the three. I'm going to dive into all three of these and just kind of give examples of where they're adding value. So number one, data quality. The areas that I've seen these be very valuable kinds of monitors for like catching issues is things like missing values, new categorical values, which I mentioned, catching an outlier. Suddenly you're seeing just a really high, really low value in your data. Maybe it's like generated by a new bot or something like that. Catching online, offline skew can be important here. You can create some pretty fancy custom metrics to compare different data sets. So configurability is what you want here. You want the ability to really kind of have some great out of the box quality metrics, but also be able to kind of write your own and can configure the data quality monitors that are really going to be like most valuable for your use case. I do get asked a lot of like, what should I monitor for? And I think it really depends on your use case, and no one knows your data better than you and the people using it downstream, like the data scientists, machine learning engineers that are creating models. So coming in with a strong hypothesis of like what could go wrong with the kind of data that you're looking at is really helpful here. But in general, like missing values, outliers, categorical, online, offline skew are kind of the things to think about here. So that's data quality. So next is drift. There's two kinds of drift. So sudden drift can happen if there's just like an immediate thing that changes the patterns in your data suddenly. And gradual is obviously what it is that kind of like just kind of gradual over time divergence of the two data sets. When you're thinking about drift, you've got two data sets. You've got like a baseline data set and a current data set, and you're probably working with some moving windows there. And you want to be able to catch both of these, like the sudden and the gradual. The sudden drift could be like an immediate issue with like data pipelines breaking. It could be like an immediate like event, like something like COVID, I think would suddenly change a lot of data patterns naturally. Gradual drift can just be like things kind of change slowly over time. And you also want to be able to detect that, but it might not require that kind of sudden immediate response to it. But this is all an art in like choosing your baseline data set. One of these distributions that's used as the baseline for comparison, and then the current one. And what I've seen work really well here is training data versus production data if you're looking at the model downstream. But if you're looking at just the feature and you're not tying it to the model itself, what is really useful here is going to be just like a moving window. What was last month versus this month? What was last week versus this week? And being able to track those over time to catch both kinds of drifts is definitely the recommendation here. I think one point to note is like the difference between monitoring a feature store and a model. So the model, you're monitoring the model inputs and outputs together. So you're already monitoring some of these features with the model output. And that's very valuable because if there's an issue with your model outputs, you're able to tie that back directly to any issue with the feature. But when you're doing that, you're already kind of downstream of any feature issue. So when you're monitoring upstream as well, just on the feature store, and you're not correlating it to the model output, because there's probably a lot of models, honestly, that are depending on those features, you're able to kind of like preemptively catch stuff before the data scientists have to look for a problem there. I know we're running out of time. So really quickly, this is the embedding monitoring approach. So you're now in the ND dimension, you're looking at monitoring unstructured data, text data, computer vision data. Essentially, the way to approach this one is you create these kind of representations of the data through embeddings, and then you're monitoring the embeddings themselves. So the way to monitor drift in an embedding would be to look at like Euclidean distance, cosine similarity, you've essentially reflected your data into 3D latent space here, and you can identify like natural clusters of things. So you'd be able to see like if there was sudden drift, gradual drift, if there was like a whole new cluster that appeared in a visualization like this. The way to detect that would be comparing the distance of the clusters from each other and monitoring that over time. So that can be done actually really simply with like cosine similarity and Euclidean distance metrics on this kind of data. So wrapping it all up here, we've got these kind of 3 scenarios I talked about. You've got vendor data shifting. How do we monitor for that? I put data quality monitors on the feature store. So you could see like the changes in like data types, missing values, that kind of thing. Statistical drift, you want to monitor tabular and embedding drift with those kind of statistical metrics. And then online, offline skew, that scenario of like taking the model from like notebook to production as well. You want to be looking at custom metrics for that data skew itself. So kind of a data quality scenario there as well. Great, I want to pause for any questions.
You can hear me. That was brilliant. We actually have a couple of minutes for questions, so you have time. I'm gonna start by asking a question that I hear quite a lot. I think a lot of people are confused about it. When we store data in a feature store, at least at Hopsworks, we would say store that data unencoded if it's a categorical feature, and if it's a numerical feature, that you want to standardize or normalize or scale, we would say store that unencoded in the feature store and then do the encoding in the training and inference pipelines consistently. But in some cases, people might say, well, I want to store the encoded data in the feature store. Can you do monitoring of encoded categorical variables or scaled numerical features, and does that make any sense?
You totally can. I would want to monitor it honestly at like both spots if possible. But once it is encoded, like data scientists are probably monitoring it with the model output there. So they're probably like doing the encoding, like they take unstructured data, turn it to embedding, they take categorical data, one hot encode it. They're probably monitoring those transformations. It kind of gets to this diagram here, where you have that additional step of feature engineering before it's going into the models. The thing that's interesting though is like I would monitor both because there's probably different feature transformations that they're making there. And if an issue shows up with a model, you want to be able to tie it back to like their step of the feature engineering code or like some quality issue with the feature upstream. So being able to kind of monitor in both spots, I think is valuable here.
Yeah, I guess one of the challenges there that I would see, like particularly if you take gradient-based models, gradient descent-based models, is that we often normalize the numerical features, for example, and we want numerical features in deep learning. It's very hard then to define rules, So in your raw data, you have a very wide distribution of your feature values. Outliers are easier to identify, but then what's the standard deviation in your raw data is not a standard deviation in your normalized data, and then it becomes quite challenging for people to really understand that. I don't know. I think that's something I find very challenging to discuss with people.
Yeah, I think there's definitely some stuff to unpack there. Are you thinking about like the approach for monitoring it before?
Yeah, well, I guess what I'm curious about is just like we have standard techniques, like you showed some very interesting techniques, of course, comparing data distributions and distances between those data distributions, but they're really typically for unencoded feature values. But then, when you encode them, you're obviously shifting the distribution, and then those techniques, become less. I guess there's less of a signal to work with.
Sure.
So I think it's a very open area for work, and I'm curious to see what's going to happen in it.
Yeah, that's very interesting because I love monitoring at every point you can, but I mean, what you're raising there is like there might be some challenges to monitoring pre-feature transformation, specifically in terms of like the statistical distributions too. So yeah, deeper.
And the LLM ones is really interesting. So you mentioned that you could take, you could compute the cosine similarity between two embeddings to get difference between them. Do you in your case, do you need a vector database to do that, or do you do it on demand, or what's Arise's kind of way of doing that?
Great question. Arise will create embeddings for you. So we have some code that will actually create these, but there's also the option of like extracting embeddings right out of your model, which is again like a downstream thing once you got the model involved, or getting embeddings out of something like OpenAI, which I think is really cool way to just kind of generate and extract embeddings. But there is like the step here of like, yeah, you've got the raw data like computer vision, NLP, you need to turn it into an embedding to do this. So that's definitely kind of part of this pipeline here. I think of that as like a feature transformation step for sure.
Cool. Now there were two questions in the Q&A section. I kind of got carried away. Maybe we can take them on Slack. Thanks everyone. Thanks for those questions. Thanks very much, Claire.
Thank you.
Talk to you again. Great. Now we have Xander Matheson, and Xander Matheson is the CEO and founder of Bytewax. Before starting Bytewax, he worked across machine learning infrastructure and data science teams at Heroku and GitHub. He started Bytewax to try and make it easier for engineers to add real-time capabilities to their products. We really like Bytewax because we really like the fact that Python developers can now get into streaming without having to build this massive infrastructure. And I know Xander likes to surf as well, which I also like, so we have that in common. Xander, over to you.
Hey everybody, I'm going to do the little share my screen dance. So we'll see if we get this working correctly the first time.
Yes, we're good to go.
Right on. Well, I'm really excited to be here. I've been listening either directly or in the background all day, and there's been some really interesting things. And what has really stood out to me in many of these talks is just how complicated some of the architectures and setups can be when you're talking about these production machine learning systems. So props to everyone here who is managing systems like that. I know it is not easy. So my little introduction that was made by Jim, thank you. I'm Xander, founder and CEO of Bytewax. And today I'm excited to talk to you a little bit about real-time machine learning and in specific real-time feature pipelines. So you might be asking yourself, in addition to all this complex architecture that I already manage and infrastructure, why do I need to add in additional complexity about real time? And the truth, which is its own session, is that you may not need to, but I'm going to share today how you can start thinking about that, adding real-time machine learning and real-time feature pipelines, and potentially bring major impact to your business with streaming data and real-time ML. So real-time machine learning is all around us today. You have recommendation systems like addictive TikTok videos. You have ads on many platforms, some of those which are highly relevant and using many different inputs, streaming inputs. You have personalization on many of your favorite apps and websites. And then another good one is fraud detection. So when you're traveling, you get that text message right after you buy some train ticket or something like that in a foreign country. So that's a good example of many of the real-time machine learning systems we see today. But before I go on, a little bit more about me and why I'm here to talk to you today. So as was mentioned, I'm the CEO and founder of Bytewax. And before that, I'll talk a little bit about Bytewax, what Bytewax is. It's a stateful stream processor. It's an open source project. As Jim mentioned, it's Python, and we made it so it's easier to work with streaming data. But before Bytewax, I worked at GitHub, and before that at Heroku, and was working in many different data hats, I suppose, between data science, data engineering, machine learning, and machine learning infrastructure. Kind of migrated my way through a few of those things. And at the end, I was working on machine learning infrastructure at GitHub. And I left GitHub specifically to start a company focused on enabling real-time machine learning, as it was a big point of friction for us at GitHub. So I'm also outside of working on BiteWax, a proud human and dog dad. I had my first daughter about 1.5 years ago, and I have a 8-year-old Aussie Shepherd Border Collie mix. This photo here is me trying to look cool, hiking up to go skiing. Outside of surfing, I also like to go skiing. And you can find me in the BiteWax Slack or in the featurestore.org if you want to chat more, or if you're happen to be in Santa Cruz where I live, send me a LinkedIn message and we can grab a coffee. Okay, on to the talk. Today's agenda, we're going to cover a little bit about background about real-time ML is, and then we're going to dive into how we can enable this with streaming data and stream processing. So moving right along here. So we all know that timeliness matters, but how much does it really matter? It has been shown to affect the bottom line of businesses directly and indirectly. In this case, we're talking about latency, but there's also freshness that is another aspect of this. So these statistics from Google, Walmart, and others may not look like much, but at their scale, it is millions or billions of dollars. But you may be thinking to yourself, oh, it's only for big companies. It can also affect smaller companies. Timeliness or latency can impact in additive ways how well your organization or big business will do with things like customer retention and customer lifetime value. But not only that, but in some of the tech-enabled businesses, it's a winner-take-all type of market. And you're competing directly to provide the most impact or value to the user, and this will result in either thriving or going out of business. So what does real-time machine learning really look like? Broadly, when we talk about real-time machine learning, it fits into one of two categories. And the first of these being offline training and online serving. What happens with the offline training and online serving is you, in a batch method, train your model, and then you promote it, and then you serve it in real time. And the other method is when both that training and serving happen in an online fashion. So you're constantly updating the model. So we'll kind of talk about what these are in more depth. This is a simplified version based on some of the diagrams I've seen today, but it's a sketch to illustrate from a high level how the online system works. So you have a mechanism to train your model in a batch fashion with some historical observations, and then is promoted to a serving layer where it can then make predictions. And then you have another system where you're receiving new data as it is generated, processing those observations, and then making them available to the serving layer so the fresh features can be used in the model inference. Obviously glossing over some of the little intricate bits of these systems in this. Another sketch in contrast to that is for online training and serving. So we have the observations coming into the model, and then you're making a prediction with those observations, and you're also updating the model. So an example of this that is fairly common is using some of the unsupervised methods. One of those, which is anomaly detection, various different anomaly detection algorithms where you can update the model incrementally. So today, though, we are going to focus on the feature side of real-time machine learning, and how you can create real-time feature pipelines with BiteWax. Before we do that, I would like to divert a little bit just to talk about streaming data and how we can process streaming data. So we'll build a little pipeline to analyze a stream of data. I'm going to play a little video here. I hope it is easily viewable on your screens. Okay, so streaming data is all around us. I think the best way to kind of think about this, if you're a Python developer, is it's kind of like an infinite generator. And so that's what I'm like, what I was typing up in this video here. So we've created a little generator, and then the consumer or the downstream system will request if there is new information available in kind of a recurring polling manner. And so that in this video is us saying next. So you can think of the stream of data being the generator, and then the processor downstream is saying, hey, next, 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 and then it's changing that data for whatever purpose that that you require. Okay, so the unbounded nature, which we were alluding to with that infinite Python generator, can really feel quite daunting. And in order to manage processing this data, we often use unique processing tools to chunk up or batch our data, or to maintain a memory of what has happened in the past. And the tools we use to do this fall into the realm of stream processors, and they're either referred to as stateful or stateless stream processors. The stateful ones are the ones that can retain stuff in memory, and one of which is ByteWax. Other tools you might be familiar with or heard of that can do this is Spark with their structured streaming part of the project, and then Flink and Beam are another common open source tools to do this. So all of these tools give us some semantics to connect to streaming data sources and process them in windows or micro batches to join different data streams together, filter it, enrich it, and then write it out to a sink, which in the real-time feature pipelines will be the feature store. So to illustrate what we're talking about with streaming data and this idea of like continually asking for if there's new data available and then processing it as a stream, we're going to I'm going to show a little code snippet that basically pulls Hacker News API for everyone's favorite news source, Hacker News. It continually polls Hacker News for new updates and then processes them in a streaming manner. We're going to do a little stateful operation here where we're going to count the number of comments on a story and update that incrementally, and then we'll just print it out to the terminal. Okay, so I have another little video here, so we'll run this and give it a second to get going. So ByteWax is a Python framework with a Rust processing engine, but you don't really touch the Rust processing engine much. So what you see here is just Python code. It's nothing too fancy. The framework provides a lower level API that we've used here to build our custom input source where we're pulling Hacker News. And then we've also parameterized this data flow. So we can pass it an initial ID. So let's say that we had to go back in time and start from a certain period. We could find out what that story ID is. We can start from there and pass that through to our input. So in this data flow, we're setting a periodic input. So we're polling. I'm just going to take a quick pause here. So most clients that connect to streaming data sources, whether it's Kafka or Redpanda or a WebSocket, they're generally polling and asking if there's new data available. So we've just kind of slowed this down. And in this instance, oh no, that's the wrong button here. Let me get to the right spot. Apologies. Okay, I won't be pausing it anymore. So every 15 seconds, we're going to call this, or ByteWax is going to call this input next item function that we'll show here in a second. And so we're just kind of like polling and saying, hey, do you have any new updates? Do you have any new updates? And we've kept in memory the max ID of the last time, and we'll just find the IDs between those and send them downstream, redistribute them. So in the case of multiple workers, we can split them out, and then we'll process those individually as a stream of data. In this code, what we're doing is we're finding the root ID. So we might get a common ID and we have to traverse up the thing and get the parent ID. So we can do that with a map operator. The map operators are the operators are essentially the tools you can use to kind of control the flow of data throughout. You can think of each step as like a node in a graph. So in this case, we have our input that brings us many IDs, and then we flat map those, that's the operator. So we split them out and we process them one at a time. We've redistributed them again across workers. Then we've retrieved metadata. Then we've traversed back up this graph of comments, grabbed the key parent ID, and then we're using a stateful map where we have a builder function and a mapper function, which in essence is like, every time I see a story ID for the first time, I'm going to do that build ID, which is make a story object. And then every additional time I see it, I'm going to update the count. And that's that mapper part. So I've left some print statements in those, so you can see when the story is created, and then the comment is updated. And then finally in this, we're outputting to the terminal downstream, we're outputting that count of comments. Okay, so that was all really cool, right? But what happens if the server room goes on fire and the whole thing collapses? Or if you want to do something more complicated, like many different types of windows or many different things in addition to what we showed there, which was just a simple comment count, it could be quite untenable, or you might end up with the wrong calculation. So what is generally advertised as a best practice, which we'll show next before we create our actual feature pipelines, is to split out. So in our streaming application, we had getting the raw data, doing some stuff with the raw data, and then doing this like stateful calculation and then printing it out. And it was all in one application. So the recommended best practice is to sort of split that out with something like Kafka or Redpanda in between. And the reason you want to do that is it writes to more durable storage layer and is backed up. And so if our worker or if our server room, like in this this graphic here, really actually goes on fire and our data flows go down, we can recover them and replay them from the correct offset and not lose any data for our feature pipelines downstream. So here's an update to our previous diagram of splitting out our calculations. So we've added some complexity to the overall amount of infrastructure that you have to manage. And that in this case is Redpanda, which is a Kafka API compatible streaming platform. You can think of the streaming platform as like the transport/storage layer for streaming data. So you can send the data through, but it also maintains some of what you've sent through at a durable level that you can replay it. So anyway, so we split this thing out. We've added a little bit of complexity, and the trade-off we're making for that complexity is we're able to do two things. One, have some more resiliency. The most common place our data flow might fail is in that calculations, those comment calculations, or the more sophisticated calculations. They may fail because we run out of, maybe it gets really big and we run out of memory, have to move it to a different machine, or maybe the data somewhat shifted and you have like some failure because a field changed or whatever it might be. So we have some resilience there. The other benefit is that we can have many consumers of the data we put in Redpanda without hitting the API many, many times. So we've saved ourselves the requirement of like overloading that single API to have many of these downstream pipelines. So moving on from here, we're ready to make some feature pipelines. So the first, you can think of what I've done so far as like, okay, let's get some data we're going to be using for making predictions. All of this is a little bit, you have to use your imagination because the feature is not really used and there's not a model downstream. But so we have pulled some raw data that we thought we could use to make some interesting predictions with the model. We've now created a pipeline to do something like that, to create one feature, which is probably not the right feature, but is count comments. And now we're going to split these things out so we can have more of a production ready system, and then we can have many feature pipelines. So once more, we're going to have a little video that I'll try to talk through. So we're going to modify our previous example that you already saw to write the data out to fit into that architecture. So we're going to use Red Panda as the input, and as the streaming platform, and we already have that running in the background in this instance. So what we need to do to connect to Red Panda is we can use the Bytewax Kafka connector. So we'll replace the Kafka output, or sorry, the standard output where we're writing to the terminal. We're now writing to Red Panda. The reason it says Kafka output is because it's Kafka API compatible. So it's one works for both. So we replace that output step in the flow. And now there's a couple more things that we're going to do after we replace that output step. One of which is we don't need our stateful map count comments anymore. We're going to put that in a separate feature pipeline that's going to be taking input from Hacker News raw. So we can remove that from our code, and we'll remove the corresponding story class that we made and the update count. And what we're going to do and what we're going to replace that with is a serialization step. Red Panda requires that our data comes in as byte string. The topic requires it comes in a byte string, so we just need to serialize our data into a byte string and then pass it through. So we'll JSON serialize it and then into bytes, and then we can send it through, or it will work sending it through that Kafka or the Red Panda output. So here you see me in the console UI, create the topic, Hacker News raw. We'll skip over the details of what the topics are and partitions and everything like that. So we have our topic. Now we can start writing data to it. So we run our Hacker News flow, and when we find out there's an update, we shove that into Red Panda. And in the Red Panda UI, you can do some cool stuff, like you can see the data. So we could leave this thing running, and yay. Now we can move on to the next part, which is how can we create these feature pipelines from Red Panda. So that's also a nice little video here. Our data flow has been chugging along nicely in the background, and we have a bunch of stories and comments in this Red Panda topic. And now we're ready to write some features against this to first do what we were previously doing, which was count comments. So luckily, Bytewax has a nice Kafka input adapter or connector that can be used with Red Panda. So here we can add it in place of when we had the Hacker News input that we built, where we built that custom class. Here we're just going to use one out of the box. And then we're going to take that stateful map code that we used before, and we're going to throw it in here as well. And then we can use that to count our comments. And now we're going to put it back into Red Panda. And before we do that, we'll serialize the data again. So we deserialized, counted, and then we serialized it and wrote it back to Red Panda. Let's skip ahead here. I went a little bit maybe too quickly here. So let me explain what's going on quickly, and then so we added an input in our data flow code that you can see up above here. We added the Red Panda input. So now we're consuming, instead of consuming from the custom class that we wrote, which was polling an HTTP endpoint, we're consuming from Red Panda, and then we're deserializing that data because we serialized it on the other side. Now we do our stateful map, which is counting comments. So we create a story object and then update that story object with the count of comments. And then we now we end up with data in the format of story and the count of comments. We serialize that once more so that we can into a byte string, so we can send that to Red Panda, and we're sending it to a new feature called HN feature 1. We've run this thing in the video already. It started from the beginning of the Kafka topic and has crunched through all the data. We have a logging step in here, so it's logging some of these comments along the way. I think I recorded this 2 days ago or something. So there's probably, I don't know, maybe there's something here, something about Meta headsets. And then we can go back to the UI. Oh, well, what I wanted to show, which is I mispressed here. You go back to the UI and you can see the story and the running count of comments, which is going up and up and up. So that's that. Someone else today has already showed how you can plug these sort of things into the HopsWorks feature store, but that would be our next step. Say we actually had a feature that we wanted to use with our model, and we were going to predict the, I don't know, trending hacker news or something. We could do that with HopsWorks. There's a tutorial on it that has BiteWax in the HopsWorks tutorial repo. But basically you would tell HopsWorks what the schema was and what the define that feature, and then you can kind of point it to the Kafka topic. So that was a lot, and it was pretty fast, but I managed to make it in the time with no time for questions. If you want to check out the code, you can find it on my GitHub, AW Maths and Guide Periodic Note News, and it will be a guide shortly on our website because I'll make it a guide there, and then you can find us at BiteWax/BiteWax. Yeah, thank you, everyone.
Brilliant. Thanks, Sanders. Thanks, and great to see code and that data scientists can actually realize the dream of building real-time machine learning in Python.
Yeah.
So I'm really looking forward to see what you guys do in the future. Thanks. We're going to move on, and so as Sanders mentioned, we're out of time for questions. You can write questions to him on the Slack, and hopefully Sanders will jump in and answer there. We're going to move on to Dagworks, and we have a talk by Elijah Ben-Izzi. Hi, Elijah. Are you there? I'll read your bio. Great. So Elijah Ben-Izzi, he built large components of the simulation trading infrastructure to Sigma, where he led a team to test and ensure the reliability of the simulations. And then he built out the ML platform at Stitch Fix that was used by over 100 data scientists. And most recently, he co-authored the open source library Hamilton, which is a general purpose lightweight framework for building data flows in Python. And due to that success, he left his job at Stitch Fix, started Dagworks, and Dagworks' goal is really to make it easy for data scientists to build and manage machine learning pipelines. Looking forward to this. Elijah, big fan of Hamilton as well. And the stage is yours.
Awesome. Thank you so much, Jim. I'm having trouble sharing my starting video. So, but I can start. Oh, there we go. Start my video. All right.
Oh, we see you. Great.
And so I exist, and I'm going to share my screen so you can see what I'm actually talking about.
There we go.
I want to go ahead and say that everything is good. So first of all, yeah, thank you so much for the introduction. I really appreciate it. Super excited that Xander went before me. I think I'm going to talk a little bit about streaming in my talk, and they can integrate with a bunch of different platforms. BiteWax could totally be one of them. Yeah, so hey folks, name is Elijah. Jim introduced me, but I'm going to be talking about something I'm really excited about, which is the open source library Hamilton, and how you can use it to build out feature engineering capabilities. Specifically, how you can use it to write your features once and run them everywhere in different contexts. So today, what do I want you to come home with? I want to convince you that 1, writing portable feature engineering code is hard. 2, state-of-the-art approaches aren't flexible and powerful enough. I put a little spicy emoji by this because you're hearing about a lot of interesting state-of-the-art approaches, and I think they're all amazing. I want to offer sort of a slight alternative or a very different way of thinking about it. Hamilton can help you write code to run in multiple contexts and keep your code organized and clean. And Hamilton is easy to get started with and easy to use. So first, a little bit about Dagworks. We're aiming to build the unifying layer for data, ML, and LLM pipelines. It's all open core, so we have a paid product, but that's not what I'm talking about today. I'm not selling anything. I'm going to be talking about Hamilton. Everything here is free to download and use and all open source. So you can install it on PyPy, on Conda as well. Easy to get started. You've got documentation. I'll give the links later. And you can try it out at tryhamilton.dev. This is a website that uses Pyodide to have a sort of interactive Python experience in your browser. You can explore Hamilton, run through a few examples and sort of learn the basic concepts. So on the agenda today, first, I want to talk about the problem or the challenges with feature engineering. Then I want to talk about the solution we came up with, Hamilton. Next, I want to talk about how you can use Hamilton to write your features once, and run them everywhere. I'm going to apply this towards batch and streaming mode. And then I'm going to talk a little about additional benefits of Hamilton, what having a Hamiltonian code base does and how it sort of can help you. And finally, talk about some open source progress and community updates. So what are the challenges with feature engineering? Well, I want to look at a common scenario that's based off of something that I saw at a previous role in e-commerce, but I think is generally fairly widely applicable. So customers will fill out survey results when they're signing up, when they have something they want to tell you. Your model makes predictions, and the goal is to get the survey results, featureize them, and send them to the model so you can make accurate predictions. What are the caveats here? Well, you've got streaming survey results trickling in. As you just learned, the infrastructure for that can be fairly nuanced and complicated. Data comes in dumps nightly, so there's batch data to handle. Multiple teams are working together to do this if you're at a bigger company. So you've got your feature teams, your infrastructure teams, and your data teams. And features are derived from other features that are derived from data, right? So it's functions of functions of functions of your raw data. So visually, this looks something like this. You've got your customer surveys coming in, you've got your batch data coming in, and you've got your live browsing data coming in. You put them through these feature transformations, which I'm going to break into map, aggregation, and joins and queries as sort of the standard shape. And then you want to do model training or inference, right? We're going to be focusing mostly on feature transformations with a little touch of inference during this talk. So the context you'll want to run this in to actually make it clear, you could want to run it in batch on tables in your data warehouse for training data, run inside a streaming processor such as Bytewax, or Bytewax to organize it all, or Kafka as a processor for near real time, and transform browsing data live. We're not going to focus on that one, but it's sort of natural to extend this to true online versus streaming contexts. And complications. You want to ensure that the data is the same in all contexts so that you don't get a difference between your training and your production serving context. So how do you handle joins or alternative data sources in non-batch mode? And how do you include aggregations in streaming mode? These are all sort of fairly complicated things. And how do you track lineage, versions, et cetera, for different data sources, right? These are the things you have to think about when you're having a feature pipeline that's run in multiple different contexts. So back to that spicy point I made at the beginning, I want to argue that the current approaches kind of fall into two different sides of a spectrum, right? So on the one side, there's context-specific execution. And what this looks like is you write batch code and you write streaming code. These are two separate pieces. And they, so two separate ways of doing it. And you, the first one, you have as much power to do each one in whatever way you want, but it can be cumbersome to manage, right? You have two separate ways of writing code. You have two sets of versions, and the big question is, do they match, right? On the other side of the spectrum, you've got a single feature DSL to unify. So you got to learn a new way of doing things. It can sort of be opinionated about how you do these aggregations and how you do these joins and make it very powerful. And I think these are sort of really interesting and fascinating, but it can be tougher to grok, limited to specific operations, and highly opinionated on how you do aggregations and joins, which often I find are as much an infrastructure question as they are a modeling question. So I want to propose something kind of right in the middle. And the idea is, can we write normal Python code that is dry, meaning you don't repeat yourself, applicable in all settings, so you can reuse pretty much all the same code, fully customizable. You decide how to do joins differently, you decide how your aggregation approach, you write map functions however you want, and you bring all your own infrastructure, and that are self-documenting and imply structure, meaning it's really easy to figure out exactly how the what is happening in your feature code just by looking at the code. So I'm going to talk about how Hamilton is the solution we came up with here to solve this problem, and it comes from a very simple concept. So the idea is, what if every feature corresponded to exactly one Python function? And what if the way that function was written told you everything you needed to know about how that function worked? So in Hamilton, the artifact, feature in this case, is determined by the name of the function, and the dependencies are determined by its parameters. So if you've ever seen PyTest, it's kind of taking that idea of fixtures and adding type safety and sort of taking it to the extreme. And what does this look like? Well, just to be clear, Hamilton supports all Python objects and any sort of data frame library. It started with Pandas, so I'm going to kind of use that because it's something everybody knows. But really replace it with Polars, PySpark, et cetera. There are different certain nuances, but it'll all kind of work the same. And you can have Python objects, whatever you want to pass between. It's just Python functions. So instead of writing operations on a data frame like you would here, DFC equals DFA plus DFB, DFD equals transform of DFC, you declare your your features as functions and write them out individually. So as I said, the output corresponds to the function name. So this is creating two features, one called C and one called D. And D depends on C, and C depends on A and B, which aren't defined here. So they could be something from the outside world, or they could be another upstream feature. So to tie this all together, what do you actually need to run it? Well, this is a full hello world. You've got your functions, each of which defines a feature. And then you've got a driver to say what and when to execute, right? So all the driver does is import your modules, load it up, and then execute, pass in some input data. You can think about the driver, the functions is setting up delayed execution. The driver is interpreting that and actually running it. So to sum it all up, for each transform, you write a function. Functions declare a DAG, which is a directed acyclic graph. If you're not familiar, it's just a way of saying like, run this, use this data to run that, use this data to run that, etc. It looks like a flowchart. And Hamilton handles this DAG execution using your driver. And it's as simple as that. So you're probably asking, doesn't Hamilton make your code more verbose? You have to write now functions instead of individual lines sort of operating on the same data frame. I want to say yes, but that's not always a bad thing. And in most cases, that's probably a good thing if you do it right. But when it is a bad thing, we have decorators. So these decorators you can think about as sort of macro DAG operations that enable you to sort of change the shape of your DAG and make it a little more concise. There's a bunch of them, and this is there's sort of a whole algebra here. But the one you need to know about for this talk is called config.when, which allows you to use a static configuration parameter to choose between different implementations of the same sort of node or function. So now let's talk about how you can use it to write once and run everywhere. And the basic premise here is that we're going to have one, and this is where I a little bit led you on. It's not just one creature per function. For most functions, you're going to have just one, and you can share the vast majority of the code. But using that config.when, we're going to allow you to swap out implementations to choose exactly how to work, right? So I should have probably had an asterisk by write once, run everywhere, but I kind of like, I think this really is like a good way to do it because it allows just the flexibility and power for the more complicated operations, and everything else, you can run the same stuff. So with map operations, we're going to treat single versus bulk operations to be equivalent. Oftentimes, even the single online operations, you're going to want to be running in small batches. So, and you run vectorized. Aggregations, you're going to choose, do you store your aggregation, compute it on the fly, update regularly, etc. For joins, you can use we're going to use a query instead of a join, although there are other ways to do it depending on the data size. And again, for aggregations joins, you're going to implement just the small pieces that differ between them. So back to our scenario, remember e-commerce survey data coming in. We've got a set of simple map operations. Say you have a raw survey data where the customer inputs their budget, gender, and age, just sort of spitballing here. Derived features is their budget high? Are they a high roller? Is male, is female? Joins, you've got the time since the last login, which is a function of sort of the client ID and the login data. And aggregations, we're going to normalize the age. These features are kind of just made up, but the shape of this isn't too far from something that I've seen in real life and that you've probably encountered. All right, so what does this look like in batch? We're going to go over a full sort of working example of code and show how the DAG changes along the way. But first, this setting here. So the goal is to compute features and infer the model in batch, right? So we're going to do feature calculation and then model inference. Kind of if you were doing like a snapshot thing, it's pretty trivial to think about how you replace it with the actual training piece. And the context, we've got a database with raw survey results, another database with client login data, so we can get that information. Say the model is already trained. Again, I said you can use this for training, but we have a model object that we can access. And the data is of a reasonable size. That's just because I'm going to be using pandas, but Hamilton can work with any data frame library and has sort of tools to help you scale up pandas even. So what does data loading look like? Well, we actually do have some specific data loading adapters and decorators, but for now, we're going to do some very simple code, create a connection, load from SQL, and then we're going to have 4 columns here, 3 of which are features we cared about, budget, age, and gender. And the last is client ID, which forms the spine, right? So this is just a single node to start loading your data. And this produces a DAG that looks like this, right? We've got our survey results database and table. Those are strings coming in from the user. Then we get survey results and we split it out into separate columns. So now let's do the map functions, which are derived features on top of our features that we just extracted raw. Let's say we want to get is male, is female, is high roller. These are sort of very simple implementations. You can imagine these getting more complicated. One of the nice things about Hamilton is it's separated, each one of these is separated into a specific place. So if you want to change it, if you want to sort of understand exactly what's happening, that's fairly easy to do. Now that we've added these, you can see we've got 3 more nodes, is male, is female, and is high roller. And we're starting to build out our DAG. And the point I want to make is one of the cool things about Hamilton is you can sort of take these DAGs and add extra pieces to it and start building it iteratively and composing it to turn from a simple data loader into a more complex data pipeline. Now, what are our joins going to look like? Well, we're going to do a join in memory, but you can easily do a join in your warehouse if you want. So this is loading your client login data, getting the last logged in, which is a merge there, and then a time since last login. Pretty simple, which is just a subtraction. It's a map operation. And you can see we've added another section to our DAG, getting another feature that we're going to want to use in our model. Aggregations. We're going to do the same thing that I talked about earlier, where you're not using necessarily Pandas series, but you're using Python objects, taking a series and turning it into a float. So to get mean, standard deviation, and then normalize it, which is just a map operation. And finally, we've got that added to our DAG, and we have got all our features. So we've got aggregations, join, and map operations. And finally, we want to do inference. In this case, I've just defined model data to make it very explicit what the model is taking in. There are other ways to sort of join these series that you can use in Hamilton. This is just a way to make it very clear. And predictions, which take in a model that you pass in from the outside world, as well as the model data, and run your prediction. So you've got predictions on top of your inference, and this is the entire batch DAG. To put it all together, here's what the driver looks like. This would be in your etl.py script. Say you're running an Airflow or wherever. You would import your features, run it, and pass in just the inputs you want based off of sort of your setting. Simple enough, easy to run. All right, so what does this look like in the streaming mode, and what specifically do we have to change? Well, let's set up a context first so we know what we need to build. You see you have a service to give you client login data. You've stored aggregations from training. So we have those means and standard deviation, and your goal is to be near real time, so to predict as soon as raw data is available. What are the changes that are required? Well, we have no aggregations available, right? So we have the stored aggregations training, we'll use that. We want to swap out an external join with an API call. So say we have a service, as I said, to give us the client login data. We're going to be using single datums, not data frames. We kind of treat them the same here. I found that in most cases, the performance hit of using single items versus vectorized stuff is almost negligible. But there are ways to sort of vectorize in Hamilton too, if you want. So we're going to be using this decorator config.when to swap out the features you need to change. There are 4 different things here. So note we've got 4 things that are different versus like 20 or 30 features that we've defined overall. And this is loading in the survey results, loading in the last log data, and loading your scalars here. Note that we have this sort of double underscore thing after the feature name. All this means is Hamilton's going to chop it off, and it's kind of a clever way of defining 2 features that point to the same thing in the same file, right? And we're doing config.when mode equals streaming to say, oh, in streaming mode, we're going to do it this way versus in batch mode, we're going to do it another way. And what does this look like? Well, the DAG is actually simpler because we're loading data from external sources, so there's more complexity pushed outside. But comparing it to the other one, we've got the joins, the maps, and the aggregations. We've got the data loaders I've highlighted, the joins and the aggregations that are different between them. The maps are all the same, as are most of the sort of pieces within those in the glue. So what does the driver look like? This is kind of like generic streaming stuff, taking a list of records, output a list of predictions, probably a list of records. In this case, I just made a list of floats. Set up your configuration, instantiate your driver, and process your records, which all it does is set your inputs from the records and execute it, right? So we've got a feature pipeline that works in batch or streaming, and most of it is exactly the same. And you know everything that's different. So it should be pretty clear to figure out what's going on and figure out what the corresponding batch operation and streaming operation is. All right. So Hamilton gives you portable feature engineering code, but also gives you a host of other benefits. So because it lets you write these Python transformations as simple, or these transformations as simple Python functions, they provide everything you need to know. So unit testing is really easy. They're all just plain old Python functions. You can unit test individual pieces or unit test an entire path. For documentation, all you need to do is use the Python docstring. For modularity, you naturally have it broken into small pieces, and the small pieces are organized into modules, so it makes modularity really easy. Your code naturally forms a central feature definition store. So it's not a data catalog per se, but it's a very valuable thing to know exactly where your data is coming from. And you can sort of visualize the DAG as well. Debugging, you can execute functions individually and set breakpoints, even pass in mock data fairly easily. And for trustworthy data, to make sure your data is trustworthy, we have validation included out of the box. So we have all sorts of cool validators, including a Pandera integration that's built into Hamilton. Right. So how does this integrate with feature stores? Because we're at the Feature Store Summit. Hamilton is kind of the transform layer. It actually works in basically anything that runs Python. So HopsWorks, Feast, Tekton can be the storage and sort of moving around stuff layer. And we actually have a blog post of Feast integration here that I'm really excited about that shows a few different ways to use Hamilton to make it easier to manage Feast features and manage Feast constructs. All right. So taking a step back, it's not just applicable towards feature engineering, although that was sort of the bread and butter and how it started, but it can improve code wherever Python and data are involved. So for LLM pipelines, we've got users online writing retrieval augmented generation and fine tuning. For ML training pipelines, a lot of people writing sort of training pipelines. You can see that's not actually that different from what we showed you earlier. And for sort of general data engineering pipelines, we've got all sorts of integrations with Pandas, PySparks, Polars, et cetera. And it's pretty complementary with most existing infrastructure. It's really a way of organizing your code and doesn't really care about how you run it. So if you've got Airflow, DBT, Prefect, Dagster, et cetera, it's sort of complementary with that. It kind of is a different way of doing chains in the LangChain, although you can use them together nicely if you want. PySpark, it's complementary. We have a whole blog post and a whole integration about using PySpark. With Kedro, it's sort of complementary to the structure, if you like the way that Kedro is organized, and replaces the sort of way that Kedro builds DAGs. For Ray and Dask, it's very complementary, and the goal is for it to up-level your sort of software engineering skills, so that you're thinking less about infrastructure and logic at the same time and can sort of separate them out. Right. Finally, a note on open source progress and updates. We've got a thriving community. This is we have about 110,000 plus downloads. These are a bunch of users that we know from just having chatted with them. There's a whole host more that we don't know and others that we sort of talked to, but they're all using it for sort of critical models in production. We have a growing set of core contributors, a full company dedicated to building it. That's us. We're looking for contributors. So we have a whole Hacktoberfest thing going on. We've gotten a bunch of engineers who've wanted to really sort of like start contributing to open source and a bunch of tickets that are easy to get started with. We're looking for bug hunters and user feedback. Nothing better than the more people telling us problems and things they like about our code, the better we can make it. All right, in progress, we're working on more expressive APIs, so flexible loading and materialization. I didn't show it here, but we have all sorts of ways to decouple the loading of the code from the actual transformations and saving of your data. New higher power decorators is really exciting, ways to sort of perform macros and make it extremely expressive. And we're always listening to new ideas. For the execution side, we're thinking of building out the ability to compile a Hamilton code to, say, Airflow. So you write your code in Hamilton, which is easy to think about, press a button and it gets compiled down to the right Airflow DAG. Snowpark integration and a whole host of ideas. We've had a bunch of good user interaction here from open source. So give Hamilton a try. We'd love your feedback. Try hamilton.dev, easiest way to get started. You can install it on PyPy. Please give us a star on GitHub. If you like it, we really love knowing that people are sort of like what we're working on. You can create and vote on issues on GitHub, join us on Slack, and for those later, there's a link to a blog post that goes through this talk and code to play with. So you can download all of this and get started and sort of adapt it to your case. All right, so thank you so much. I really appreciate your time. Really excited to be here among everybody, really interesting talks. Here's links if you want to like yell at me online, QR code to the GitHub repo. Thank you so much.
That's brilliant. Thank you, Elijah. And it's great to see an in-depth discussion of some of the capabilities of Hamilton. One of the things, we have a little time for a question or two. One of the things I really like about Hamilton is that particularly with new data scientists who maybe are used to writing notebooks and they don't, factor their code out in their transformations into separate functions, is that we can easily introduce unit testing and pilot testing. You didn't go into too much details about that, but you think it's more important as an enabling technology, or where do you see the testing come into it as well with Hamilton?
So we have a blog post coming out soon about testing that I'm really excited about. I think it's really important. I think that you can easily get into the testing too much thing or testing too little. It's either you're not doing it at all and then you start testing all the things you don't need. think Hamilton can help you sort of identify critical flows and then separate out the logic from the sort of glue code behind it. So I think the hardest part in testing is how do you mock? What do you mock? How do you like handle external services? So that's where I think it's really enables people to get started with that. It sort of offers a whole new way of thinking about it and can make it easier.
Brilliant. And I guess another area where we often see in feature stores being used, and it's the flip side of feature engineering, is batch inference.
Yep.
So I could see a very good role for Hamilton for writing batch inference applications where you're taking your data pre-computed from the feature store, but maybe you've got model dependent transformations and so on. Have you looked at that area for Hamilton much?
Oh yeah, I mean that was one of the original use cases, doing batch inference. But I think we kind of talked over that a bit in the talk, and right, it allows you to take sort of the smaller mini batch stuff that you might run in streaming and then apply that. And there's a really cool thing that we did with Spark in case you want to scale up, where you can sort of run your map operations in pandas as UDFs on Spark, and then handle Spark operations, sort of keep stuff similar between different contexts.
Brilliant. Thanks a million, Elijah. And with the mention of Spark, I think we'll move on to the company behind Spark, Databricks. Elijah, you'll be on Slack. I hope if there's any questions, we can get them on Slack.
I'll be answering questions.
Okay.
Thank you so much. Really appreciate it, Jim.
Brilliant. So without any further ado, we'll move on to the last talk in this session. It's Databricks. We've had Databricks talking before at this Feature Store Summit, so we're delighted to have you back again. We have two speakers. We have firstly Akrati Talati, and she is an ML AI engineer working on building the feature store for the ML platform at Databricks. Prior to Databricks, she worked on distributed systems and ML infrastructure at Google. She has a master's in CS and is passionate about encouraging women to pursue careers in tech, which I think we all can agree with. And we also, joining her, we have Mingyang Ge, and he is an ML AI engineer working on building the feature store for the ML platform at Databricks. Before Databricks, he worked on conversational platform at Google Assistant. Delighted to have you, and let's see if we can get the screen sharing going.
Awesome. Thanks, Jim. As Jim said, like, my name is Akriti, and I'm the tech lead for feature serving at Databricks.
Hi everyone, my name is Mingyang, and I'm a software engineer working on feature store at Databricks.
And we are here today to talk about how Databricks feature and function serving can deliver personalized context for LLMs. LLMs are all the talk now, so let's get started on that. We are very excited for the agenda today to share with all of you. First, we want to discuss like how traditional hotel booking websites are built. We are just taking like an example of hotel booking since it's easy to follow for us. And then the next, we'll talk about how we can transition the website to an LLM chatbot. We'll then share like current shortcomings of an out-of-box chatbot and how structured enterprise data can fulfill those gaps. And finally, my colleague will take you through the demo of how Databricks feature and function serving powers the LLM chatbot. And we'll close off the talk by diving into conclusions and any questions you may have for us. Okay, so let's start with how a traditional hotel booking website works. For this website, like typically it's built on top of a mobile or web application that takes in user city of interest and booking dates. It then performs a personalized search and some ML-based ranking of the search results for the logged in user. It is pretty good, but it cannot capture the user's intent as well as an LLM can. And in order to capture the user intent better and to provide an intuitive user interface, we probably want to build this website with a conversational bot that can help with these. So let's take a look at how to build personalized chatbot for hotel booking website by using a large language model. And we'll see how leveraging the enterprise data that we all know very well about, like, can make the LLM chatbot even better with personalized context. So before we dive into that, like, I want to take an example of what the interaction with out-of-box chatbot without personalized context would look like. And for that, I'm using an out-of-box conversational model from OpenAI. And I asked the chatbot to create a 7-day vacation plan for a user on my website. They wanted to travel to Amalfi Coast in September. So here's what it responded with. It said, sure, I can help. However, I'm an AI language model and I don't have access to your personal information. And it suggested me to contact the travel agency or use a travel booking website. So without any fine tuning or additional context, it understands really well that I'm planning a vacation. It also understands that I need to book flights and accommodation. But what does it not know? It doesn't know anything about the user, like what kind of vacation they generally book, what is their typical budget, what type of accommodations they prefer. But we are all feature store enthusiasts here, and we know exactly what enterprise feature data in any of the feature store has. So let's take example of Databricks here. Databricks already has like all this enterprise data that I need to power my LLM. And I can use the feature and function serving functionality to serve business data and functions at a low latency in a real-time environment. And all I need to do is store the enterprise data and serve it using one of the serving solutions. So let's see how we can get this information from Databricks. Let me define first, like I am going to be using Lakehouse and Unity Catalog. So a Lakehouse is primarily like a combination of a data lake and a warehouse to power different workflows such as business intelligence, analytics, machine learning. And Unity Catalog is a catalog for governance of the data. So Databricks lets me use the entire Lakehouse as the feature store. What I would do is in Unity Catalog, any Delta table that has a primary key can be used as a feature table. We'll see that later in the demo as well. And also Unity Catalog makes it possible to access the data from all of my workspaces, whether they be staging, dev, or production environments. And Unity Catalog allows me to specify permissions for all of my data. So this hugely simplifies the governance model for the data. And I can see all the lineage upstream and downstream for the data and the code that I have. So now that we have the data in one place, let's see how we can access it in real time at low latency. So for that, I'm going to use Databricks feature and function serving today, which supports real-time and low latency serving of data and real-time calculation of any on-demand features. It supports running arbitrary Python functions for calculating real-time features or context features. And it lets me do arbitrary function chaining. Real-time feature serving solution hugely increases the contextual understanding for better chatbots. Let's see how I can power the chatbot with the context data from feature and function serving that we just talked about. So bringing everything together, my users' feature data and hotel data along with the custom code to calculate discounts is part of Unity Catalog. I use feature and function serving to query the data at low latency. Next, I built some tools for LangChain. I'm going to be using LangChain here today to call the feature and function serving to fetch that data and embed it into the prompt to provide personalized context. And finally, all of this gets built into the chatbot that knows when to query which data. So let's see what that LLM workflow would look like here. When I ask the user, when the user asks the AI bot to create a travel plan for them, the chatbot will ask first, like, what do I know about the user? So here chatbot will query feature serving to find users' budget or other preferences. For example, like how many people does the user generally travel with and what are their personal preferences? Next, it will ask like, what are the best hotels based on users' personal preferences? And for that, it will do a top case search using vector search tooling for hotels based on users' budget and other preferences. Then it will calculate like what's the total amount for the trip. And for that, it will again use the feature serving to get the real-time availability and prices for the preferred hotels. From this, it calculates the total price, on demand using a custom function that I have defined in the Lakehouse. Then it calculates the final prices after doing some discounts based on the membership type. As you can see on the right, that Databricks allows me to do arbitrary function chaining for all the operations I need to calculate the final cost of the trip here. Okay, enough talk. So now let's see this in practice for the hotel booking website. And for that, I would like to invite Mingyang to do a demo.
Thank you, Arkady. Yeah, cool. So in today's demo, we will build oh, sorry, can we share my screen? Oh yeah, thank you. Yeah, so in today's demo, we'll be building a hotel recommendation app with context data enhanced LLM. Let's first have a look at the goal we want to achieve today in this demo. Let's say you have a conversational app and the user ask you to plan a 7-day vacation to Amalfi Coast around September for user ID, blah, blah, blah. For comparison, I copy over the response from the language models. I'm going to show you in a little bit. So for generic LLM assistant, it doesn't know anything about the user. Let's see what it does. Right? So it says, sure, I can help with you with a plan in September in Amalfi Coast, but it doesn't know anything about the user and it doesn't know anything about the hotel. So it asks for details. It's pretty smart, but it's not super helpful. So what happens if we enhance it with context data? With this enhanced version, it can say, based on your preference, here are some hotels available in Amalfi Coast for a 7-day trip. And it lists some available hotels with all the price calculated for a 7-day stay. Let's see how we can build this. Cool. This is a little recap of the diagram Arkady already showed you earlier. So besides the LangChain and LLM part, we simply have these 3 blocks to build to provide context data for the language model. In the first block, we have a table lookup that lookups the user preference by the ID. The second block is a vector search API to call to return some relevant hotels. And the third one is a little bit complicated. It has a table lookup. And after the lookup, it gets a value and it applies 2 functions to do some calculation. We all know language models are not super good at calculation. We have to do it with some help of the feature serving endpoint. In here, you can see all these table lookup and the functions are chained together. Yeah, in your application, you can arbitrarily train them in any way you want to have a DAG to fit in your custom logic. And all these tables and the functions are stored in unit catalog. So unit catalog is the one-stop storage that store every entities you have to build to train your model or build your application. Let's jump to the UI to have a quick look. So this is a catalog Explorer UI, and I have some tables already stored in my catalog. Any table, if they have already have a primary key, there will be a feature table already. This table have a user ID and some budget preference. And we're also going to use some functions in this example. For example, this one, you can see the custom logic is built into this function in Python. Okay, let's head back to the notebook and see how we build them, how we put them together. For the time constraint, I will skip all this setup and straight head to the language model. Okay, here, just to prove I'm not making things up myself. So this is a basic generic LLM model we are going to use. We are using OpenAI's chat like GPT 3.5 Turbo without any customization at the first version. We initialize the agent. Now we ask this question to plan a vacation at some time for a user. It says like, I can make the plan for you, but I don't know anything about you. Now let's enhance it with context data. So with the help with LangChain, we just need to extend this base tool and create this several tools to fetch context data. As mentioned before, we need to have 3 tools to query the 3 APIs. The first one is a user budget preference tool called the first serving endpoint. We give it a name and a description as a hint for the language model to use. And the business logic is pretty simple. It's basically HTTP request to the endpoint we create and host on Databricks. We give the user ID as the input, and the output will be the budget preference for the user. The second tool will be a vector search API call, which is pretty similar. It will return the relevant hotels for the user preference. And the third tool is also a call to the feature serving endpoint we create and host on Databricks. This time, the input will be the hotel ID and the days, number of days the user wants to stay. And the result will be the final price. So this serving endpoint will do all the feature lookup and function evaluation under the hood. Now we have all the building blocks ready. Let's put it together. So we basically list, put all these tools into a list and pass it into the agent. Then we give the agent a hint as a system message, just to describe how these tools can be used. You can see, we are saying, please use the budget preference from this trusty tool. And you can also use the hotel IDs and calculate the total price. Yeah, it's not code with natural language, but language model is able to understand it. Okay, cool. Now this AI bot is ready. Let's ask the same question. You can see the response is different now. The language model basically first query this first endpoint to get the user preference, and then it queries the vector search API to get the relevant hotels. And then it calls the third endpoint to do the extra lookup and the calculation, given our provided user-defined Python functions. Now, as a result, it lists all the available hotels and calculates all the price. It's pretty powerful, right? Cool. This is all I need to demo today. Heading back to you, Akrati.
Thanks, Mingyang. If we can switch to the presentation. All right. Yeah. Okay. Perfect. So thanks, Mingyang, for the great demo. We saw how structured data is critical to providing personalized context for LLMs and chatbots. We saw how feature engineering in Unity Catalog makes the entire lakehouse a feature store. Using feature engineering in UC for LLM chatbot helps govern the data presented to LLM, and it makes the lineage of the data and code available at my fingertips. Also, on top of that, using the feature and function serving helps seamlessly deliver personalized context from the Databricks Lakehouse at low latency and in real time. You can calculate any on-demand features using custom code with feature serving. And you can chain these custom functions together to provide real-time context for the chatbot. So essentially, all of the enterprise data powers the LLM to provide custom and real-time context that makes it much more powerful than an out-of-box LLM. Thank you for attending the session today. We are now ready to take your questions, and we'll be on the Slack channel after the talk if you want to talk to us.
Brilliant. Thanks very much, Kadi, and thanks very much, Mingyang. It's great to see a demo as well, right, to make it real. I think this is fascinating because this is obviously a very exciting area, personalized MLMs. And what you see in the community is a lot of interest in vector databases as a place to probabilistically search for data that will help enrich your prompt. But you're making the case that structured data and data from the lakehouse is as important or more important. How would you compare both of those as potential places for personalizing LLMs?
Yeah, that's a great question. There's a lot of interest for both structured and unstructured data, and I would basically say that structured data provides a very useful context to the LLM that is required, right? Like as we saw today, we needed unstructured search for basically like looking up, if you take the example that Mingyang had shared with us, we needed that to look up like the hotels, but there was a lot of data that is already available in the lakehouse that we could use to provide a lot of context information to the LLM that it would typically not have. And it also like helps us ensure that if I'm using like an out-of-box LLM from a third-party provider, I am very concerned about like governance and security of the data as well. And so like this ensures that we are not, we have full control of like what data gets shared in what manner here.
So we have a question on the chat here from Anders Berg, and he asks, what would be the format of the user preference in the example? How would you build it from your user interaction?
Great question. Mingyang, do you want to take this one?
Yeah. So in this demo, for the user preference, for simplicity, we only have the user budget preference, which is an estimate of the user, like how much they want to spend for a night. And this is a integer or double value in our lakehouse table, and it has the user ID as a primary key, and it can be used as a normal feature table that can be looked up.
Yeah, and to add on top of that, what we essentially like a couple of more examples you could think of is you might have like meal preferences for the user. Essentially like thinking about it in terms of like traditional MLOps, like it has a lot to offer when you transfer all of that knowledge to LLM ops, and thinking about it from that perspective, like number of people that travel with, number of the type of hotel that this person usually likes, like embeddings for those, all of this data can transfer over for your user preferences here. And to answer maybe your second question, which is about how can we build it from the user interaction. So that is the prompt engineering part that Mingyang had showed earlier in his demo, where you would customize like the description so that the tool is able to provide all of that information to the LLM chatbot, as well as the overall system description that you provide that helps build all of that information into it.
Cool. I have another question. We have another one on the chat, but I'll ask my own before I take that one. That one's already answered. So when we use the term prompt engineering, often we'll take the prompt and then we'll go to a vector database to try and find relevant documents. That's kind of the assumption, is that it's prompt and you're using the prompt only. But you showed that you can use the user ID. And in many websites, you're going to log in or you'll have an order number as a way of identifying the user. And I see that as the portal that opens up the enterprise data to integration into your prompt. So what should we call that? I would not call it prompt engineering. I would call it, session ID, user ID plus prompt engineering. I don't know.
That's a great question, Jim. Like, I think you bring it up like a very good point. Like, I think that's the whole point. That's why we wanted to bring this up conversation like here in this community and say that this is not, this is basically like integrating your structured data into the LLM. So providing it like as part of, and there is like more we can all like do together in this journey. And that's why like, I think this is more of like a tight integration of structured data, similar to how vector searches are like getting integrated into LLM, chatbot, QA bot, etc.
Brilliant. Okay. There may be more questions on the Slack, so jump over there. Thanks very much. We're going to take a little break. After the break, it's going to be a 6-minute break. We're going to have a bunch of great sessions lined up. We have Featureform, Fennel, Uber, FeatureByte, and H2O. So back in 6 minutes time. See you very soon. All right, welcome back. We are live. I'm delighted to welcome Simba Kadar. Simba is a real character in the field. He's been around for quite a while, and he is the founder and CEO of Featureform. He started his ML career in recommender systems. He architected a multimodal personalization engine that powered hundreds of millions of users' experience. He later open sourced and built a company around their feature store, and that's Featureform. It's the virtual feature store. It enables data scientists to define, manage, and serve model features using a Python API. Simba has also published, he's a published astrophysicist, an avid surfer, which I love, and he ran a marathon in basketball shoes, which is a little bit crazy, but that's Simba. Over to you, Simba.
Thanks for the intro. I'm gonna share my screen. Really excited to be here again this year. I assume you all can see this, or someone will yell at me that they can't.
Yeah, we're good.
Awesome. So yeah, feature stores, it's not just about storage. I would argue and have argued that feature stores, it's kind of this misnomer that we're kind of sort of stuck with, because it's a very hard thing to change the name of a category after it's been created. But I think that when people hear feature store, they think of a specialized database to store features. And I don't really think that's a problem to be solved. When most people think of feature stores, they think of something that looks like this. We call it a literal feature store. If you've ever used something like SageMaker or Databricks' feature store, it kind of has an architecture which sort of mimics this. Again, everyone does it a little differently, but I would say generally it looks like this. And how that looks like is you would take your data sets, you would transform them to build your features, and you treat your features as this kind of final artifact that goes into the feature store. And the value there is that all of your features are in one place. They can be served both in kind of OLAP style fashion for training and in transactional fashion of low latency for inference for models that are interactive, like a recommender system or a fraud detection system. The problem here, which I'll get into, is that the feature is treated as this final artifact. Like we're treating the feature as like a row of data, when in practice, the feature is almost always actually tied to the definition, this idea of the transformation. And if you don't tie the transformation to the feature, you end up in kind of this high friction area, because a lot of the value of features is the ability to, like the point of the feature store is to increase iteration time, or rather decrease iteration time, increase the number of iterations. And if you have to constantly switch back and forth, it causes a lot of pain. In practice, especially for a production feature, we have a set of features that are batch. We have a set of features that are streaming. And we have a set of features which can only be produced at request time, or on-demand features. These would be things like if you are doing fraud detection, you might take, or let's say actually you're doing something where you're checking a comment for hateful speech. There's some features you'd probably create off of the comment itself. That you can't pre-process that, right? Like that has to happen at request time. And that would be the case for on-demand features. There are a lot of features which, let's say they have like long window time, et cetera, which can be done via batch. And there's a set of features which really benefit from having near real-time, up-to-date, fresh features. So on the left side, these are features that can be pre-processed, and the kind of decision tree of whether to use streaming or batch is really how much does freshness impact the features or the model's performance, or that feature's performance towards the model. Great. So let's talk about the actual workflow of building features. A lot of people, when they think of feature stores, they think of kind of that production, like I built my feature, now I store it in the feature store. But again, lots of the point of building features is the kind of constant iteration of features. And this is actually what I see in practice. Even if you're using a feature store, you end up with something that looks like this. So let me break it down. There's this fence in the middle, which I so artfully put together. But I'll start with the top part, which is the experimentation piece, which is actually where most of the time is being spent, like where most of your time as a data scientist is being spent. In that world, you're working with a lot of notebooks. You are interacting with your infrastructure to build, or maybe even just working locally, to come up with signals that you feed into the model, the features. Some of them are interesting, some of them aren't. You may be interacting with a set of bash scripts, Airflow jobs, etc. But once you find something interesting, what I see in practice a lot is you actually have to throw that notebook or something over the fence to some other team that has to then go implement it. And no one's happy because oftentimes they screw up. And oftentimes they're like, what is this kind of garbage notebook that I've just received? I have to somehow like cross-write into Scala for our production pipeline. So this is where a lot of the friction comes from. And just having this kind of literal feature store, this place where you just store features, doesn't solve this. Because you still need to handle cases where you have streaming features. You still need to handle on-demand features, which doesn't really exist in the experimental function. It's almost like you're still having the problem of writing two different pipelines, and oftentimes even having two separate teams to handle building or coming up with features and getting those features in production. If you have dealt with this, then this might resonate. One of the big problems is that I think as MLOps practitioners, we really get caught up, I mean, just as engineers, I think. We like working on what I would call the data processing side of things. How do we do streaming faster? Like, how can we use whatever cutting edge new framework? We can use Rust to make this, 10% faster to handle however many exabytes of data. The thing is, though, that most of the problems that I see companies face is actually more of a workflow problem. How can we get end data scientists to work together to collaborate? How can we make it so that the workflow of getting a feature all the way from experimentation, ideation to production to be something that is very clean, has clear flow, has clear history, lineage, versioning, governance, monitoring, all the pieces that would be required. How can we get all of that to work together seamlessly? It's not necessarily that the problem is so much that, oh, Spark isn't fast enough. If only we had a better Spark, or if only we had a better Flink. It's really, how can we make all of these disparate pieces work together in a workflow that is coherent from end to end? It's a workflow problem. And I think most MLOps problems are, in practice, workflow problems and not infrastructure problems. And I think that we get too caught up with building new cutting edge infrastructure, and solving people problems is much tougher. It's really hard to come up with the right APIs and the right abstractions. And I think that for the feature store case, we've come to the wrong abstraction. And I think that it's kind of time to rethink what a feature store is. I know there was a talk earlier about the logical feature store. We call it the virtual feature store. And I think that is kind of the direction that as an ecosystem we need to move towards. These are things that traditional feature stores don't solve. Like, sure, you can go and you can write your feature to this new sync, which is a feature store. But think of all the things that you did on the way. Your untitled notebooks, your DF finals, your feature table V7 that's in Snowflake or wherever, even if it's in the feature store, it's still called feature table V7. You have these random scripts to trigger materializations, these ad hoc Spark submits, all these problems, and no documentation. It's not really built into the workflow because the feature itself is an artifact which is separate from how it was created. So even if you find a feature that may or may not be relevant, you don't really know what this thing is. how it was created, where it came from, how to rebuild it. You're kind of in this situation where technically your feature is now in production. You can train a model of it, you can serve for inference, but the workflow is just broken. Like it's just completely ad hoc. If these things, just a few more memes, I promise. If these things look familiar to you, then you likely are facing something that may or may not look like what I'm describing. This is not something or a set of problems that is unusual or something new. In fact, it's interesting if you kind of roll back time and look at the first feature stores that were built internally at companies. Companies like Uber. In my last company, we built a feature store. They would look like, we call it a physical feature store. Some people call it a feature platform. But the idea of tying the transformation to the storage is actually the more common paradigm that we see. Even in companies that have literal features, so like even if you look at like companies that have open source feature stores, it's actually only one team and the other team did the transformation piece. So internally, even though there's two separate pieces, it still looks like this. And the idea of this is now you're actually iterating on features as logic and not iterating as features as like this row of data that gets outputted after your pipeline. This really makes things better, especially when you're dealing with streaming features, real-time features, but just even in general, just the iteration, you get the lineage automatically, you get all of the stuff that you would expect, and the workflow becomes very clean. But there's another problem here. This works really well internally in the sense that if you have a team that builds this thing and maintains this thing, you can get away with rehousing all of your data on your own internal platform. However, as an external vendor, if you're looking at using an external vendor, like let's say I come to you and you, wherever company you're at, you're a larger company, let's say, and I say, hey, to use our feature store so that you get all this ability to define features, to manage features, to serve features, to do all the things you would expect, you need to actually move all of your data onto our infrastructure. And then you need to transform it via our infrastructure. And we kind of own everything end to end. It's a hard sell. Internally, if you're an internal team, you can do that. You get more buy-in because in the end, you own the thing. It's your code. As a vendor, it's a hard pill to swallow. And in practice, there's only so much value you get from doing this, right? Because your problem, it's the wrong puzzle piece. Your problem is not that, oh, we don't like Redis. Redis isn't fast enough, or we don't like Spark. We need something else. We need to build something that is completely new, a whole new type of Spark or a whole new type of Redis, which is better than what exists today. Some people may have this problem, but I would say that the majority of companies that use us that we talk to don't. It's not really what they're facing. Another kind of common thing that a lot of the feature store that I've seen talk about is making everything streaming. And I get it. Like theoretically, like streaming is a superset of batch. So like every batch problem can be actually defined as a streaming problem in almost every case of a feature. In practice, though, like that's like a nice theoretical world. In practice, batch is way easier. And if you can get away with batch, you should probably use batch. And only when it makes sense to have streaming should you use streaming. And in practice, what we see is like 5% about on average of features at most large companies are actually streaming. In practice, almost everything is batch, and there's not really much value in taking those batch jobs, rewriting them, making them all streaming. Finally, the last kind of wrong puzzle piece is that, oh, what we're missing is this new type of storage layer, which is just where we put our pre-computed features. That's a feature store, as the name implies. And again, it's just not really solving the problem of how do I iterate quickly on features? How do I keep features reliable? How do I collaborate on things, which would require having things like lineage and governance and et cetera. It's really just like a new type of database, which, going to the first point, isn't really the problem to be solved. And as I was thinking about this and thinking about the fact that, hey, we built a physical feature store, that feature platform, but in practice, it's not what people really need. In my opinion, like externally as a vendor, I just don't think it makes sense to force everyone to rehouse all of our data onto us and for us to actually do the transformations and to create some new DSL that every data scientist has to learn. So we came up with this idea of a virtual feature store where you have a declarative API, which you can define and manage your features in. Literally where the idea of feature form and the name came from was I wanted Terraform for features. And that's kind of what we end up building. Something that looks like Terraform, but built for feature pipelines from end to end. So you can define your features, define your labels, define your training sets, define your transformations. You get built-in collaboration, versioning, etc. You get monitoring and alerting built in. Pretty much add this layer, this application layer on top of the feature store infrastructure and use an orchestrator to make the underlying infrastructure work like a feature platform. That was kind of the premise of this. And it works really well because what we're trying to solve here is solve the workflow problem. How can we make all this stuff work together cleanly? And you can solve things like point-in-time correctness. You can solve things like backfill, etc., without having to actually replace all the infrastructure. Especially in situations where companies have like an on-prem and then in cloud, or they have situations where they have, you know, Dynamo for some features, Redis for others. Like there's way more complex deployments in the real world. And really what people are looking for is one pane of glass to define and manage and serve these things. And that's what Terraform's promise is for infrastructure. And I think we needed the same thing for features. And that's the kind of premise of the virtual feature store. And again, to the point of the thing, the feature store in this case is almost a misnomer. It's not about storing features in the sense of like a row of data. It's about storing features as this definition, treating like a definition language and building in all of the components you would expect to exist in an ML feature, around an ML feature, from governance to monitoring to collaboration. Yeah, a little quick, but I actually left a little bit of time for questions. I can kind of go in a lot of different directions here, depending on where people want to go.
Brilliant. Thanks a million, Simba. Great to have you back again. Can you tell us a little bit about the open source angle of feature form? You know, I think many in the community have looked at Feast as being quite successful, but we've seen less development, let's say, on Feast in the last while. And I think you guys have been growing quite a lot. So what's your experience with working as an open source feature store?
Yeah, I think one thing that helps us on, so we are open source, we're open core, more, I guess, accurately. And the things that aren't open source, like we are a business, we do make money. The way we make money is we have purposely not open sourced a few components. The components we don't open source are 1, governance, and 2, stream processing. So if you need governance or stream processing, then that's only in the enterprise product. In the open source product, we do everything else. And from the beginning, we were very clear where that kind of paywall was, and that allowed us to really commit fully into open source and not have to ask the question all the time of should we open source this, should we not? Because we've, from the beginning, been very clear, and it's been the right cut. Because if you care about governance and you really, really care about streaming in real time, you probably are in a position where you want to work with an enterprise solution. And if not, then there's an amazing open source solution for you too. So the short is that we, from the beginning, knew we wanted to be open source. We view open source as kind of the right, there just needs to be a strong open source player. And even more so now, to your point, seeing that Feast is kind of, the maintenance of it has dropped significantly over the last few quarters.
I have another question, just because, you know, you're very active in the community, and you know, we mentioned earlier you have a Python API. What's your take with the, I mean, feature stores originated in the enterprise. It originated with big data, with Spark and Uber, and now we're seeing kind of, at least we're seeing some movement of ordinary, let's say, data scientists and Pythonistas to seeing the value of feature stores. How far do you think we are along that journey, and how long do we have left to go?
We're super early. I actually think that for feature stores to become what I think they'll become and how valuable I think they are, feature engineering is such a core piece of process, right? Like the same way that PyTorch is just something you would just always use if you were using that sort of, if you chose that framework. I just view that something like a feature store would exist in the same way that a software engineer uses Git. Like I view it as something that is as fundamental as like using notebooks. The problem is that most of the feature solutions that exist, we have like a local mode that you can actually pip install feature form, start using it with zero infrastructure. You get all the versioning, all of the things I talked about, and it's all running on your local laptop without deploying even a Docker container. And my view of the world is that that's what it needs to be like, because for experimentation has to be a lightweight process. Production is a very heavyweight process, but we want to cross that chasm. And I think the framework needs to really do both. And I think everyone really gets focused on the production part, which is really heavy in enterprise. And I think that there's been a huge lack of the open source side. I also think this is why a lot of data scientists hate MLOps, where like ML platform teams are like, yeah, like here's another tool for you to do. And data scientists are just like holding their head like another tool. Like we think a lot about the data science workflow. And I actually think that unfortunately, that's like a unique thing amongst vendors. There's that map that has like 5 million companies on it. I always joke that if you were to take that set of 5 million companies or however many companies are on it and limit it to the number of companies that people actually love to use, like truly love to use, would choose to use it every time given the option, it would drop to like 10, 15 products.
I mean, I kind of have a take on this as well. Like we had a couple of speakers earlier talking about some of the inherent complexity, particularly in MLOps.
Mm-hmm.
And as you know, MLOps is supposed to be like DevOps. And the idea of DevOps is to start small, build something small, get it working, and then incrementally improve it with confidence that the changes that you make won't break the system. But where we got to as a community with MLOps is that we kept adding more. So I think Fabio earlier showed effectively the canonical reference paper, the most cited reference paper for MLOps has the most boxes. It is the waterfall lifecycle development model, and it's calling itself MLOps. And I just find the irony in that is just kind of because as a mental map, nobody is following that mental map. Nobody I know of. I mean, I don't think any company in the world has implemented all those boxes in the system. So how do we reset this? How do we reset like the way we build machine learning systems so that they have the properties that we want, they're reliable, that we can incrementally improve them, that we can have good processes for developing them? What do you think the way forward is?
I think it's a great question. I won't claim to have the answer, but I do think that we can learn a lot from DevOps. And I think, like I mentioned, Terraform, which is a product of HashiCorp. And HashiCorp is one of those companies that I find to be very fascinating because it's like 7 open source projects. It like grew faster than Slack revenue-wise. It's kind of a weird company in that sense, and like how it's defined. It's not just a simple platform or one product. But I think it's totally correct for DevOps because, like MLOps, everyone does it so differently. And there is, in my opinion, there's no such thing as like an ML platform that like works for everyone or even works for even 20% of people. I think if you build a platform, you're cutting to like 5%. You might solve all of our problems way better, but really everything's so different in the same way DevOps is. What you need is like a tool belt. And you can pick and choose the tools. And sometimes maybe the tool that you need is a bash script because it's just like, that's it. It's not that complicated. Like I just need a script here. In other places, you need a feature store. Maybe you don't. And I think like being able to build that way, and I've always viewed that this was always going to be choosing the best in class vendors, mix of like kind of your own pre-built simple things where needed. And you can kind of, that's how I think it should be. And that's how DevOps is done. And I don't know why in MLOps we really treat it as like, you need to have like the Ferrari or you need to like, or you have nothing. I think that the in-between is missing. And I think that's because everyone hasn't built a lightweight solutions. I know we have, and we try to, but I think there's a lot more to be done.
Okay, brilliant. Thanks a million, Simba. It's been great talking to you and great to hear you, evangelize the virtual feature store concept again, and great to hear from Feature Form.
Thanks.
There were maybe questions for you on the Slack, so jump over there and see what's cooking.
We'll do.
Moving
Thanks.
on. Sorry?
I said thanks again for having me.
Of course. Brilliant. Now we're moving on. So Simba has talked here before at the Feature Store Summit, but we have Nikhil Garg, who's going to talk here for the first time. Nikhil Garg is the co-founder, CEO of Fennel, a real-time feature store built by an ex-Facebook team. And previously, he was at Facebook, where he led teams behind PyTorch. In a previous life, he was an avid computer programmer and represented India in the world finals of the ACM ICPC twice. So you're no longer a programmer, Nikhil. I still program.
I still write. I mean, my team would tell me that I should not be writing as much code as I'm writing right now, but I still manage to sneak in a PR or two every now and then.
I had the same problem for a long time. Anyway, really looking forward to this.
Thank you so much for having me. Let me share my screen. Do you all see my slides? Wonderful, great. Great to meet you all. Apologies in advance if my voice is a bit broken. I'm still recovering from COVID, but I think I'm all patched up enough. I want to start with my journey of feature platform. It started several years ago. I was at Quora back then. I started the machine learning infrastructure efforts, and I gave a talk in 2017 talking about open source ML systems that need to be built out. And I talked about two layers of the very nascent MLOps stack. One was model management, the other was feature extraction framework. And I went on to describe what I thought, based on the needs we had already experienced at Quora, what a good feature extraction framework may look like. Those were the early wild west days. You can see I was calling it feature extraction framework. The term feature store did not exist yet back then. And so, I gave this talk, I presented what I thought were, obvious ideas, and I moved on with my life. I, from there, went on to, work at Facebook. At Quora, I led several quality abuse risk related teams. At Facebook, I was closer on the Rexis side and some on, integrity, but not fraud space really. Eventually, I ended up, running a large part of the team behind PyTorch as well. And each of these experiences was, quite transformational in many ways. Through Quora, I first started understanding the problem from first principles. At Facebook, I saw, what 3 generations of a, solution for this looks like. Kid you not, Facebook has, I think as of right now, over 100% organization working on the feature engineering system. I saw real time, gaining adoption and becoming very important everywhere. And at PyTorch, I truly, got doctrined the school of, beautiful Python APIs is all that matters. And if you can make people productive, everything else can follow from there. When I was leaving Facebook, I was, thinking of doing my own startup. I looked around, and to my surprise, the deck that I had put out in the open in 2017, I still didn't find a feature store, as it was called, by then. I didn't still find a feature store that more or less, lived up to the manifesto I'd created. And so we just decided to move on and do that. And that's what I'll be talking about in today's discussion. What Fennel does and how it is so different from a lot of other options out there, and what is the thinking process behind that. For the first few minutes, I'll spend maybe 5-7 minutes, not more than that, just literally walking you through some code snippets of what does it feel like to write features in Fennel. This is important because it sets the tone for the rest of the conversation. After that, we'll talk about a handful of choices that are very, countercurrent right now, very unique choices in, the constraints we are taking. And finally, depending on how much time we have, we can go a little bit deeper into the infrastructural choice, like specific, nuts and bolts of how things work together. But first, I'm gonna keep sharing my screen, but open Fennel docs and walk you through a few code snippets to help you understand, what's the experience actually feeling like. Fennel has 2 main abstractions, a data set and a feature set. I'll only talk about data set right now. We don't have enough time for a full walkthrough. Data set is effectively a table of data. This is a data set called product. It has 5 columns: product ID, seller ID, price, and so on. Each of them has a type. As you can see, the schema is written in a Pydantic inspired manner. You have some metadata, owners, and tags, and so on. And more importantly, here we have system telling us that we should be looking at Postgres table called product info every 1 minute and using whatever new updates have happened there to hydrate this dataset product. In other words, this dataset product is going to be a near real-time mirror of your Postgres table product info. And if your data did not live in Postgres, we have, let's say it lived in Kafka, we have different decorators for all of those systems. All that changes is the source decorator, but wherever the data lives, whether it is, S3 or, Snowflake or Redshift or Kafka, Kinesis, Postgres, MySQL, wherever the data lives, we know how to get it. All you need to do is define the schema in a Pydantic inspired manner and put the source decorator on top of that. But quality is a very important concern for us. It's a top 3 design decision for us. And so there are a bunch of small primitives already for you to start elevating your data hygiene. So for instance, you have a very strong typing system. Here, for instance, if we see a description, it can be string or it can be null, that's fine. But if we see a price that is null, we would not even admit that data in the data set. More generally, we have strong typing, and so anything that does not meet your types does not get admitted into the data set. We have new types as well. We have a type for regex match where you can say that only those strings satisfy this type that, satisfy the zip code regex, and only valid zip codes at the type system level are enforced to be present in the column. So downstream users don't have to do defensive programming. There's just one primitive. We have many more primitives. Here's another one I want to show you right now. We have native data expectations. So in line, you're able to describe that you expect the column price to be between 1 and 10,000 in at least 95% of the cases. This is a lot like great expectations. In fact, it is literally built on top of that. But this is computing these expectations in a streaming real time as new data is arriving, and you can set up alerts against that as well. Now, all I've shown you is wherever data lives, you can bring it to Fennel and start elevating the data hygiene. But more often than not, you want to derive more data using the data sets that you already have. So imagine this is a data set you wish to derive, which given user ID and seller ID is counting the number of orders from that user on that seller in last 1 day and last 1 week. So a typical rolling window aggregation, a very common in feature engineering. This is how you would write that pipeline. This is a function in the class. You are saying I'm starting from order and product datasets. These are the datasets I showed you earlier. You're saying if I know these two, I know how to derive this out of it. And now order gets bound as a function argument here and product gets bound as a function argument here. And you can now describe all your pipelining logic. You can join, you can transform, filter, add rows, add columns, all of that. Now, there are many things that are really nice about this. I'll highlight a couple and I'll go back to slides after that. The first thing that's really nice is it's extremely declarative. You're not having to think about, where should this run? How much RAM should be given? What if data doesn't fit in RAM? How should it be partitioned? How should it be scheduled? Is it waiting for an upstream job to finish? You don't have to think about any of that. The second thing that's really nice about this is very, very Python native. This is an actual Python Lambda, a free-form Python Lambda that will be executed against every row in this data set. This is an actual Pandas data frame. And so all of Pandas API is transparently available to you. You can import your favorite Python libraries and start using them as a part of this Lambda. So if you know Python, if you know Pandas, you know how to use this, and you can bring the full firepower as well. The most important thing is this is actually a streaming pipeline. It looks really simple to write, but as new rows or new updates arrive in orders and or products, this logic is executed incrementally only for the new data. And this data set is updated wherever those updates happen. And that process is happening continuously. And the exact same code ends up powering irrespective of order itself coming from, let's say, batch sources like S3 or Snowflake or Kafka, or same for this. None of that matters. The exact same code powers, and you're now able to bring data from multiple places in the same plane of abstraction and act on that. That's all I want to show you right now. Now, with this flavor in mind, now let's talk about some of the interesting choices we have made that are somewhat counter-current right now. To simplify the authoring experience, as you can see, we let people write pure Python with Pandas. There's no DSL involved. There is no PySpark involved as well. And so benefit of this is, people, ease of use is obviously there, but they can interop with full Python ecosystem as well. And this is straight up, a page, we took from the PyTorch playbook. And our belief is we need to meet people where they are. I think what I see a lot of other technologies in the industry doing, this is what TensorFlow did as well, until PyTorch came and started beating them, is build the experience with performance in mind. Whereas I think what PyTorch did was they said experience is important and will solve performance at lower levels by doing a lot of innovation, which is what we ended up doing this. How do we then solve performance? We built everything in Rust. We do very fast Python Rust interop. We literally embed the Python interpreter inside our Rust primaries. And some of the new improvements that are coming in Python, where GIL is not a problem anymore, it actually turns out to be a lot more feasible than we initially thought early on. On the data computation side, Simba earlier mentioned that most use cases are batch. That is true, but we also found that almost everyone has some streaming features, and people are not comfortable having two different frameworks, some for streaming, some for batch. And we also believe that the utility of streaming is only going to go from here. And so what we did was we have no separate batch or streaming subsystems. There is no place in the product where you annotate and say this is batch or this is streaming. The exact same code works for everything. Everything is streaming all the time. It's built on Kappa architecture. And not only it makes the system future-proof, it ends up removing a ton of complexity from the end user. Like for instance, backfilling a streaming pipeline is so terrible because backfilling is inherently a batch-oriented operation, but the streaming pipeline going forward, it needs to do streaming. It's resonance mismatch. And so this completely eliminates all of those interaction modes. And the way we were able to do this is we literally wrote our own stream processing system written in Rust, very memory efficient and purpose built for this kind of operation that becomes common. There's another element of real time, which is what are sometimes called as on-demand features in our world. As we spoke with more and more companies, we discovered that people want features to be able to depend on each other recursively and derive from that in arbitrary ways. And there are also many features which you have to do some more interesting processing. So we came up with this abstraction called read-write separation, where our features are not stored data, but rather they are stateless functions. And those stateless functions run on the read side where the request is waiting, whereas all the computation that is asynchronous via pipelines is happening on the write path. The write path is throughput oriented, but not latency bound. Read path is very latency bound, but usually not throughput oriented. And you now have the ability to keep some computation on write path, some on read path, all on write path. You can pick and choose how you want. And what this ends up doing is very flexible feature patterns become possible. So for instance, if let's say in recommendation world, which is my world at Facebook, a very common feature is dot product of user embedding and content embedding. That's very hard to express because you have to do that computation on read side. You cannot pre-compute order n square user item dot products. But by keeping it on the read, but keeping some other computation on the write, it becomes quite natural to express as well. To simplify quality, this is another thing that we kept hearing. We just went ahead and made a native best-in-class tooling and added it to the product itself. And literally what we did is, we asked ourselves, what are all the quality problems we've ever seen in our lifetime related to features? And for each of them, we asked ourselves, how do we design a solution against them? Can we catch them at compile time? Can we catch them upstream? If not, if none of those preventive mechanics work, can we diagnose that somehow? Can we do monitoring, etc. on it? And so what this ends up doing is, as people's features get more complex, the confidence still stays up. And everything from versioning, immutability, strong typing, data expectations, drift monitoring, unit testing, all of that just natively part of the product itself. Here I'm showing a couple of screenshots of drift monitoring and data expectations. Very contrary to the very previous speaker, we actually to simplify operations, we do deep vertical integration. We are highly anti-virtual. We find that when we are starting to research into this, is existing feature stores need people to bring their own KV stores, their own compute engines, own Spark, own metadata stores, sometimes own Kafka as well. And you could make a case that customer already has some of them, but in practice it is a lot harder than that. There's a lot of operation work and more importantly cost work as well. Redis and Dynamo actually do not work for a lot of people at scale in terms of cost. And then even if cost is not an issue, operation is not an issue, shared dependency then leads to a lot of confusion. Like who does auto scaling of a shared Spark cluster as an example? What happens if some jobs are failing? Who's on the on-call for that? And so this is a very counter-culture choice, but what we have done is whatever funnel needs, we bring that up and manage all of that ourselves. And there is zero dependency installation for the end customer. Obviously, this increases our surface area quite a bit. We have to do as good of a job running everything smoothly in a cost-effective manner, in a compliant manner. But as always, every step of the way, the choices we take are make it easier for the end customer, make it harder for ourselves. Taking a page from the PyTorch playbook, so to speak. And finally, to simplify InfoSec, this is also a counterculture choice we made. We we do also have data planes and control planes, but our data planes are rather thick and control planes are absolutely tiny. And as a result of this, what happens is our control plane can literally go down and your workflows will not be interrupted at all. In other words, our data planes are thick enough to be nearly self-sufficient. Even the auto scaling lives inside data plane. Even the console UI where you see the code of your features lives inside data plane. So your data and the code of your features are never really leaving your data plane. Now, all of these choices, literally every single one of them, requires us to solve hard engineering problems, but it ends up creating, in our admittedly biased view, a much superior experience for the end data scientist. Now, I probably don't have time to go through all of these, but I'll just walk through a couple of these things real quick. As I mentioned, we built up our own streaming engine. We had to satisfy the constraints that we created for ourselves. I'll just walk you through a couple of choices related to those. One very important choice we made, by the way, this section is now going a level or two deeper than the rest of the conversation. We have built up our streaming system in a way that there is no synchronous communication everywhere. It's a full shared nothing architecture. Unlike Flink, where operators communicate with each other via RPC calls, which has some benefits, but it has some downsides as well. Fennel does not do any of that. Communication is either within a node, so in-memory channels and so on, or it is asynchronous, mediated via Kafka. And since we use Kafka, it naturally handles back pressure, backfilling, things like that. A single node can go down, many nodes can go down, and everything else continues making progress without any interruption. And we also get exactly once processing for free as a result of this. We use RocksDB for managing the state store of our streaming jobs. But there are several interesting choices we made here as well. All the writes during iteration are buffered in memory, and they are applied together atomically later. This maintains the exactly once processing, and our jobs as a result of this can die anywhere and can wake up on any other node of the cluster, and they'll continue working. We are taking periodic backups using EFS. I don't know if any of you are using EFS for backups, but really, really good tool for that particular problem. And we also store some transaction markers in Kafka so that if we have to do recovery, we do optimistic recovery, we are able to do that effectively. We are doing continuous checkpointing. This is one of the bigger problems with Flink. Flink checkpointing model is stop the world, which means every time you're writing a new feature, the topology is changing, which then means that you need to stop the world for a few minutes, which creates a lot of lag, not acceptable. In our model, every job is checkpointing itself continuously, independent of other jobs. So it's distributed checkpointing. The local SSD checkpoint happens every second or so. So the processes could die and wake up again on the same machine, and they just literally pick up right where they started. And we do persistent checkpoints across machine boundaries using object stores every few minutes. And so if the whole machine dies and we have to bring up the job on a different machine, it first spends a few seconds catching up and then continues processing from there. The benefit of this is the system becomes much simpler for us to operate. It's quite literally built for resilience in mind. A node can go down and there is no issue whatsoever, and we can still get fast recoveries. Now contrast this to what a customer may have to do if they were to run Flink on their own and handle these kinds of issues. One very common problem with Spark and to some degree Flink in feature engineering world is they run out of memory. I mean, they generally happen for all data engineering jobs, but particularly for large rolling window aggregation jobs in feature engineering. We have built up a stream processing engine in a way that there is no in-memory state of jobs. State always lives on disks. And in practice, it's built up in a way that it lives in either the OS page cache or block cache of RocksDB, maybe mem tables. So we still end up not creating that much overhead in reading and writing from it, but the state does not blow up no matter what. And OS transparently pages out certain memory if it is not needed, so that it does not go out of memory. In addition to that, we don't do any in-memory shuffle operations either. As I mentioned, all communication is mediated via Kafka. We don't use JVM. We write things in Rust. There is no GC, so memory cannot go up temporarily, and we generally have very tight control on RAM. And all of it means that OOMs are structurally impossible. And once again, it's much easier to run a cluster like this compared to what our customer may have to do. Our streaming engine is time aware itself. Flink and Spark are both way too general purpose, but there's a lot of structure in the problem of feature engineering. There's always a notion of time. And in fact, you do need that notion of time to be able to do watermarking, handling out of order events, time window aggregations, and so on. So our engine is itself time aware. And that is how we are able to do point in time, feature creation, but it now also allows us to do point in time correct streaming joins, which are really powerful because, let's say you have a stream of Kafka events and you want to enrich those events with some information that lives in Postgres. That's effectively a join between Kafka and Postgres. And doing that in a time correct manner is very, very hard. But making our streaming engine time aware, this becomes immediately easy for us. There's no central scheduler. Everything is horizontally scalable for us. There is a supervisor on each node picks up, divides work, and then they just go on their own. And this is another choice, which means that there's no synchronous communication and no single point of failure. These are some of the tidbits of the engineering that went behind in unlocking the experience choices I was talking about. You can always read more on our documentation and reach out to me over email as well. That's all I have. Happy to take any questions.
That's brilliant, Nikhil. Thanks very much. It's really interesting to see, the level of detail you've gone into, and I actually work with the Flink guys, so I have colleagues Paris Carboni and Safer Reedy. So they did designed the Chandler-Lamport global checkpoint algorithm for Flink and wrote the main paper on it. So I mean, that paper itself, the research paper that they published, enabled the community to build confidence, I guess, into the correctness of their algorithms. And you've done obviously some stellar work at Facebook before. Do you intend giving out the details of your global checkpointing algorithm and the correctness, or do you have any plans on filling in more on that?
We do want to over time, write more on that. I mean, so first of all, a couple of things to say. We have a lot of respect for what Flink people did. I mean, they are true pioneers. You're standing on the shoulders of giants there. I think they came up with they formulated these problems. Let me put it that way. I think problem formulation is a lot harder than solving them usually. And now that we have seen a whole generation of people use that for this specific problem, those are the areas where we are, optimizing. So a lot of respect for them. Definitely plan on making more of this content available over time. We also intend on open sourcing a lot of what I described it today. It's a question of when, not a question of if. We are a tiny company and we only have so much bandwidth. But yes, stay tuned. Hopefully there will be more to share on that.
Great. We have a question from Saurav Srivastava on the chat. Is Python and Pandas combination able to handle feature generation for large volumes of data, petabytes of data, or should you be using Spark?
No, absolutely, it can. And once again, see, the magic is not that we are relegating everything to Python and Pandas, and Pandas famously does not work beyond a certain scale of memory. And so what we are doing is all of this computation is mediated via a Rust streaming engine, and it takes small chunks of data and relegates the control to Python and Pandas only for that small chunk. But the chunking and the assembling and all of that is still happening in the Rust land. And so, we can almost put, bounds on how much memory it's going to take and so on. And you can, fearlessly operate this in very large data sets. It's all horizontally scalable, in fact, as a result of that.
All right, great. We have another question, but I think maybe, from Jeffrey, maybe we can take it on the Slack because we're out of time. Thanks a million, Nikhil. It's been great. And looking forward to see more of Fennel in the future.
Thank you. Thanks for having me, folks. Bye-bye.
Great. Thanks very much. So, drop over to Slack if you want to see more, ask Nikhil more questions, or if you want to see the answer to some more of the questions that are there. Next up is Uber again. So we have Uber's risk knowledge platforms. We have, I can see Kaveh is here. So Kaveh Srinivasan is a software engineer in the Uber risk knowledge platform team. Her role revolves around contributing to Uber's graph database and devising practical solutions that aid in combating fraud on a larger scale. So before joining Uber, her experience was centered on addressing abuse and spam within Yahoo Mail, and her focus on real-time solutions to various abuse scenarios. I can see Christopher is here. He's a machine learning engineer in the risk applied machine learning team at Uber, and he builds ML infrastructure tools to assist machine learning engineers across the risk platform in building effective model training for fraud and abuse problems. Leveraging the tools he creates, he also trains and deploys models to tackle some of the most challenging earner abuse issues found at Uber. And then we have Jean Kai as well. It's a senior software engineer in Uber's risk knowledge platform team, and she's a key member working on the key large-scale distributed self-serve feature engineering platform for ML purposes. And she architected and implemented core components of the stream computation platform to support various teams across Uber. And we're delighted to have you here to talk about, I guess, use of feature stores in terms of risk. So over to you. You can share your screen. I think we're a little bit, that's probably me. Yeah. I was zoomed in too much, not everyone else. Okay, try and share your screen and we'll see if everything's going good.
Great. Thanks so much for the intro, Jim. Yeah, so we were going to do our own intro, but we can go ahead and get started. So yeah, I'm Chris. We have Kavya and Jean here, and we'll pass it off to Jean to take us on the start of our talk.
Yeah, hi everyone. Today I'm going to present Risk Knowledge Platform together with Kavya and Chris, and here's today's agenda. First, we'll start with platform overview, then deep dive into UFlow and uGraph feature store, then later the use case for machine learning of risk assessment. Next. So why Risk build this feature store? The motivation is Risk needs a scalable self-service feature engineering platform for computing features for predictive decisioning and machine learning purpose. The use case includes payment fraud, promotion abuse, GPS spoofing, account takeover, and so on. Next. Here's the architecture of the Risk feature store. So when an event happens, for example, when user take a trip or user signs up, this kind of events will hit the risk decisioning service, and then the risk decisioning service will fetch the features from knowledge platform, includes uGraph and UFlow. So all the features are managed by a feature spec, and then both uGraph and UFlow have DB write log. And together with the event log of the decisioning service, both will contribute to the feature time travel tool that Chris is going to present later. Next. So here's the end-to-end feature engineering flow. The data analysts and data scientists will try to explore and analyze what data is useful for building into a feature. Then they will go through the feature engineering process and then feed these features into machine learning models and rules, and result in potential actioning like ban, warn, or error. The latter two steps are called decisioning, and then the decisioning result will contribute back to the feature iteration. Next. Yeah, so let's deep dive into the UFlow feature store. The UFlow computes 3 types of features: batch, near real-time, and real-time. All the features are managed in the following 4 aspects. First is the feature catalog. It has all the definitions of the features. And then we have, next is the feature quality. The users are able to access the metrics of feature correctness, distribution, completeness, freshness, and anomaly detection when they want to explore. And when the users want to debug, they can trace up and downstream of the feature by the feature lineage, and then try to find the feature correlation between each other. And when people create, evaluate, or deprecate a feature, then that's the when the feature lifecycle comes into the picture. Next. So here is how our batch feature computation work. The data source is from Hive. It can be self-computed or externally pre-computed. And then the Hive data flows is dispersed into Cassandra with the support of Auto Bootstrap, Auto Backfill, and CI/CD. And during the dispersal, there will be feature level optimization. Like, for example, we only disperse incremental changes to save the computation resource. And we disperse the data with TTL, so it can save some storage costs as well. The end-to-end development is all spec-driven, so it's non-engineering friendly. Next. So next is a near real-time computation. The data flows from Kafka to various kinds of things. And then all the pipelines enables feature write log and the DLQ support. And all the data quality metrics are handy for people to explore. So for some compliance use cases, we also enables the end-to-end exactly once processing for them. So the backfill from Hive is also supported for this computation. And for the complex use cases, we have RPC fanout. Early termination is supported for optimization of performance. So for different use cases, all of them are decoupled for the resource and computation, and multi-tenancy is supported. Next. Yeah, so both the mentioned batch feature and near real-time features support aggregation. So our aggregator has aggregation function like sum, count, and so on. And the window can start from minutes to hour to day or year or lifetime to date. Yeah, and then all the computed features will go to Cassandra and then will be fetched in our real-time service, which comes in the next slide. Yeah, so here is our real-time service architecture. It has two parts. One is the feature access and one is the feature update. So for feature access, we enables cache for it, and hierarchical feature fetching are supported. So people can mix and match different gateways, different DBs, different orders, and then to achieve the comprehensive fetching. And then for some use cases that after the feature fetching, we also update back the feature. Yeah, and similarly, the write log is also enabled for the feature update in this real-time service. And for the real-time service, we'll achieve 4 nines availability. And this is all for the UFlow deep dive. And I'm going to hand over to Kavya.
Thank you, Jean, for that high-level overview of UFlow. Hey, everyone, I'm Kavya, and I work in the UGraph platform of the knowledge platform team. Next slide, please. So a little bit context about knowledge graphs. So we at Uber have a lot of data about a lot of different entities. To make sense of these entities, a graphical representation is very powerful because it helps us understand unstructured data and convert it into a structural form by representing it through vertices and edges. So the relationship between the vertices help us understand direct and indirect relationship, which are not clearly visible from the unstructured data. And it's also easier to visualize the data and also query it using some of the open source languages that are available. In particular, this is useful in risk context where you want to be able to understand the fraudulent activities that are happening, which are also not easily visible through the data that is as is available. Next slide, please. What is UGraph? UGraph is actually an internal term, and it's an umbrella term that we use for providing both real-time and batch solutions to do feature computation and querying. It supports real-time for point-to-point queries and also batch for ML-based feature computation and also bulk queries, mostly used for deriving insights and also facts. Next slide, please. So the real-time and the batch is what we refer to as OLTP and OLAP. So I'll be talking about the ingestion framework of how data gets inside. So like how Jean mentioned, we also have a spec-driven framework for OLTP and OLAP, where you can specify whether the data is ingested through a Kafka topic or through Hive. And you can specify what vertices and edges needs to be ingested, along with the different properties for the vertices and edges. And the Hive table ingestion, which we often refer to as the bulk ingestion, happens through Spark jobs, which is either once a day or at different intervals in time. Kafka topics are used most for streaming ingestion, which is happening through our Flink-based streaming ingestion platform. And we use Cassandra as our primary database for OLTP. And on top of it, we also have a querying layer that almost always gives you a real-time snapshot of what is there in the current time. Next slide, please. OLAP ingestion framework, similar to OLTP, is also a spec-driven ingestion framework, but we only operate from the Hive tables because it's a batch processing system. But here, the kind of output that we store is in 3 parts. So one is reconciled graph, another one is feature graph, and the other one is intermediate graph. So reconciled graph is similar to the OLTP data, where at any point in time, it gives you a holistic view of the entities in current time. Feature graph is more of an ML-driven use case, which is also a subset of reconciled graph, where you don't have all the entities in the graphical data, but only select entities based on different ML use cases that we need. And it's usually run for a historical point in time. So usually ML engineers come up with a specific use case that want to run for a historical time data. The third one is the intermediate graph, which is used for regenerating reconciled graph in case we miss any data, and also to generate the feature graph for historical time. And it's a date partitioned table, so we can go back for however long we want and then regenerate the data. As similar to OLTP data, we also have a querying layer, and the querying layer, I'll talk about it in later slides, which is a common querying layer used between the OLTP and OLAP. Next slide, please. So to more explain about the feature graph and how it is built. So ML engineers usually want point-in-time historical data. So they come up with a use case, and they also specify what start dates and end dates that they want to run this feature graph for to generate the historical data. So we go back in time, use the data from the intermediate graphs to generate the feature graph. And this is an accumulated data, right? So we do this for successive dates between the date ranges. And then at the end of it, we have one final feature graph, which can be used for querying by the ML engineers. Or you also have the ability to look at the partition data and see how features are changing in between. So this is, again, a spec-driven framework where you don't have to worry about writing a code. You just have to give us a spec, and the system will take care of generating the feature graph for you. Next slide, please. So now that the ingestion and the ML feature generation is done, I want to spend some time about Cypher. So Cypher is the open source query language that's available for querying graph databases. So it was generated or discovered by SQL, based out of SQL. So the syntax is very similar between SQL and Cypher in how you write the query. So here I have a very simple use case where it tries to represent user-to-user relationship that is connected through a phone number. So you have a user vertex and you have a has phone number edge followed by another vertex, which is a phone number vertex. And from the right side, if you see, you have a U2 user that's connected also to the same phone number. So this is a very simple query to connect users between two users who share the same phone number. Next slide, please. So if you want to use this query to generate features, then I've extended the same case to generate unique UUIDs who are connected through the same phone number. So the same query is extended. And in addition to returning the user UUID, you also return the distinct UUID. So you can similarly add relational clauses in this. You can also extend it to apply filters like how you would do in SQL. So it's just about how you write the query to extend it for different feature generation use cases you would need. Next slide, please. So how does it all come together? So once you have the Cypher query, you give it to our service, and the service will take care of generating a query plan that is as optimized you would want in the query execution. And then it gives it to a computational layer, where instead of running the query against the whole database, we fetch a smaller portion of the graph database based on the query that you've given us. And then from the returned subgraph, you will compute the query or do the feature computation on top of it and return the response back to the service. So this is at a high level covers what we do with uGraph in risk context. And now I'll hand it over to Chris.
Thanks, Kavya. That was an amazing overview of uGraph. Yeah, so my name is Chris. I'm a machine learning engineer here on the risk team. I'll talk about machine learning for risk and how we can provide real-time predictions is what I'll start with. Sort of going back to the architecture Jean mentioned earlier, we have sort of user starting off with requesting a trip, and this first flows into our decisioning service. This decisioning service is ultimately where we can provide our predictions and make a decision on certain kinds of requests. For machine learning engineers, this means making calls to Michelangelo, which will serve our machine learning models that can help us evaluate risk across a number of domains. We may have many different models, such as payment fraud models or account takeover models. And let's go about thinking about how we might build one of these models. And maybe we can start with how might we build a payment fraud model? Maybe the goal here is we want to calculate the probability of some kind of payment resulting in fraud loss when, for example, user requests a trip. Of course, whenever we train a machine learning model, we need data. And so the first thing we can start with is in this decisioning service, we have some log of events for every event that we've provided a decision for in the past. And this log may contain many entity values, such as the user that's acting, the payment that they used, the email domain of the user, maybe the fare that the ride costed the user, and maybe the timestamp that the trip happened at. This data is called our basis data. And we can see that if we combine this data with some kind of label that we determine in some fashion, we can train some kind of maybe naive model classifier that can feed in this data and maybe give us a not so good model. And let's think about why, right? The type of data that we have here in our basis data might not be very powerful for machine learning. For example, just using the email domain alone or the ride fare alone, this data may cause the model to overfit on, for example, the ride being very expensive and or certain email domains being very fraudulent, at least when the model is trained. And so what can we do to make it better? Of course, we would like more data, maybe enrich the model with more features. And let's start with how we can do that with batch, right? So I want to dive into how we do batch feature backfill. So the first observation here is that in our basis data tables, we have a few different kinds of entities. We have primary entities. These entities sort of like define the primary actors that are involved in a request. Here we have the user, they're the ones making a trip. And then we also have secondary entities. And these entities are sort of like the entities that are shared among multiple primary actors. For example, the same user may share the same payment or maybe even share the same email domain. And the observation there is that when we do batch feature backfilling, we can take those secondary entities and pre-compute some kind of entity feature tables across many different metrics to provide feature values for every entity value. In this case, we sort of see that across many entities, such as like maybe an email domain or destination geohash, we can compute features such as like the email domain chargeback over a 7-day window, given that we also are computing for like metric of chargeback in a time window of 7 days. And we can do this for many time windows, many metrics, and many entities, and all the entities that are in our basis table to compute sort of like a product of the number of entities times the number of metrics times the number of windows. And this allows us to extend our training set to at least cover all of these entity feature table features, which gives us a lot of additional predictive power in our machine learning. And you see now we have a high performing model. But of course, like, what are the gaps? Like, when do we need real-time feature engineering or near real-time feature engineering? Well, the answer is like when we want to ask questions like this. How many trips has the user taken in the last 24 hours? If we just do this in a batch fashion, this might not give us an appropriate level or appropriate granularity of accuracy. Or we want to get like some kind of attribute feature like the user's last known phone number, or if there's some new entity value observed for the first time and we're sort of observing the cold start problem, we may see that it doesn't have values populating very well yet. Or anything related to graph where we want to count number of like users linked by the phone number to the current user, or even like for the fraud domain, number of banned users linked by the phone number. Any kind of feature engineering on primary entities benefits substantially from real-time feature engineering, which is really relevant for the types of problems that we see in the risk domain, such as account takeover, new user fraud, and marketplace abuse, and even safety. And so let's kind of dive into how do we do near real-time feature backfill and what are the benefits? So the first observation is that for these sort of attribute features that we have, we can use temporal join to stitch their values to our training data set. So temporal join has just been a tool, kind of a term that's like known about for a while, where for every event in your basis data, you get the value of the feature that happened right before. And so this is how we can stitch sort of attribute features to our training data set. And then we can see like the benefit of having near real-time aggregation features for this new.com domain that we saw on the last slide. Near real-time feature aggregation here can sort of help us fill in the gaps that batch feature backfill would have. And the caveat here to all of these like solutions for creating features is that the data must exist in some kind of offline storage. And so the solution that we built for this is we started persisting changes into a write log. And so remember from earlier, we have this sort of solution architecture for near real-time feature computation where data is read from Kafka. And then in our ETL, we may do some kind of RPC to an external data source before we load into Cassandra. This value of this RPC may not exist in historical data, so we also write it to our write log. And this write log is the same write log that lives below ugraph and uflow. And this sort of allows us to persist all the changes to Cassandra features and can later be transformed into a change log. what can be transformed into a changelog, you say? Well, one observation we can have is that we can drop redundant writes for attribute feature types. This sort of like gives us a way to implement an optimized change data capture solution. And for streaming aggregation features, like we can maybe relax some of the latency requirements and say that we can do some kind of pre-aggregation to reduce QPS to Cassandra and reduce changelog storage, as long as we say we can aggregate on like a minute level basis. Yeah, so this is the last slide, but kind of like summing it all up together, one of the main challenges we see is that we want to provide machine learning engineers access to a tool that can construct training data for them. So this is what we have with this time travel tool. Users can specify sort of like their basis table, join keys, and feature groups. And for both batch and near real time, as long as that we have data in TV changelog or in some kind of Hive ingested Kafka, users can specify basis data, use our time travel tool, and ultimately output a new table with a bunch of extended batch and streaming features. And this allows us to transfer from ML with basis and batch feature backfills to ML with near real time feature backfills. Yeah, so that's our slides.
Brilliant. That was a great tour de force of many different contributions you've made to building this system. And you know, I think I haven't heard the kind of the differentiation between. I'm going to ask one question just to start off with. Attribute and aggregation features. You know, you kind of differentiate between them as different classes. Is that something you've done internally? Because I haven't seen it too much in the community.
Yeah, we used to call these non-aggregation and aggregation features. The key observation is just the way that you can, like the functionality, like how you can time travel with the features or how you can get the latest values. Since with aggregation, you always have some kind of group by, you're grouping by user UID and some time window, but attribute is sort of grouping by like an infinite time window. You can go back far, like infinitely. Yeah.
Yeah, I have an observation about time travel. I mean, sorry, what you call point in time joins. You can tell me what you think about it, right? So we use the term multimodality in deep learning, that, you know, you have some image and then you have some text, and then people are trying to extend it to multiple dimensions. But it's really kind of similar to what we're doing. We take an observation, maybe some credit risk, and then we say, well, what was the state of this feature at this point in time? What was the point? So in some level, we're kind of trying to solve problems, I think, that other domains in deep learning are just starting to look at. Would that be reasonable, or am I off track here?
So when you say multimodality, right? The first thing that pops into my mind is like the image and text, right?
Yes.
In this case, we're sort of looking at the problem of, like given this point in time, like what's the current state of the world that we know about, and like can we provide the correct like what the best decision that we would have been able to provide.
Well, I mean, think of it as being, you have different pipelines updating different parts of the world concurrently at different cadences. And we're trying to figure out, you know, what were the values at this observation point for this label that I'm trying to use as my kind of point in time and get the feature values for. I don't know. I think it's a challenging area. We've looked at implementing join operators for Spark at this, and so I'm too deep in the leaves, I think.
I see. I feel that there's some opportunities for sort of like knowledge understanding up until a point in time, and we can maybe even consider like having understanding of like image data up until a certain point in time and feeding that as like feature values. I feel like is all a data engineering problem.
Yeah, I mean, another problem I've seen is we often see that we have this look back window that we're not going to go look further back in time. And then you have in the online feature store, you might have a time to live for a feature, and there's potential for data leakage there. So if you make the time to live feature very low, but when you're generating historical data, if your look back window is larger, now you have potential for data leakage. So it's a fascinating area.
Yeah, definitely.
Brilliant. Thanks a million. Thanks, Christopher. Thanks, Jean. Thanks, Kaya.
Thank you.
We're going to move on. So I'm delighted to have a new feature store, FeatureByte, join us today. We have Javier Conort, and he's a visionary data scientist and co-founder of FeatureByte. It's a company committed to empowering data scientists and streamlining feature pipelines. But before co-founding FeatureByte, he was ranked as the #1 Kaggle competitor in 2012, 2013, and he pioneered AutoML at DataRobot. And at DataRobot, he decisively shaped and executed the data science roadmap in his role as chief data scientist. And he's a rich history spanning over 25 years in the data domain. He started his career as an actuary in the insurance industry, and now he's made the move to data science. Welcome, Javier.
Hi, everyone. Thanks, Jim. Thanks for the introduction. So my name is Xavier Connor, and the co-founder of FeatureByte, AI-based feature platform. And today I'm going to talk about the challenges of feature engineering, the benefits of feature platform, and how we use generative AI at FeatureByte to make feature engineering even more accessible. So while feature engineering is a critical step to build machine learning models, is still a very challenging task for many companies. So to create and serve features, there are three skills that are essential. Domain expertise help us understand the data and how the different data assets connect. And this makes it that we can come up with feature ideas. Data science skills help us translate those ideas into mathematical forms or code. And it's a time-consuming task, and because the possibilities for features are limitless, and it's a challenging task because there are different types of features that you can create in function of the semantic of the data. Data engineering skills are also essential. You often have to work with extra large transactional data. You also have to work to build the pipelines that are time accurate to avoid time leakage and to ensure training serving consistencies. And also you have to serve the features in production. Google Bard reminds us of another important principle for features. He advised us to create features that are relevant to the use case, and also that advise us that those features have to be informative and interpretable. And while those three skills remain essential, there are two recent innovations and that can improve the feature engineering process, the feature platforms, and generative AI. Feature platforms offer multiple benefits. So they make the feature engineering more accessible and more efficient in several ways. First, they reduce the latency of feature serving by pre-computing features and storing the feature values in the online store. Second, they prevent the inconsistencies between training and prediction. And it is an important result to prevent situations where inconsistencies may affect the accuracy in production. Third, they often simplify the creation of complex features thanks to a declarative framework, and this quite often in Python. Fourth, some feature platform accelerate experimentation by offering automated backfilling, and so there is no log and wait. You can experiment your new feature IDs directly. Fifth, they make it easier to find and reuse existing feature. So this is important to avoid the feature explosion. And finally, they provide a unified solution that makes the transition from experimentation to deployment smoother. So in summary, they make feature engineering more efficient, more accessible, and more accurate. Along feature platform, transformers are revolutionizing data science. They simplify very complex tasks, NLP. So they allow data scientists to transform a text column into new outputs that can be more easily aggregated, like text embedding, sentiment analysis, or extraction of keywords, or extraction of entities. And this work can be done by data scientists by using off-the-shelf transformers without training data, which is awesome results for data scientists. And as a product manager, they're opening a new horizon. They make that product managers can create new data-driven products. There are two personas that may be concerned with transformers. Risk manager may find transformer too new, too opaque, and too stochastic. And MLOps engineers may be worried with the operationalization of the features. So you may have a question: do I still need feature platform for transformers? The answer is yes. They complement each other. Feature platform can improve the operationalization of transformers. They ensure point-in-time correctness. They allow low latency of serving of those features thanks to their pre-computation. And they also give opportunities to reduce expensive transformer calls via partial aggregation or other mechanism, other caching mechanism. Another question is whether transformers will replace traditional feature engineering. Here I'm more skeptical. The use of transformers were successful in some situation, for example, to work with sequences of events, and so there were successful results for recommendation system. But the use of transformers on a larger context, on many more columns, and that are less well defined, the problem is more challenging. And even if a solution emerge, there will be less magic than for NLP. It won't be pre-trained off-the-shelf transform that you can use directly, but you will have to train those transformers on your own data and use a lot of data to get meaningful results. And for many of us, it may not pass the model validation process because of concerns of explainability, and also concern on the robustness if the data is not enough large. So why do I think transformers are still revolutionary as a product manager? What I particularly like with transformer is their ability to work with semantic, to understand semantic and connect semantics. And I think is a result that we can use to improve feature engineering. In feature engineering, we are working with many different assets and concepts that contain semantics. And there is opportunity to use transformers and generative AI to connect all those assets together. So I will give some examples of how generative AI can help feature engineering and build and how he can help create those features that Bard advise us to create the relevant, informative, and transparent features. So when we work on the FeatureByte Copilot, we made 3 key observations. First, we found that generative AI is already very familiar with data modeling concepts. They understand what are the best practices in data modeling. They understand what is a slowly changing dimension table. They understand what are entities. They also can recognize the semantics of data columns well beyond numeric and string. If meaningful names and good descriptions are provided. And it's again a very important result because these allow to connect columns together and make appropriate choice of type of features to create from those columns. We also found that generative AI possesses deep domain knowledge for many different domains. And this can help take some important decisions in the feature engineering process. And it also gives the opportunity to use generative AI to assess how relevant a feature is to a use case. Here, I'm giving a simple example. So we all know that there are different types of numeric columns, and some columns cannot be added together. And a good example of that are rates or any measure of intensity. And it's a concept that generative AI understands well. So I'll just ask him what I can do with whether a split column is additive, semi-additive, non-additive, circular, or categorical column, and he finds that the split column is non-additive, and reminds me that the non-additive column cannot do any sum on the non-additive column, so you cannot do sum of the speed of the cars in the city. It won't be it may be correlated with your target, but it won't be a meaningful and robust feature. Another example how generative AI can help you in feature engineering is so sometimes you have columns in your tables that represent event type. So here we have the example is with a credit card transaction table, where we have a transaction type with 7 types, and I can ask generative AI which type of transaction is the most meaningful for the use case of fraud, and generative AI is capable to make good recommendation and advise me to first focus on purchase transaction, then on cash advance, and then on reversal transactions, and will tell me that bank fees features will not be useful for this use case. Another relevant result is that generative AI can give plain English of explanation of why a feature is relevant. So he can provide a more detailed description of the features, explain what is the score that was used by this feature, can give examples, and can also assess whether these features is relevant to the use case. And here he gives a score of 9 out of 10. And generative AI is also capable to do this, even for complex features. Here is a diagram how FeatureByte Copilot is currently leveraging generative AI. So we use generative AI in two areas. First, we use generative AI to understand the description of the data, the description of table, columns, entities. And also we provided the description of the use case, which domains this use case belong to, the context and the target. And the generative AI is capable to make sense of all this information and map these to our ontology. And this information is used as an input of our feature ideation engine that suggests features with code and description. And we again use generative AI to evaluate the feature and assess its relevance. And the result is a context-aware feature suggestion, where we sort the features by their relevance. We provide the explanation found by generative AI, and also we organize the results by categorizing the signal type that was captured by the feature. So you can either choose to add those features directly to the catalog, or generate notebooks to have the SDK code related to this feature and edit those features to create similar features. Here I give a link of examples of feature SDK and notebooks that we provided in our tutorials. This is my conclusion. So feature platforms and generative AI are accelerating data science in three ways. First, they reduce time to value, thanks to quicker experimentation, thanks to backfilling. Also, by reducing the manual work, you reduce the effort. And we saw that feature platforms allow a smooth transition from experimentation to deployment. They also, the two solutions, the two innovations combined increased production accuracy. We saw that training serving consistency is important to ensure that the production accuracy is aligned with the production that you got during validation. And there are opportunities to create better features. One with transformers by doing a better NLP from a text, and also by getting better feature suggestions that are context aware. And another important outcome of those innovations is that they enhance transparency and give the opportunity to bridge the gap between features and non-technical stakeholders. Thanks to plain English descriptions of features and their relevance to a use case. I think is something really important to achieve a broader adoption of AI in companies. It's important that non-data scientists can understand well what we are doing, and this transparency can improve, increase the trust that those non-stakeholders give us. So that was my last slide. Thank you for sharing with me this experience. And yeah.
Thanks very much, Javier. Fascinating stuff. And I think you're doing some really innovative work here on Gen AI. I'm going to start by asking you a question just about, you mentioned some of the potential contributions of generative AI to feature engineering, from ontology to domain insights to generating code and explaining to stakeholders. Where should you start, or where are you starting? How are you ranking or prioritizing those different ways in which we can add value?
Oh, yeah. So we don't use yet generative AI to generate code.
I do. That's why I think I threw that in there.
Oh, yeah, you are doing it. Oh, okay.
I've asked it to. I have a surfing example where I asked. I said, "Can you please extract the height of the wave at this beach? I'm interested in surfing, and please put in a data frame and so on." And it wrote the code for me, and that saved me. Like I wrote the code a year before. It took me about a day to write. I'm not a great programmer, but GPT-4 was very good. Anyway, sorry, go ahead.
Yes, it's something that I would love to do, and the fact that we have a SDK, the declarative framework make this easier. So you don't need to teach a generative AI to write a complex SQL that can support time travel. But we first focus on mapping the data to our ontology to improve, to make that our feature suggestions are context aware. And also personally, I find that it's really important before using a feature to build intuition on how this feature can contribute to a model. I don't like to look only at the correlation, but to have my own expectation of how this feature can be useful. And I found that actually generative AI was quite good in doing that. And also I found that sometimes as a data scientist, you have nobody to talk to show the feature. Nobody really cares, and I was pleased to see that generative AI lacks some of my complex feature, and I said, oh yeah, they are very relevant to the use case. But yeah, I agree with you. There are many opportunities to use generative AI. Our next step would be to generate a description, automatically descriptions from manually crafted features, and the other step will be to generate the code automatically, like you did.
I find it interesting. You had often when we talk about the types of features, apart from data types, we think of feature types. We often talk about ordinal, where we have an order, and then we can say, well, we have another categorical where we don't care about the ordering and so on. But you talked about summable, and so you're really thinking about feature types and how the feature computations are performed on them.
Yeah. And I find that the feature to categorize the features is something important to organize the feature catalog and to make the search of the features easier. So we try to, we want to categorize the type of columns with our ontology and the type of features in a novel way that make it easier to, maybe to use the columns, and also make it easier to use the features.
Brilliant, and I'm really looking forward to seeing the progress you make in using Gen AI to help build better feature platforms. Brilliant. Thanks, Javier.
Yeah,
and you're calling in from Singapore, are you?
Correct. Yeah,
that's great. And I'm sure it's a strange hour of the day. I won't even ask.
Thank you very much.
Thanks, Javier. Okay. Right, we're getting close to the end. We've got one talk left, so I'm delighted now to have another new, we can say relatively new entrant into the field. I mean, H2O have been around for a long time, and of course AT&T are a very storied, established company. But we haven't had you here at the Feature Store Summit before, so we're delighted to have you here. We have Chris Simicat, who's Director of Customer Solutions for FSI and Strategic Products at H2O. He serves as Product Manager for H2O Feature Store and is responsible for key client relationships with global systemically important banks and other financial institutions. He has over a decade of experience as a data and AI leader, and he's worked at Fortune 50 and 1,000 enterprises and startups. He's successfully spearheaded and contributed to over 100 use cases spanning fraud, cybersecurity, pricing, customer acquisition, recommendations, forecasting, with revenue growth surpassing $250 million. Chris thrives in tackling data and AI challenges, crafting solutions, and delivering impact. And joining him, we have Prince Paulraj, who's he's the head of Chief Data Office at AT&T India Development Center, accomplished leader in the field of data and AI, made contributions to AT&T through his work in various initiatives. He works particularly on innovation, especially in the realms of AI, Gen AI, and his achievements include delivering over $1 billion in benefits to the company over multiple departments. A strong technical background and leadership skills have enabled him to execute and deliver multiple and numerous AI products, including the H2O Feature Store developed in conjunction with AT&T, Fraud AI, Watchtower, Hyperlocal Offer Recommendation System, and AI-driven domain agnostic matching and mapping. Great to have you both here. Go ahead, and the stage is yours. Prince, I don't think we hear you yet. Okay, well, we have an X showing. It wouldn't be a live event if we didn't have a technical hitch at some point. So,
all right. So, hey, Jim, this is Prince. Are you able to hear me?
Yes, we hear you great, loud and clear.
Awesome, Jim. And Chris, can you just bring the slides for me, please?
All right, guys, everything's good. We're good to go.
Awesome. Okay, hello everyone. So today I'm tag teaming, with Chris, and there are three important topics that we're going to discuss it today. All right. So the first one is talking about H2O and AT&T together co-developed a product called Feature Store, and want to give you a simple overview about that particular product. The second thing that I want to more focus on, how actually we use this H2O Feature Store in AT&T, and it's not just for a data scientist, also for citizen data scientists. So we're going to show you the entire flow of how we are operationalizing this entire AI at the scale of AT&T using the Feature Store. The third one is Feature Store and Gen AI. We put together a small video clip to show you guys how actually Feature Store also really helping us in the world of Gen AI application side of it. So those are the three important topics today we're going to cover. So first one, let me talk about the overview about H2O Feature Store. So if you ask any data scientist, if you ask them, where do you spend most of your time? 80% of their time they spend finding the data, collecting the data, cleansing it, and creating this valuable features that's really helping anyone if they are building any sort of a machine learning model. So most of the time, they spend time in preparing those features, and these all features, if you think about it, it's sitting in data scientist's laptop, or maybe somebody stored in a database, or somebody trying to put it in some cloud storage place. But this is such a valuable assets. If you take any company, you really want to keep it in one place and try to make use of it across the entire organization, right? So that's a very key important factor. So 80% of your time, if you think about it, and you create that hundreds and thousands of features, you want to store it in one place and reuse it as many times you can. So move on to the next slide, please. So the next slide, I just want to talk about the data that it's been, produced in the organizations, right? It's there in the form of real time, or it is there in the form of batch mode, or even in real time. And we get all these data sets, and we use multiple data pipelines in order to do that feature engineering, right? I'm just naming few products in industry, right? So we have Databricks, Snowflake, and Palantir and use Azure ML or AWS, or somebody can even simply use Jupyter Notebook, right? Doesn't matter which pipeline actually you are producing those features, because these all features can come in a different pipeline. But how about we store all of them in one place? We store them in offline mode, because that really helps the data scientists to really train their model, right? They can experiment looking at all the different features, and they can create best model that they want. But at the same time, how about all those features also available for us in the form of an online store? So that you can quickly do the lookup. Sometimes you need to score the models in milliseconds. You can use definitely the online feature store. And if you have both these features, either sitting in offline or online, but you got to know the metadata about these features. So that is also, if you package all of them in one single storage, and either you're using it in the consumption standpoint, training side, or real-time predictions or batch predictions, you can easily use it. These are the 4 important steps. If you take any data pipeline, whether you're working with the data or preparing the machine learning model during a training or predictions, it can be used. So that's the concept behind this H2O feature store, keeping it all in one place and making it available either offline or online. So the next slide, I will talk about how actually we are using it in AT&T, right? You can think about AT&T being such a big company. We have more than 250 professional data scientists out there. But today, all of our data scientists have been onboarded into Feature Store, right? And they derived or they produce the features. There are about 40,000 features sitting in the Feature Store. And there are more than 200 machine learning models has been onboarded into the Feature Store. So you take any particular machine learning model, but if you try to look at the lineage about the model, and these features, they are categorical variables or like numerical variables. Some of them are velocity features, something you derived it, in a direct way or indirect way or a relational manner. Some of them are streaming features. Doesn't matter. All these features, because I explained you, we have the online feature scoring capability, as well as you can do the offline. It's all sitting in one place. That's the good about H2O feature store. So today, because we have these 40,000 features and 200 machine learning model, it's not just our professional data scientists. The very important element that I want to highlight here, there are more than 200 citizen data scientists are using it. So these features that they created, it's not just only used at the time of model training or scoring, but citizen data scientists can also come and do a simple data lookup to understand those features. Maybe they can use it part of their business process. They can insert the data if they want to take some actions out of it. So end of the day, these features, we think it's a valuable assets for the data science overall, but we are able to handle those features even in citizen data scientists. Some of them are SQL savvy, right? Some of them, they don't even know anything about it, but they can able to use these features and part of their business process. And the second thing that I just also want to highlight here, in fact, I'm going to talk about 2 real-time model serving use cases. The first use case is, it's actually taking multi-million transactions, and it has to, the model that what we deployed in the platform needs to respond in milliseconds also. So if you go to the next slide, I'm going to talk about fraud use case, right? AT&T being a telecommunication company, anyone else in the industry, fraud is $1 billion problem for us, right? So the bad actors, they daily come up with a different, new scheme of things, and come and try to victimize our customers. So it's very important for AT&T how we protect our customers, right? Doesn't matter what form of this the fraudsters are attacking us, but we have to protect our customers. At the same time, we have to give a very balanced approach in customer experience as well. We don't want to create more frictions. So it is important that these all features that all our data scientists in AT&T they produce, we want to keep it in one place and really make it happen when we talk about like millions of transactions, fired across a different, omni-channel. I'm showing actually in the next slide overall high-level view, right? If you just go with me from the left to right, there you can see anyone showing up to AT&T retail store and they want to buy a phone or upgrade a phone, add family member whatsoever, or you go to AT&T.com and trying to do those activities, or you're calling our customer care agent and trying to purchase a phone. Doesn't matter, you come any one of our omni channels, and we collect all these features. The moment you engage with us in that sort of a platform, generating those features and storing them in Feature Store. That's why you see even part of the injection process itself, the Feature Store has been kicked in and actually is working behind the scenes for us. And we have put together the pipeline in place, and it's actually collecting those features, for that particular transactions. So then, doesn't matter, you come through any one of the channels, either you're logging in or adding stuff to a card or checking out or shipment. These are all the 4 high-level, transactions that I'm talking about, but there are like, hundreds of transactions happens in the overall workflow. But anytime you do any one of those things, the machine learning models, there are like more than 50 machine learning models running behind the scenes and trying to understand, this particular transaction is fraudulent or authentic. Right. And there you can see we are also using, H2O driverless AI. So it's very important for us to not just only use the features that what we created and trying to see that in the combination of driverless AI, it is really, making sense to us to understand a particular transaction is a fraud or not fraud. And of course, based on the model outcome, in a real time during the serving time, we are taking some sort of an action. So in a nutshell, even the serving side also our online Feature Store has been used. So if you think about a simple real time AI pipeline, right from where we are gathering the data because a particular transaction is happening, then creating those valuable features, then keeping them part of this machine learning model and scoring them, and then really taking the remediation during the serving time. All the angle this Feature Store has been plugged in part of the platform. So that shows you how this H2O Feature Store is really helping us the entire journey of one particular transactions. This all needs to happen in milliseconds, by the way, right? And 24/7. That's the sort of an operations we are running against the H2O Feature Store. So if you go to the next slide. So here I'm talking about another use case, right? So this use case, like anyone else in industry, obviously we have to take care of our customer churn. Someone you can think of it, the Feature Store is not just a storage standpoint for us to keep these features, but at the same time, it's giving a shopping experience, right? Anyone can get into the Feature Store and they can shop around the features. It was created for a different context by different data scientists, but maybe those features are useful us, right? I mean, can we just do the experimentation and see do we get any performance, right? That's what happened in one of our machine learning model by our data scientists. And before, they used the Feature Store, they had the accuracy about 66, percentage. But obviously they went to the Feature Store and they looked for some of the features. And in just a matter of 2 hours, the Feature Store, when they looked at the features, and especially some features related to the account activity, that really lifted the model, the performance. And so, we got about 11% increase in our, kind of a lift we got it in our machine learning model. So this is another use case that I'm just talking to you. When you operationalize this Feature Store, one side I shown to you how it's really helping us during the real-time pipeline. The other side, even for a shopping experience, you're going to look at those, features. Like I mentioned, we have 40,000 features. That's really helpful, right? When you have 200 model, in place, you can shop around and getting this sort of a lift. It's really awesome for us. So these are the, the 2 important use cases that I just want to explain to you guys when we are operationalizing this Feature Store, end-to-end fashion, not necessarily from the, the model training, but all the way to the endpoint of model serving as well. So let's go to the next slide, please. So the next one, we're going to show to you a small a demo of how actually this feature store also, used in the context of Gen AI. We all know that Gen AI is kind of a big disruption, I would say, right now in the market. It's a hockey stick growth. But how actually we are using the feature store, how it's really getting into the context. And Jim, sorry, Chris, you have a video? Yeah, so I'm going to, search one particular feature set, Kaggle. You all know that this is a Titanic disaster, the feature set. And you can look at our GUI, that how it looks like, the H2O feature store. You have all sort of, description about that particular feature set and all the features, the time to live or time travel, or even the governance standpoint, whether it's a spy data or not, along with the version control, all those things in place. In the right-hand side, you can kind of see the features. I'm just clicking off some of the features here. The people who surveyed, either it's a numerical feature or categorical features. You can kind of see all those features in the right-hand side, right? So now I'm getting into this AT&T Gen AI, a use case standpoint. Now a citizen data scientist is asking a question, just to brief me the description about this particular feature set, right? So this is a citizen data scientist. And when they ask, it definitely brings the description about that particular feature set. It's talking to the feature store and getting it. And second time now I'm asking a bit more complicated question. Show me the count and percentage of all the passengers who survived and did not survive by ticket class, right? And here I'm also asking group by some of the factor, and look at that, the answer that is coming from feature store, right? So that's the way we are using the feature store. I'm just asking some other question over here. So the context here is a citizen data scientist who can simply ask using a natural language, simple English, and when they ask questions, we are able to generate the query very native to the feature store. And from the behind the scenes of the feature store, we are able to pull the data and present it to the users where they can able to consume it in a simple queryable fashion. So these features what's sitting in feature store, it's not just there in offline and online, because we have a very good metadata associated with these features. Now you can get into the Gen AI mode and you can just ask a simple question. It can able to produce the answers straight away from the feature stores. So those are the three things today we want to talk about it, and how this H2O feature store is so unique in a manner, and also how we are using it in AT&T. With that, I just want to conclude. Any questions about H2O feature store? I have my contact details over here, as well as Chris from H2O. So this is a code developed between AT&T and H2O. And please, we have our LinkedIn profile as well. So any question, please, talk to us, and we are ready to help you.
Thanks a million, Prince. And thanks, Chris. This has been really great to hear some of the that you have all those data scientists, hundreds of them working on the same platform. I'm really fascinated about the citizen data scientist, because we've seen the previous talk we had FeatureByte talking about generative AI as a way to help people define features and to understand the domain and have domain knowledge. What's your take on the role of, I guess, citizen data scientists in feature stores? Like, what will they be doing to help create features, and will we make it easier for them to create features? We had a lot of talks today about very complex feature engineering, with streaming and batch and so on. What's your take of the role of the data analyst or citizen data scientist?
So, maybe I just, talk about the two things, right? So one is that these features, if you think about it, some of them are very simple features, right? You get into a simple pipeline and you compute those features, and and publish them into the feature store, then it's really available for anyone, either data analysts or a citizen data scientist. They can consume it. But if you really think about the other side of it, sometimes we create very complicated features, right? And especially when we use this H2O feature store, even we use the H2O driverless AI, that can even create an exponential number of the features, looking at the features that what we have it in feature store. So it's also, from a data scientist standpoint, it's not just a store where you can keep these features. Now we can also recommend some of the features to the data scientist. That is number one, that's coming as a value add. And second thing, there are new features has been introduced. That is another good thing about it. And all these features are now available in one place. The citizen data scientists don't really know about how this feature has been computed and all the complex and all those things behind logic behind it. They're going to access it like one database, one table where you have all the data. That's the simplest form. They can just query the data. And now with the with all this Gen AI into play, now even you don't need to write a query, right? You ask simple questions and it can able to produce those features. Then you try to see those features is helping, and some of the features are really helpful because they are sometimes easy to understand and inserted part of their business process. So twofold. One is the data scientist also getting a benefit here, and second one is as citizen data scientists, they don't worry about the pipeline, they don't worry about how it is being computed, but at the end of the day, they can use it for part of their business process.
Yeah, I mean, actually, one point that might be interesting would be to think about the metadata aspect. Like, so, if you're a citizen data scientist, you can obviously describe the feature, you can describe its domain and so on, and its usage. And I think there's opportunities there for using Gen AI to link that extra description that you get with the computations and the usage and the models that will be put into it. I don't know if you've been looking at that at all.
Yeah, one thing that's a little bit unique in the feature store that we co-develop is that the fact that you can introduce artifacts to associate with what we call feature sets or with the projects. And so being able to incorporate that with the language models, then you can have a conversation to help contextualize not just the technical metadata, like show me how many, what's the cardinality of this, categorical or what's, the IQR of a continuous feature, but also like help me understand the business context. Is this a fraud data set or is it a customer relationship churn data set? And, when might I, have an opinion on when I might need a little bit of both?
Yeah, I think, Chris pointed out a great point here. So you take one particular feature set, right? I mean, I think you have seen it, while we are showing that video demo here. We have something called artifacts where you can even point out your wiki page about that particular feature set or features that you're talking about, right? Or you can upload a document about that particular feature set or how you use those features part of your model development, right? Or you have a model lineage document you can also attach to it. So now you have the data, the features, along with that, you have these documents. Now the Gen AI definitely, connecting the dots. Now we are able to produce the desired result. In fact, you saw the demo now when, Chris was showing a demo, somebody's asking a question, it's giving answers back. It's not just, a hard-coded query or something, right? It is auto-generated query that it's able to do it with the help of the metadata that we captured behind the scenes for all the features. And also user is adding more data towards the, that particular feature set, like, let me share a wiki link there. Maybe I put my Word documents there. Maybe I got some PowerPoint, let me host it there. But all those things now available, right? So with the help of a Gen AI, we are able to, make use of those valuable metadata.
Brilliant. And I definitely think the more data, the better. We know that with AI.
Right.
Brilliant, guys. Thanks a million. It's been great to have you. And, if there's questions on the Slack, go ahead and jump on there. And with that, we're at the end. That's it. I think we've had the best year. I will say, we think we've had the best year of talks so far. Great quality, no hitches, live event, always potential for hiccups, gone very well. And I'm really glad to have a growing and thriving community, which is fantastic. And thank you to everybody who stuck it out for the entire day. I know we've had people joining globally from all over, so we have people joining and leaving as the sun sets and the sun rises, and all for the speakers who've come in at the awkward hours of the day for many of them. And we'll be back again next year. And if you're interested more about feature stores, of course, you can go to featurestore.org. You can join the Slack channel. You can contribute, look at things like the benchmark that we presented this year. And, you know, we're really happy that people have been here. The videos will be out by the end of next week. They'll be on YouTube. And thanks very much for attending. Have a great rest.